The universe is already incredibly huge, but scientists keep telling us that it's still getting even bigger. This might sound strange. What does it really mean for the universe to expand? When we hear expanding, we might imagine objects flying away from each other through space. But in this case, it's not the objects moving through space, it's space itself that's stretching. Galaxies are drifting apart, not because they're zooming through space, but because the space between them is growing. But if the universe is expanding, then what is it expanding into? Is there something outside of the universe, or is space endless? Before we dive into these questions, let us know where in the world you're watching from, and what time it is for you right now. Drop it in the comments below, and settle in for a fascinating journey to the edge of the universe. At the beginning of the 20th century, most scientists believed that the universe was fixed and unchanging. The common idea back then was that the universe had always existed exactly the way it looked, with stars and galaxies staying in the same place forever. People thought the cosmos was eternal, still and unshakable. But this idea started to change when astronomers began looking more carefully at the light coming from distant galaxies. One man, in particular, played a huge role in turning this old belief upside down. His name was Edwin Hubble, an American astronomer whose discoveries would completely transform how we understand the universe. Edwin Hubble worked at Mount Wilson Observatory in California. There, he had access to an amazing new tool, the Hooker telescope, which was 2.5 meters wide. At the time, it was the most powerful telescope in the entire world. Thanks to this telescope, Hubble could study very faint, faraway objects in the night sky that had never been seen clearly before. At first, scientists weren't sure whether these fuzzy patches of light he saw were just clouds of stars inside our own Milky Way galaxy, or something entirely different. But Hubble proved something incredible. Many of those faint smudges were actually entire galaxies on their own, located far beyond the Milky Way. This was a major breakthrough. It meant that the universe was much larger than anyone had imagined. But Hubble didn't stop there. As he studied these galaxies more closely, he noticed something strange and fascinating. When astronomers measure the light coming from distant galaxies, they look at its colour, or more specifically its spectrum. Hubble saw that this light was shifted toward the red end of the spectrum, a phenomenon known as redshift. What is redshift? It's something that happens when light waves are stretched out, making the light look redder. It's very similar to a common experience with sound. When an ambulance drives away from you, its siren sounds lower and more stretched out. That's called the Doppler effect. Redshift is like the Doppler effect, but with light instead of sound. This redshift told Hubble something important. The galaxies he was looking at were moving away from us. And the farther away a galaxy was, the faster it seemed to be moving. Hubble didn't just find this happening with a few galaxies, he saw the same pattern over and over again. This consistent pattern came to be known as Hubble's law. What did this all mean? It meant that the universe was not standing still at all. It was expanding. All the galaxies were slowly moving away from each other, as if space itself was stretching like a balloon being blown up. And if the universe is expanding now, that must mean that in the past everything was closer together. If you go far enough back in time, it suggests there was a moment when all matter and energy were packed into an incredibly small, hot, and dense point. Then, suddenly, everything began to expand outward. This powerful idea became the basis for what we now call the Big Bang theory, the theory that the universe had a beginning. When we hear that the universe is expanding, it's easy to picture galaxies and stars flying through space like rockets, zooming away from each other in all directions. But that's not quite what's happening. The truth is even more fascinating. The galaxies themselves are not racing through space like cars on a road. Instead, space itself is growing and stretching, carrying the galaxies along with it. This small difference changes everything. It completely shifts how we imagine the universe and how it behaves. When scientists talk about the expanding universe, they don't mean galaxies are just drifting apart across space. They mean the very fabric of space is getting larger over time. A good way to picture this is to imagine a balloon. Now think of little dots drawn on the surface of that balloon. These dots represent galaxies. As you blow air into the balloon, the surface stretches, and the dots move farther and farther apart, not because the dots are crawling across the surface, but because the surface itself is expanding. That's very similar to how the real universe works. This idea of space expanding rather than objects moving through space isn't just a fun thought experiment. It changes how we understand the entire structure of the cosmos. Usually we think of space as a kind of empty stage where planets, stars and galaxies exist and move around. But in reality, that stage is not standing still. It is growing. It's as if the stage itself is being built while the play is happening. Because of this, something amazing and strange happens. The farther away a galaxy is from us, the faster it seems to be moving away. That's because there is more and more space stretching between us and those very distant galaxies. Some galaxies are so far away, billions of light years, that they appear to be rushing away at unbelievable speeds. This isn't because they're speeding through space, but because the space between us and them is expanding very rapidly. One of the strangest and most mind-blowing results of this is that there are galaxies so far away that their light will never reach us. Even if they shine their light for billions of years, the space between us and them is growing faster than the light can travel. It's as if the galaxies are being pushed beyond our sight by the stretching of space itself. This means that, although the universe is filled with galaxies, there are parts of it that we will never be able to see. These regions lie beyond what scientists call the observable universe, the part of the universe from which light has had time to reach us since the universe began, which happened around 13.8 billion years ago. But this stretching of space doesn't affect everything. For example, the Earth is not being pulled away from the Sun. Your chair isn't moving away from your desk because of expanding space either. That's because gravity is strong enough to hold things together on small scales. In places like solar systems, galaxies, or even galaxy clusters, gravity wins the tug of war, and space doesn't expand in a noticeable way. The expansion of the universe only becomes noticeable over vast distances, millions or billions of light years apart. Another strange but important idea is that there's no center of the universe. There isn't one special point where the expansion began, and everything is flying away from it. Every point in the universe is stretching, and from any galaxy you look at, all the other galaxies seem to be moving away. Imagine standing on any one of those dots on the balloon. No matter which one you choose, it will look like all the other dots are moving away from you as the balloon expands. That's exactly what astronomers see when they look through their telescopes. This idea was very hard for scientists to accept at first. It's not how we experience movement in our daily lives. In our world, when something moves, it moves across a fixed background, a road, a field, or the floor. But in the universe, even the background is changing. It's as if the floor beneath your feet was stretching while you walked, carrying you without you even realizing it. The story of how our universe expands doesn't start with a slow and steady stretching of space. Instead, right after the Big Bang, something wild and astonishing happened, a sudden and unbelievably fast growth called cosmic inflation. This burst of expansion didn't last long. In fact, it happened in less than a trillionth of a second. But even though it was brief, it left a huge and lasting mark on the universe we live in today. In those very first moments after the Big Bang, the universe was a scorching hot, incredibly dense mix of tiny particles and energy, a sort of glowing, chaotic soup. But almost instantly, space itself began to expand at a speed far greater than anything we see now. During this tiny window of time, the universe grew from something smaller than a single atom to something that was light years across. And all of that happened in less than 1 second. This incredibly rapid growth smoothed out the early universe. It erased any major clumps or rough spots, making everything surprisingly even and balanced. But at the same time, tiny little ripples in density were left behind. These slight bumps and dips, barely noticeable, were very important. They became the seeds from which stars, galaxies, and planets would later form. Without this dramatic inflationary event, the universe might not have turned out the way it did. It may have remained too chaotic or too clumpy to support the kind of structure needed for life. But thanks to inflation, the universe became vast, mostly smooth, and just varied enough to allow galaxies, stars, and even people to eventually come into being. Inflation set the stage for the slower, more gentle expansion that followed, which has continued ever since, shaping the universe's current size and structure. For a long time, scientists thought this expansion would eventually slow down. That made sense. After all, the force of gravity from all the galaxies, stars, and matter should have been pulling everything back together, at least a little bit. But then something unexpected happened. In the late 1990s, two teams of astronomers were studying supernovae, bright explosions that happen when certain stars reach the end of their lives. By looking at distant supernovae, the scientists hoped to measure how fast the universe had expanded in the past compared to now. But the results shocked everyone. These faraway supernovae were dimmer than expected, which meant they were farther away than they should have been, if the expansion was slowing down. Instead, this strange discovery revealed that the expansion of the universe wasn't slowing down at all. It was speeding up. To explain this puzzling behavior, scientists came up with the idea of dark energy, a mysterious invisible force that seems to push galaxies apart and overpower gravity. Today, scientists believe that dark energy makes up about 70% of all the energy in the universe. But the strange thing is, we still don't really know what it is. Unlike ordinary matter, which clumps together to form stars and planets, or even dark matter, which gathers around galaxies, dark energy doesn't bunch up. It seems to be spread evenly throughout all of space. And as the universe expands, dark energy doesn't thin out. It keeps on filling the new space that forms. In fact, one theory says that dark energy could actually be a built-in feature of space itself. As more space forms, more dark energy appears, making the universe expand even faster. It's like a snowball effect. Expansion creates more expansion. Another idea is that dark energy is connected to something called the cosmological constant. This idea was first introduced by Albert Einstein when he was developing his theory of general relativity. Back then, most scientists believed the universe was static, not expanding or shrinking. So Einstein added the cosmological constant to his equations to make the math fit that belief. But when Edwin Hubble later discovered that the universe was actually expanding, Einstein dropped the constant and called it his biggest mistake. Now, because of dark energy, that old idea is making a comeback. Some scientists think that the cosmological constant might actually be a real part of nature, something woven into the fabric of space itself. If that's true, then dark energy might not be some new, unknown force, but something Einstein had already predicted, even if he didn't realize it at the time. This discovery has raised some deep and troubling questions about the future of the universe. If the expansion continues to speed up, what will happen in the far, far future? One possibility is known as the Big Freeze. In this scenario, galaxies will drift farther and farther apart, stars will eventually run out of fuel, and the universe will grow cold and dark, slowly fading into silence. Another idea is even more extreme, the Big Rip. If the force of dark energy grows stronger and stronger, it could eventually tear apart galaxies, stars, planets, and even atoms themselves. Everything in the universe could be ripped to pieces by the accelerating expansion. The universe is full of mysteries, and one of the biggest is dark energy. This strange force is responsible for making the universe expand faster and faster. Scientists believe that dark energy makes up about 68% of everything in the universe. In contrast, dark matter, another mysterious substance, accounts for about 26%, while all the regular matter, the stars, planets, and everything we can see, only adds up to about 5%. Other forms of energy, such as light particles, photons, and neutrinos, are so tiny in comparison that they barely count. Even though dark energy has an extremely low density, about 7 times 10 to the power of negative 30 grams per cubic centimetre, it still dominates the universe. This is because, unlike matter, which clumps together into galaxies and stars, dark energy is spread evenly across space. No matter where you go in the universe, dark energy is always there, filling every inch of the cosmos. Scientists first suspected dark energy existed when they studied distant exploding stars known as Type Ia supernovae. These supernovae act as cosmic measuring sticks because they shine with the same brightness no matter where they are. By looking at how their light stretches as it travels through space, a phenomenon called redshift, scientists can figure out how fast they are moving away. What they found was shocking. Instead of slowing down, the universe was expanding faster and faster. This was the opposite of what scientists expected. Before this discovery, most believed that gravity from all the matter in the universe would gradually slow down the expansion, much like how a thrown ball slows before falling back to the ground. But the data showed that something, some unknown force, was pushing the universe apart. That force was later named dark energy. There are several ideas about what dark energy could be. One of the leading explanations is called the cosmological constant. This idea suggests that dark energy is a constant, unchanging force that fills space. It's sometimes described as the energy of empty space, or vacuum energy. Another possibility is that dark energy comes from scalar fields, a type of energy that changes over time and space. These fields could behave differently in different parts of the universe, making dark energy more dynamic. Some versions of this idea include quintessence and moduli fields. Other theories suggest that dark energy could interact with gravity in unknown ways. One idea, called cosmological coupling, proposes that dark energy and gravity might be linked in a way we don't yet understand. Another theory, interacting dark energy, suggests that dark energy might be influenced by other unseen forces in the universe. The idea of a mysterious energy filling space actually goes back to Albert Einstein. In the early 20th century, Einstein introduced a term called the cosmological constant, L lambda, in his equations of general relativity. At the time, scientists believed the universe was static, neither expanding nor contracting. To make his equations fit this idea, Einstein added the cosmological constant, which acted as a force counteracting gravity, preventing the universe from collapsing in on itself. However, in 1929, the astronomer Edwin Hubble discovered that the universe wasn't static at all. It was actually expanding. This made Einstein realize that his original assumption was wrong. He later called the cosmological constant his greatest blunder. Ironically, decades later, scientists would find that a repulsive force, what we now call dark energy, was indeed pushing the universe apart, meaning Einstein's idea may not have been a mistake after all. In 1980, physicists Alan Guth and Alexei Starobinsky proposed a groundbreaking idea called cosmic inflation. This theory suggests that just after the Big Bang, the universe went through a brief but extremely rapid expansion, growing at an unimaginable speed. This inflationary period shaped the structure of the universe and explains why galaxies are distributed the way they are today. Inflation seems similar to dark energy, as both involve the rapid expansion of space. However, the energy driving inflation was much stronger than the dark energy we observe today. Scientists are still trying to understand if these two forces are connected, or if they are completely separate phenomena. By the 1980s, scientists had developed models of the universe that relied heavily on cold dark matter, CDM, a form of dark matter that moves slowly compared to the speed of light. These models did a good job explaining how galaxies formed, but they had some inconsistencies. For example, they predicted a slower Hubble constant, the rate of expansion of the universe, than what astronomers actually observed. The situation changed in 1992 when NASA's COBE spacecraft discovered slight irregularities in the cosmic microwave background, CMB, the faint glow left over from the Big Bang. This discovery pushed scientists to reconsider their models. A major breakthrough came in 1998, when astronomers studying distant supernovae found clear evidence that the universe's expansion was accelerating, not slowing down. This was the first direct proof that dark energy was real. More discoveries followed. In the early 2000s, experiments like Boomerang and Maxima analyzed the cosmic microwave background and found that the universe's total energy density was very close to what is known as the critical density, the exact amount needed to make the universe flat on large scales. However, when scientists measured the amount of matter in the universe, they found it was only about 30% of this critical density. The missing energy was explained by the presence of dark energy. Further confirmation came from the 2-degree field, G2DF Galaxy Redshift Survey in 2001, which measured the distribution of galaxies and showed that dark energy was needed to explain the observations. Then, from 2003 to 2010, NASA's WMAP satellite provided even more precise measurements of the cosmic microwave background, solidifying the lambda CDM model as the best explanation for the structure and evolution of the universe. The name dark energy was first used in 1998 by physicist Michael S. Turner, following the earlier term dark matter, which had been coined by Fritz Zwicky in the 1930s. Despite all these discoveries, dark energy remains one of the biggest puzzles in modern physics. Some scientists believe it could be a fundamental property of space itself. Others think it might be linked to quantum mechanics, the strange rules that govern particles at the smallest scales. Future experiments, including new space telescopes and large-scale galaxy surveys, aim to uncover more clues about this mysterious force. To truly grasp how the universe grows and stretches over time, scientists need to take incredibly precise measurements of its expansion. In the realm of general relativity, researchers figure out how fast the universe is expanding by studying its shape and a crucial concept known as the cosmological equation of state. This equation explains how factors like temperature, pressure, and the combined densities of matter, energy, and vacuum energy interact in different parts of space. One of the biggest challenges in modern cosmology is figuring out the equation of state for dark energy. Scientists believe dark energy plays a major role in the universe's rapid expansion, but understanding its true nature remains a mystery. To study this, researchers include a concept called the cosmological constant in the Standard Model of Cosmology, also known as the Friedmann-Lemaitre-Robertson-Walker metric. This leads to what experts call the lambda cold dark matter model, or lambda CDM model. It's often referred to as the gold standard of cosmology because it closely matches what we observe in the real universe. Since the year 2013, the lambda CDM model has been repeatedly tested and confirmed through highly accurate observations, including data from the Planck spacecraft and the Supernova Legacy survey. Early results from this survey suggested that dark energy behaves almost exactly as Einstein's cosmological constant predicts, with an accuracy of about 10%. More recent discoveries from the Hubble Space Telescope's Higher Z team indicate that dark energy has been influencing the universe for at least 9 billion years, long before the universe began its rapid acceleration. However, despite these findings, dark energy remains one of the greatest puzzles in physics. It appears to be extremely smooth and evenly spread across space, with an incredibly low density. Unlike other forms of energy or matter, it doesn't seem to interact with anything except gravity. Its density is astonishingly small, about 1 divided by 10 followed by 27 zeros kilograms per cubic meter, making it nearly impossible to detect in laboratory experiments. Yet, despite being so faint, dark energy makes up around 68% of the universe's total energy. This is because, unlike matter, which clumps together, dark energy spreads out evenly across all of space, exerting a profound influence on the universe's expansion. One of the leading explanations for dark energy links it to something called vacuum energy. This refers to the tiny fluctuations of particles and antiparticles that constantly pop in and out of existence in empty space, following Heisenberg's uncertainty principle. According to Einstein's theory of relativity, this vacuum energy should have a gravitational effect, meaning it contributes to the cosmological constant. This, in turn, is believed to be one of the main reasons the universe's expansion is speeding up. However, there's a massive problem. When physicists use quantum field theory to predict how much vacuum energy should exist, they come up with a number that is vastly larger than what is actually observed. This enormous gap between theory and reality remains one of the biggest unsolved problems in modern physics. Regardless of what dark energy truly is, for it to drive the accelerated expansion of the universe, it must have an extremely strong negative pressure. In general relativity, pressure acts similarly to mass when it comes to its gravitational effects. Both pressure and mass are part of something called the stress-energy tensor, which determines how matter and energy influence gravity. In the case of dark energy, this negative pressure works against gravity, causing space to expand at an increasing rate. If the universe were shrinking instead, this same pressure would slow down its contraction. This phenomenon is sometimes called gravitational repulsion because it seems to push everything apart, counteracting the usual pull of gravity. When we break down the universe into its main components, we find that everything we know falls into three broad categories: matter, radiation, and dark energy. Matter includes everything that has mass, from stars and planets to tiny dust particles. As the universe expands, the energy density of matter decreases in proportion to the cube of the expansion factor. Imagine you have a box filled with particles. If the box doubles in size, the energy of the particles inside doesn't just get cut in half. It decreases by a factor of 8 because the volume increases in 3 dimensions. Radiation, which includes light and heat, behaves a little differently. As space expands, the energy of radiation decreases even faster than that of matter. This is because, in addition to spreading out over a larger volume, the waves of light and radiation get stretched. This stretching effect, called redshift, makes the radiation lose energy more quickly than matter does. Dark energy, on the other hand, does something completely different. Unlike matter and radiation, its energy density doesn't decrease as the universe expands. Instead, it stays the same, no matter how large the universe gets. In other words, while matter gets diluted as space grows, dark energy remains constant, filling the void evenly and continuously driving the universe's acceleration. Scientists have gathered several lines of evidence that support the existence of dark energy, even though it hasn't been directly detected. Distance and redshift measurements. By studying how the light from distant objects has been stretched over time, scientists have discovered that the universe has expanded more rapidly in recent history than it did in the past. This suggests that something, likely dark energy, is causing this accelerated expansion. The need for extra energy. The universe appears to be flat in shape, meaning it doesn't curve inward or outward. In order for the universe to be flat, there must be a specific amount of total energy present. Since visible matter and dark matter don't provide enough energy to meet this requirement, scientists believe dark energy must be making up the difference. Patterns in cosmic structures. When astronomers study the large-scale arrangement of galaxies and cosmic structures, they find patterns that suggest dark energy is at work. The way galaxies are distributed throughout space provides additional clues about the expansion of the universe and the mysterious force driving it. In the year 1998, a group of astronomers known as the High Z Supernova Search Team made a shocking discovery while studying a special type of exploding star called Type Ia supernovae. They expected to find that the universe's expansion was slowing down due to gravity, but instead they found the opposite. The universe was actually expanding faster and faster. Just 1 year later, in 1999, another team of researchers, the Supernova Cosmology Project, reached the same surprising conclusion. Their groundbreaking work reshaped our understanding of the cosmos and earned them the prestigious Nobel Prize in Physics in the year 2011. Since then, many other scientific observations have reinforced this discovery. Studies of the cosmic microwave background, faint radiation left over from the Big Bang, have provided strong evidence. Additionally, astronomers have examined how light bends around massive objects in space, a phenomenon called gravitational lensing, and have analysed the large-scale structure of the universe. All these findings support the idea that a mysterious force called dark energy is driving the universe's accelerating expansion. Some skeptics argue that the strongest proof comes only from measuring redshift, the way light stretches as objects move away, and the distances of supernovae. However, other evidence, such as patterns in the cosmic microwave background, also suggests that the universe is expanding faster than it would without dark energy. Supernovae are incredibly useful for studying the universe because they act like natural measuring tools, often referred to as standard candles. Scientists know exactly how bright these explosions should be, which allows them to determine how far away they are. By comparing the distance of a supernova with how much its light has been stretched, its redshift, astronomers can accurately track how fast the universe is expanding. Type Ia supernovae are particularly valuable because they always explode with the same brightness, making them among the most reliable cosmic markers. Recent measurements indicate that dark energy makes up around 71% of the universe, while the remaining 29% consists of dark matter and ordinary matter. The leading theory that explains how galaxies, stars, and other cosmic structures form suggests that matter only accounts for about 30% of the universe's total critical density, the amount needed for the universe to be geometrically flat. More proof of dark energy came in the year 2011 from the Wiggles Galaxy Survey, which studied over 200,000 galaxies. Researchers used an innovative technique to measure distances to galaxies located as far as 2,000 million parsecs away. Their results further confirmed that the universe has been expanding at an increasing rate, providing even stronger support for the idea of cosmic acceleration. For the universe to be as flat as it appears, there must be some additional form of energy filling the cosmos. All the observable matter, both regular and dark, accounts for only about 30% of what is needed. The remaining 70% is believed to be dark energy. Data from the Wilkinson Microwave Anisotropy Probe, a spacecraft that mapped the early universe, estimated that dark energy makes up about 73% of the universe. More recent findings from the Planck satellite refined this estimate, suggesting that dark energy constitutes approximately 68%, while dark matter makes up about 27%, and regular matter accounts for just under 5%. Dark energy also helps explain strange patterns in the cosmic microwave background. When light particles, known as photons, travel through regions of intense gravity, such as galaxy clusters or vast empty spaces, they lose or gain energy. This effect creates temperature variations in the background radiation and is known as the integrated Sachs-Wolf effect. It is considered another major clue pointing to the presence of dark energy. Scientists have also started using a new method to study dark energy by measuring the Hubble constant, which describes how the universe's expansion rate changes over time. They focus on galaxies that have evolved in a predictable way, treating them as cosmic clocks. By analysing their ages and redshifts, researchers can estimate the universe's expansion at different points in its history. Despite all this evidence, dark energy remains one of the greatest unsolved mysteries in physics. Scientists agree that it plays a crucial role in driving the universe's accelerating expansion, but they still do not fully understand what it is or how it works. To find answers, researchers are exploring multiple possibilities. Some are revisiting Einstein's theory of gravity to see if modifications are needed. Others are trying to uncover the exact properties of dark energy, while some are even considering alternative explanations based on unexpected cosmic observations. One of the simplest ideas about dark energy is that it is a fundamental feature of space itself. According to this view, even completely empty space contains a form of energy, often called vacuum energy. This concept is known as the cosmological constant and is represented by the Greek letter lambda. It serves as the foundation of the lambda CDM model, which is currently the most widely accepted explanation of the universe's structure. Since Einstein's famous equation shows that energy and mass are connected, this vacuum energy should have a gravitational effect, influencing how the universe expands. However, there is a huge problem with this idea. The calculations from quantum physics suggest that the amount of vacuum energy should be incredibly large, about 120 orders of magnitude higher than what is observed. If that were true, the universe would have expanded so rapidly that galaxies, stars, and planets could never have formed. Yet, we exist in a universe where structures have formed and evolved over billions of years. Something must be balancing out most of this energy, but not completely cancelling it. Scientists do not yet know why this happens, making dark energy one of the biggest puzzles in modern physics. While many assume that dark energy is a constant, unchanging force, some physicists believe it could be something far more dynamic, an evolving energy field that changes over time. This idea is known as quintessence. Unlike the cosmological constant, which remains the same everywhere, quintessence behaves like an energy field spread across the universe, influencing its expansion in different ways at different times. It is thought to be extremely light so that, unlike normal matter, it does not clump together to form stars and galaxies. Some versions of this theory suggest that the universe's expansion is happening slightly slower than what the standard model predicts. However, there is still no solid proof to confirm or disprove this idea. One of the biggest unanswered questions about dark energy is why it became dominant at this particular moment in cosmic history. If it had taken over too soon, the universe's rapid expansion could have prevented galaxies from forming, and life as we know it might never have existed. Some scientists think this is just a coincidence, while others believe it supports a controversial idea called the anthropic principle, the notion that the universe must be the way it is because we are here to observe it. Interestingly, some quintessence models include a built-in mechanism known as a tracker that naturally explains why dark energy became influential at this specific time. According to these models, dark energy's behavior is linked to the density of radiation in the early universe, which could explain its delayed but powerful emergence. Some extreme versions of quintessence predict even stranger scenarios. One of these is phantom energy, a type of dark energy that becomes stronger over time instead of staying the same. If this idea is correct, the universe wouldn't just keep expanding, it would eventually be torn apart in a terrifying event called the Big Rip. In this doomsday scenario, the force of expansion would grow so strong that it would first tear apart galaxies, then stars, then planets, and finally even atoms themselves, reducing everything to nothingness. Another version of quintessence, known as K-essence, suggests that dark energy could be made of unusual energy forms that behave in ways never seen before. Some variations of K-essence even propose the existence of negative kinetic energy, which could have bizarre and unpredictable effects on the evolution of the universe. In recent years, astronomers have discovered inconsistencies in the measurements of the universe's expansion rate. This disagreement, known as the Hubble tension, suggests that the standard model of cosmology might be missing something important. Some researchers believe that only specific types of quintessence models, with additional interactions, can explain this discrepancy. Even though dark energy remains one of the biggest mysteries in modern physics, it is deeply connected to Albert Einstein's theory of general relativity. Some scientists argue that if general relativity were modified in certain ways, we might not need dark energy at all to explain the universe's accelerating expansion. Several alternative theories have been proposed, but so far none have been fully proven. In fact, a key discovery, the detection of gravitational waves from the event known as GW 170817, has already ruled out many of these modified gravity theories. According to astrophysicist Ethan Siegel, while alternative ideas about dark energy often make headlines, most experts in the field still believe that dark energy is real. Competing theories simply do not match observational data as accurately as the current model. Scientists estimate that the universe's expansion started accelerating around 5 billion years ago. Before that, gravity, mainly from dark matter and normal matter, was slowing everything down. But as the universe grew larger, dark matter spread out and became less influential, while dark energy remained nearly unchanged. Eventually, dark energy took over, causing the expansion to speed up. For every time the universe doubles in size, the amount of dark matter in a given space is cut in half, but dark energy stays nearly the same. What happens next depends on the nature of dark energy. If it remains constant, like the cosmological constant suggests, the universe will keep expanding forever. Distant galaxies will move away from us faster and faster, eventually reaching speeds greater than light itself. This does not break any laws of physics, because space itself is stretching rather than the galaxies moving through space. Right now, scientists estimate that the cosmological event horizon, the distance beyond which we can never receive signals or light, is about 16 billion light-years away. If something happens within that range, its light may still reach us in the distant future, but anything happening beyond that distance will be lost to us forever. As galaxies approach this horizon, the light they emit will be stretched into longer and longer wavelengths, eventually becoming invisible. To an observer in the far future, those galaxies will appear to fade away until only our own local group of galaxies remains in an otherwise empty universe. While the idea of an endlessly expanding, dark and empty universe is unsettling, some alternative theories predict more dramatic endings. If dark energy keeps growing stronger, the Big Rip could become reality, shredding everything in existence. But there are also theories suggesting that dark energy might change over time, possibly reversing its effects. In that case, the universe could stop expanding and begin collapsing in a big crunch, eventually shrinking back into a single point, possibly leading to another Big Bang and the birth of a new universe. Another possibility is that dark energy follows cycles, causing the universe to expand and contract in an endless loop of big bangs and big crunches. The expansion of the universe hasn't always followed a smooth, steady pace. Over the course of billions of years, the rate at which space stretches has actually changed. Right after the Big Bang, an event that took place about 13.8 billion years ago, the universe went through a dramatic and almost unbelievable burst of expansion called inflation. This inflation happened in less than a tiny fraction of a second, but it had an enormous impact. Once the inflationary period ended, the universe continued to expand, but much more slowly. During this time, gravity, the natural force that pulls matter together, began to work against the expansion, trying to slow it down. For a very long time, the universe was shaped by a cosmic tug-of-war between the outward push from the Big Bang and the inward pull of gravity. This struggle played a major role in how the universe evolved into what we see today. To figure out how fast the universe is expanding, scientists use a special number called the Hubble constant. This constant tells us how quickly galaxies are moving away from each other, depending on how far apart they are. It's one of the most important numbers in cosmology because it helps scientists figure out the age, size, and future of the universe. The Hubble constant is measured in kilometers per second per megaparsec. A megaparsec is a unit of distance that astronomers use. It's equal to about 3.26 million light-years. So, if a galaxy is 1 megaparsec away, the Hubble constant tells us how fast it's moving away in kilometers per second. In general, the farther away a galaxy is, the faster it's speeding away from us, and the Hubble constant helps describe that relationship. But measuring the Hubble constant is not as easy as it might sound. It requires extremely precise measurements of both the distances to galaxies and how fast those galaxies are moving away from us. One of the most reliable ways to measure distance in space involves using a special type of star called a Cepheid variable. Cepheid variables are stars that get brighter and dimmer in a regular rhythm. They pulse like cosmic heartbeats. What makes them so useful is that the time it takes for them to pulse tells astronomers how truly bright the star is. By comparing how bright the star really is to how bright it looks from Earth, scientists can figure out how far away it is. Once they know how far away the galaxy is, they can then find out how fast it's moving by studying something called redshift. When a galaxy moves away from us, the light it gives off gets stretched into longer, redder wavelengths, just like the lowering pitch of a siren as an ambulance drives away. By measuring how red the light has become, astronomers can tell how fast the galaxy is speeding off into space. With both distance and speed in hand, they can calculate the Hubble constant. Although this method sounds fairly straightforward, the actual results haven't been so simple. Over the years, different scientific teams have come up with slightly different values for the Hubble constant. This has sparked a big debate in the scientific community, known as the Hubble tension, a disagreement over what the correct number really is. There are two main methods used to calculate the Hubble constant, and they don't quite match up. The first method is based on measuring galaxies that are relatively close to us. Astronomers use Cepheid variables and exploding stars called supernovae as cosmic measuring sticks to determine the distance and redshift of nearby galaxies. This method gives a Hubble constant of about 73 kilometers per second per megaparsec. The second method looks much farther back in time, all the way to the cosmic microwave background, the faint glow left over from the Big Bang. This radiation is like a baby picture of the universe when it was only about 380,000 years old. By studying patterns in this ancient light and using computer models of how the universe has changed over time, scientists can estimate how fast it is expanding today. But this method gives a lower number, around 67 kilometers per second per megaparsec. This difference might not sound like much, but it's big enough to raise serious questions. If our understanding of the universe was perfect, both methods should give the same result. The fact that they don't suggest that we might be missing something important in our models of the universe. One possibility is that there's something about the universe we don't yet understand, some hidden part of physics that hasn't been discovered. Our current models rely on assumptions about things like dark energy, dark matter, and gravity. If even one of those assumptions is slightly wrong, it could explain why the two methods disagree. For example, maybe dark energy, the mysterious force that pushes the universe apart, doesn't behave exactly the way we think it does. Or maybe there's some kind of new exotic matter or energy that existed in the early universe but is missing today. If that's true, it could have changed the expansion rate in the past in ways we haven't considered. Another idea is that gravity itself might behave differently on extremely large cosmic scales. Albert Einstein's theory of general relativity has worked very well to explain gravity in our solar system, and even within galaxies. But we've never directly tested how gravity works across the entire universe. If gravity weakens or changes over great distances, it could affect how fast the universe expands, and our current theories might need updating. Some scientists have even proposed new versions of general relativity to explain this. To make things even more complex, we have to consider the possibility that the Hubble tension is not a problem with our understanding of the universe, but a problem with the measurements themselves. Measuring distances in deep space is extremely difficult. Even tiny errors in how we understand Cepheid variables or supernovae could lead to big mistakes in the Hubble constant. If we're slightly off in calculating how bright these stars really are, the entire chain of distance measurements could be flawed. Similarly, the data from the cosmic microwave background relies on complicated models of the very early universe. If those models are wrong in any way, they could be giving us a misleading estimate of the Hubble constant. As the universe has continued to grow over time, the rate of expansion hasn't stayed the same. In the early universe, gravity had a much stronger effect, pulling galaxies toward each other and slowing expansion. That's because everything was much closer together. But as the universe expanded, galaxies drifted farther apart and gravity's grip weakened. Then, about 9.8 billion years after the Big Bang, around 4 billion years ago, something unexpected happened. The expansion of the universe began to speed up again. This renewed acceleration is believed to be driven by dark energy. Today, astronomers are using new tools and technology to get closer to the truth. Telescopes like the James Webb Space Telescope are helping scientists gather more accurate data than ever before. The hope is that with these advanced instruments, astronomers will finally be able to resolve the Hubble tension and find the true value of the Hubble constant, unlocking even deeper secrets about the origin, evolution, and fate of our universe. The expansion of the universe brings up a fascinating and puzzling question. How does gravity, one of the most powerful and fundamental forces in nature, interact with the stretching of space on the grandest scales we can imagine? Right now, we know that the universe is expanding. This means that galaxies are slowly drifting farther and farther apart because the very fabric of space is growing. But here's the interesting part. Even though space is expanding, galaxies themselves, and even groups of galaxies, aren't being pulled apart. Instead, gravity is working hard to keep them together. So we have two competing forces in action: the expansion of the universe, which tries to pull things apart, and gravity, which tries to pull things together. And this cosmic tug-of-war shapes how the universe looks and behaves. Gravity, according to Albert Einstein's famous theory of general relativity, is the invisible force that pulls objects toward each other. It's the reason why planets orbit around stars, why stars gather together into galaxies, and why galaxies bunch up into even bigger structures called galaxy clusters. Without gravity, the universe would be a scattered mess, with particles and atoms drifting randomly through space. There would be no stars, no galaxies, no planets, just a shapeless sea of matter. Einstein described gravity as the bending of space-time. Mass, meaning anything that has weight or substance, can bend the fabric of space and time, creating a sort of dip that pulls other objects toward it. The more massive something is, the stronger this gravitational pull becomes. Now here's where it gets really interesting. While gravity is busy holding things together on small and medium scales, space itself is still expanding on the larger scales. But this expansion doesn't work like things moving through space, such as cars on a road. Instead, it's space itself that is stretching, and the galaxies are being carried along with it, like raisins in a rising loaf of bread. This stretching becomes noticeable when we look at objects that are extremely far apart, millions or even billions of light years away. But on smaller scales, within a single galaxy or a group of galaxies, the force of gravity is much stronger than the force of expansion. That's why galaxies don't stretch out or fall apart. The stars inside a galaxy, along with dark matter, which we'll talk about shortly, are packed closely enough that their gravity overpowers the tiny pull of expanding space. Within galaxies, the expansion is so weak that it basically has no effect at all. Let's take our own Milky Way galaxy and its closest big neighbour, the Andromeda Galaxy. You might think that because of cosmic expansion, these galaxies should be drifting apart, but in fact they're moving toward each other. That's because their mutual gravity is pulling them together so strongly that the effect of expanding space in their local region doesn't stand a chance. Eventually, in a few billion years, the Milky Way and Andromeda will collide and merge into one giant galaxy. This is why scientists say that cosmic expansion only really matters on the larger scales, the cosmic scale. That means the really, really big distances between galaxy clusters, not the spaces within them. Even in giant clusters where hundreds or even thousands of galaxies are packed together, gravity still rules. Galaxy clusters are among the biggest structures in the entire universe, and gravity is what holds them together. The space between these clusters is expanding, yes, but the galaxies inside a cluster stay tightly bound, orbiting a common centre of mass like bees around a hive. But what will happen in the far future if the universe keeps expanding faster and faster? Scientists believe that the expansion is being driven by something mysterious called dark energy, which acts like a force pushing the universe apart. If dark energy becomes too strong, it might eventually win the tug of war against gravity. If that happens, even the mighty force of gravity might not be enough to hold galaxies, stars, or even atoms together. Some scientists have imagined a dramatic ending to the universe called the Big Rip. In this extreme future scenario, dark energy would stretch space so violently that first galaxy clusters would come apart, then galaxies themselves would be torn to shreds, and finally even individual atoms would be ripped apart. The universe would become a cold, empty, and lifeless place, with nothing left but isolated particles drifting in endless darkness. But for now, gravity is still holding strong. It keeps stars circling inside galaxies, galaxies circling inside clusters, and it continues to shape the large-scale structure of the universe. There's one more important piece of this puzzle, something called dark matter. Dark matter is a strange and invisible kind of matter that we can't see because it doesn't interact with light or any other type of radiation. We know it exists because of the odd effects it has on gravity, which can't be fully explained by the laws of physics unless there's more matter around than we can actually see. These strange effects show up when we study things like how galaxies form and change over time, how light bends around huge objects called gravitational lensing, and even the way galaxies move within groups. We also notice its influence in the structure of the universe and the leftover radiation from the Big Bang. In the most widely accepted model of the universe, known as the lambda CDM model, the universe's total mass and energy is made up of 5% regular matter, 26.8% dark matter, and 68.2% dark energy. That means dark matter makes up about 85% of the total mass, while dark matter and dark energy together make up 95% of the universe's total energy. We don't know exactly what dark matter is, but it doesn't seem to interact with regular matter or light, except through gravity, making it nearly impossible to detect with our current technology. The main theory is that dark matter might be made up of tiny unknown particles, such as weakly interacting massive particles or axions. Another possibility is that dark matter could be made of ancient black holes from the early universe. Dark matter can be grouped in different ways based on how fast its particles move: cold, warm, or hot. Most scientists think dark matter is cold, meaning its particles move slowly, allowing them to gather together and form structures over time. While most astrophysicists believe dark matter exists, some still question the idea. A small group of scientists, confused by certain observations that regular dark matter doesn't fully explain, suggest that maybe the laws of gravity need to be changed. They've proposed alternative theories like modified Newtonian dynamics or new types of gravity, but none of these theories can perfectly explain all the evidence we've gathered so far. This suggests that, even if gravity needs some changes, dark matter still seems to be an important part of the puzzle. The idea of dark matter has a long and fascinating history, filled with interesting discoveries and theories that laid the foundation for our current understanding of the universe. The story begins with the work of some of the brightest minds in science, starting in the late 19th century. In 1884, William Thomson, better known as Lord Kelvin, made some interesting observations. He talked about the possible number of stars around our Sun in a book based on a lecture series he gave in Baltimore. Kelvin was trying to estimate the number of stars near the Sun. He did this by studying how stars moved around our solar system. Using this information, he wondered what would happen if there were 1 billion stars within a distance of 1 kiloparsec from the Sun. At this distance, the stars would appear to move in ways that were hard to explain, and this idea led to further thinking about invisible matter in space. Lord Kelvin also estimated the Sun's age to be between 20 and 100 million years, which was later shown to be wrong. But his curiosity about the stars and their movement helped start early thoughts on dark matter. A couple of decades later, in 1906, the French mathematician and physicist Henri Poincaré introduced the term dark matter, or matière obscure, while talking about Lord Kelvin's work. Poincaré suggested that there might be hidden mass in the universe, but he also thought that this hidden matter would be less than the visible matter we can see. Although his ideas were far from correct, Poincaré's mention of dark matter brought the idea into the scientific conversation. In the 1920s, dark matter continued to interest astronomers. In 1922, Dutch astronomer Jacobus Kapteyn became one of the first to use the speeds of stars to suggest the existence of dark matter. He noticed that the way stars moved in space could be affected by unseen forces, hinting at the presence of invisible matter. Then, in 1930, Swedish astronomer Knut Lundmark further expanded on the idea, realizing that the universe must have much more mass than we could observe with our telescopes. This discovery was important because it showed that the visible universe might not be the complete picture. In 1932, another Dutch scientist, Jan Oort, joined the discussion by suggesting that dark matter might exist in the galactic neighbourhood. Oort studied the movements of stars near our galaxy and concluded that there must be more mass in our galaxy than was visible. However, he later realized that his measurements weren't completely accurate, and more research would be needed to understand the true nature of this unseen mass. Then, in 1933, Swiss astrophysicist Fritz Zwicky made a big breakthrough while studying galaxy clusters at the California Institute of Technology. Zwicky was studying the Coma cluster, a large group of galaxies, and noticed something strange. The galaxies in the cluster were moving much faster than expected based on the visible mass. This led him to suggest the presence of a huge amount of invisible mass, which he called Dunkel Materiae. Zwicky estimated that the Coma cluster had around 400 times more mass than could be seen through telescopes, based on how the galaxies were moving. He believed that this unseen mass was responsible for the gravitational force that kept the galaxies in the cluster together. Although Zwicky's estimates were wrong by a large amount, mainly due to outdated values, he was one of the first to correctly identify that the universe must contain unseen mass that pulls things with gravity. Zwicky, however, had a different view of dark matter than we have today. He believed that dark matter was simply ordinary matter that didn't give off light, rather than something completely different, like the mysterious dark matter we think of today. Still, his work was a major step toward discovering dark matter. As time passed, more proof of the existence of dark matter started to show up. One important piece of this proof came from studying how galaxies spin. In 1939, H.W. Babcock studied the spin of the Andromeda Galaxy. He found that the stars on the outer edges of the galaxy were moving much faster than expected. This suggested that there was much more mass in the galaxy than could be seen by just looking at its visible stars. At first, Babcock thought that the strange spinning could be due to light being absorbed inside the galaxy, or that the way the galaxy worked was different in its outer parts. But his observations were an early clue that something invisible was affecting the galaxy's spin. The next year, in 1940, Jan Oort made another important discovery. He studied a galaxy called NGC 3115 and found a large, invisible halo of mass surrounding it. This was another sign that galaxies might contain hidden matter beyond what we could see with our current technology. the idea of dark matter really began to catch on in the 1970s. Different scientific discoveries came together to suggest that galaxies might be surrounded by huge, invisible halos of matter. In 1974, two separate research groups, one from Princeton, New Jersey, led by Jeremiah Ostraker, Jim Peebles, and Amos Yahiel, and another from Tartu, Estonia, led by Jan Einasto, Ensar, and Ants Kasik, came to the same conclusion independently, making the idea stronger. One important observation that pointed to the existence of these invisible galactic halos was the way galaxies spin. Both optical and radio astronomy played a major role in these findings. Vera Rubin and Kent Ford, using a new spectrograph, made more accurate measurements of the speed of edge-on-spiral galaxies, revealing surprising results in the spinning curves. At the same time, radio astronomers used advanced radio telescopes to study the 21 centimeters line of atomic hydrogen in nearby galaxies. Unlike starlight, which can only be seen from the central parts of galaxies, hydrogen gas extends much farther out. This allowed astronomers to observe spinning patterns at much greater distances, giving them a better picture of the total mass in a galaxy. Early studies of the Andromeda Galaxy, using large telescopes like the 300-foot Green Bank telescope and the 250-foot Jodrell Bank dish, showed that the hydrogen spinning curve didn't behave as expected based on Kepler's laws, which describe how objects should move around a centre of gravity. As technology improved, more sensitive equipment allowed for even further measurements. In 1975, Roberts and Whitehurst pushed the limits, measuring the spinning speed of Andromeda all the way out to 30 kiloparsecs. Their findings showed that the galaxy's spinning curve stayed flat even at great distances. This was important because it suggested there was much more mass out there, beyond what we could see with regular telescopes. These findings, shown in their charts, combined optical data with the new hydrogen data, clearly showing the surprising flatness of the outer galaxy spinning curve. The solid curve in the graph represented the optical data from stars, while the other curve showed the total mass, which still kept increasing even in the galaxy's outermost regions. At the same time, scientists were developing even more advanced methods to study galaxies. Using interferometric arrays, multiple radio telescopes working together, researchers like Rogstad and Shostak in 1972 mapped the hydrogen spinning curves of 5 spiral galaxies. They found that all of these galaxies had flat spinning curves as well, suggesting that the mass in the outer parts of the galaxies was much higher than what could be explained by visible stars and light. By the late 1970s, it was widely accepted that dark matter halos likely existed around galaxies, and this became one of the biggest mysteries in astronomy. In the 1980s and 1990s, many observations started to suggest that dark matter was real. One important study, done by Persic, Salucci, and Stell in 1996, looked closely at 967 spiral galaxies and found strong proof of dark matter's existence. Other supporting evidence included strange behaviours like gravitational lensing, where galaxy groups bend light from objects behind them, the spread of hot gas in galaxies and groups, and the way tiny temperature differences, called anisotropies, appear in the cosmic microwave background, which is the afterglow of the Big Bang. Today, most scientists agree that dark matter is made up of particles that we haven't discovered yet, and these particles are unlike anything we know. The search to find this mysterious particle has become one of the biggest quests in particle physics, with many researchers using different methods and experiments to try and uncover the truth. In simple terms, when scientists talk about matter in the universe, they are referring to anything that adds to the overall energy, and its density changes in a particular way as the universe expands. Specifically, it decreases as the cube of the expansion, meaning the further the universe stretches, the thinner the matter becomes. This is different from radiation, which decreases even faster. Its energy gets weaker as the universe grows, following the inverse fourth power of the expansion. On the other hand, the cosmological constant behaves differently. It stays the same no matter how much the universe stretches, meaning its energy density remains constant. This difference in how matter, radiation, and the cosmological constant behave is due to a phenomenon called radiation redshift. To picture this, imagine the universe expanding. If the observable universe's size doubles, the scale factor of expansion also doubles. As a result, the energy of things like the cosmic microwave background radiation, the afterglow from the Big Bang, gets weaker because each photon, light particle, has to stretch out over a larger area, reducing its energy. The same happens to ultra-relativistic particles, such as early neutrinos. These lose energy in a similar way. However, the cosmological constant, being a property of space itself, doesn't change no matter how much the universe grows. As for dark matter, this term generally refers to parts of the universe that we cannot see, yet still have mass and obey similar laws to regular matter. However, in more specific terms, dark matter is often used to describe a particular kind of invisible matter that isn't made up of the usual particles we're familiar with, excluding something called missing baryons. Depending on the context, the meaning of dark matter can vary. The arms of spiral galaxies spin around their centre, and as you move outward from the centre, the visible mass density of the galaxy gets lower. If all the galaxy's mass were visible, it would behave like a simple system where most of the mass is concentrated at the centre and objects orbiting it, much like how planets orbit the Sun in our solar system. Based on Kepler's third law, we would expect the speeds of the objects to slow down the farther they are from the centre, just like how the planets in our solar system move slower the further they are from the Sun. But that's not what we see in galaxies. Instead, the rotation speeds of stars and gas in a galaxy remain constant, or even speed up the farther out they are from the centre. To explain this strange observation, it seems clear that the spread of mass in spiral galaxies is different from the solar system. Specifically, there may be a large amount of invisible non-luminous matter, what we call dark matter, on the edges of the galaxy. In bound systems like galaxies, the stars are also governed by a rule called the virial theorem, which helps explain how mass is spread out in a system based on the speeds of the stars. When astronomers look at how fast stars are moving in systems like elliptical galaxies or dense star clusters, they can use this theorem to figure out how mass is spread out. However, in many cases the measured speeds don't match what we'd expect based on the amount of visible mass in the system, even when we consider complex orbital patterns of the stars. Much like with the rotation curves of galaxies, the most logical explanation for this mismatch is that there's more invisible matter involved. Again, dark matter. Galaxy clusters are key to studying dark matter because we can measure their mass in 3 different ways. By looking at the range of speeds at which the galaxies in the cluster move, by studying the X-rays emitted by the hot gas inside the cluster. By analysing these X-rays, we can determine the temperature and density of the gas, which lets us calculate the pressure. Using the balance between gravity and pressure, we can figure out the total mass of the cluster through gravitational lensing, where the mass of the group bends light from farther objects. This lets us measure the group's mass without needing to directly observe the movement of the galaxies. All 3 of these methods point to the same conclusion. Dark matter makes up roughly 5 times the mass of all the visible matter in these groups. One interesting result of Einstein's theory of general relativity is a phenomenon called gravitational lensing. This happens when big objects, like galaxies or groups of galaxies, sit between a light source and the observer. These big objects act like a lens, bending the light that passes through them, making the light from the source appear distorted. The important thing to know is that gravitational lensing only requires the presence of mass. It doesn't matter what the mass is made of. The more massive an object is, the stronger the bending of light will be. For example, imagine a group of galaxies lying between a very faraway object like a quasar and us. In this case, the galaxies in the group will bend the light from the quasar, making it look different. When we talk about strong lensing, we're referring to the dramatic way the light from background galaxies can be bent into arc shapes as it passes through a big object's gravitational field. This has been observed around many faraway galaxy groups, including one known as Abell 1689. By studying the shape of these arcs, scientists can figure out the mass of the galaxy group causing the bending. In the weak lensing scenario, the bending is much less noticeable, and galaxies don't turn into arcs. Instead, we see tiny distortions in the shapes of galaxies. By looking at these slight changes, scientists can learn about how dark matter is spread out in the universe. The patterns of mass and light from these observations match what we expect from studies of dark matter. Now, while both dark matter and regular matter are forms of matter, they behave very differently. early in the universe, regular matter was charged and interacted strongly with light, which caused it to scatter. Dark matter, on the other hand, doesn't interact directly with light, but it still affects the universe in other ways. For example, it influences the cosmic microwave background, CMB, through its gravitational pull, especially on large scales. It also has an effect on the movement and density of regular matter. Because of these differences, regular matter and dark matter evolve in separate ways and leave distinct traces on the CMB. The CMB is very close to being a perfect blackbody, meaning it gives off a smooth, even temperature. However, there are tiny temperature differences, about 1 part in 100,000, that scientists can study. These small variations, called anisotropies, can be mapped out across the sky. When scientists break down this map into a graph called the angular power spectrum, they see a series of peaks that are evenly spaced but have different heights. The exact positions of these peaks depend on key factors in cosmology, and by comparing these positions to theoretical models, we can learn more about the universe's makeup. The first discovery of the CMB's anisotropies came in 1992 by the COBE satellite, but the resolution wasn't high enough to see the detailed peaks. In 2000, the Boomerang experiment, using a balloon to take measurements, found the first of these peaks. Later, the WMAP satellite and the Planck spacecraft measured these peaks much more precisely. Their findings supported the lambda-CDM model of cosmology. Structure formation is the process that began shortly after the Big Bang, when small irregularities in the universe's density caused matter to collapse and form stars, galaxies, and groups of galaxies. Before this period, the universe was uniform, with no significant differences in density, as described by the Friedmann solutions to general relativity. Over time, tiny fluctuations in density started to grow and clump together, turning the smooth, featureless universe into a more complex structure filled with stars and galaxies. In the early stages, radiation dominated the universe and had a major impact on matter. This radiation prevented regular matter's density fluctuations from growing and forming structure. If the universe only had regular matter, these fluctuations would not have had enough time to evolve into the galaxies and groups we see today. The key to solving this problem lies in dark matter, which is not affected by radiation. This allowed its density changes to grow first, creating gravity wells that later helped normal matter collapse into galaxies and other structures. The gravitational pull from dark matter acted like a magnet, pulling in normal matter and speeding up the formation of these large cosmic structures. A striking example of the impact of dark matter is the Bullet cluster, formed by the collision of two large galaxy clusters. What makes the Bullet cluster particularly interesting is the difference between where the mass of the cluster is located according to gravitational lensing, the bending of light around massive objects, and where the visible matter is found. This difference is hard to explain with alternative gravity theories, which expect gravitational lensing to happen only around visible matter. However, the standard theory of dark matter can easily explain this. The visible gas in the clusters, which interacts with light and other forms of radiation, was slowed down and cooled by electromagnetic forces during the collision. Dark matter, on the other hand, doesn't interact with light in the same way, so it passes through the collision unaffected, separating from the visible gas. This created two separate lensing peaks, as seen. In addition to dark matter, astronomers use Type Ia supernovae as standard candles to measure distances across the universe. These supernovae have a known brightness, so by measuring how dim they appear, scientists can calculate how far away they are. This method has shown that the universe is expanding faster and faster, a phenomenon usually explained by dark energy. Baryon acoustic oscillations, BAO, refer to regular changes in the density of normal matter, baryons, in the universe, which occurred on large scales in the early universe. These changes were caused by sound waves travelling through the hot, dense fluid of photons and baryons before the universe cooled enough for atoms to form. The effects of these sound waves can still be seen in the cosmic microwave background, CMB radiation. As the universe expanded, dark matter and normal matter began to clump together, but the effect of the original changes weakened over time. However, we can still observe a slight preference for galaxies to be separated by about 147 million light-years, which is a subtle but measurable signature of these early changes. This pattern was predicted in the 1990s and confirmed in 2005 through large galaxy surveys like the Sloan Digital Sky Survey and the 2DF Galaxy Redshift Survey. By combining CMB observations with BAO measurements, scientists can get a precise estimate of important cosmic values, such as the rate of expansion of the universe and the amount of matter it contains. These results support the lambda CDM model, which is the current leading theory of cosmology. Large surveys of galaxy redshifts can help us create a three-dimensional map of how galaxies are spread out in the universe. However, these maps are not perfect because the distances we estimate are based on the redshift we observe. The redshift we measure is affected by two things. The main factor is the universe's expansion, but there's also a smaller influence from the galaxy's own motion, known as its peculiar velocity. In general, superclusters, groups of many galaxies, are growing more slowly than the average expansion of the universe because their gravity is pulling things together. On the other hand, voids, vast empty spaces between galaxies, are expanding faster than the universe as a whole. This difference in expansion causes some interesting effects. For example, galaxies that are located in front of a supercluster are moving toward it faster than expected, so their redshift will be a little higher than we would normally calculate for their distance. Conversely, galaxies behind the supercluster appear to have a slightly lower redshift than expected. This difference causes superclusters to look flattened along the line of sight, while voids look stretched. However, this effect is hard to notice in a single structure, since we don't know its exact shape. Instead, scientists can observe this effect by averaging data from many structures. The phenomenon was first predicted by Nick Kaiser in 1987, and was later confirmed in 2001 by the 2DF Galaxy Redshift Survey, with results matching what we expect from the lambda CDM model of the universe. In a related field of study, the Lyman alpha forest refers to the collection of absorption lines found in the spectra of distant galaxies and quasars. These lines are caused by neutral hydrogen absorbing light at a specific wavelength, called the Lyman alpha transition. Observations of the Lyman alpha forest help astronomers test and refine cosmological models with results that align with findings from the WMAP data. Dark matter is often divided into three types: cold, warm, and hot. These names don't refer to temperature but instead describe how fast the particles were moving in the early universe. In simple terms, they show how far the particles travelled due to random movements before the universe started expanding and slowing them down. This distance is called the free streaming length, FSL. The type of dark matter depends on how this FSL compares to the size of a protogalaxy, an early cosmic object that would later become a small galaxy. If the FSL is much smaller than the size of a protogalaxy, it's called cold dark matter. If it's about the same size, it's warm dark matter, and if the FSL is much larger, it's hot dark matter. Some theories suggest a mix of these types, which were more popular in the middle of the 1990s but became less favoured after the discovery of dark energy. The key idea behind the free streaming length is that, after the Big Bang, the universe started with small changes in density, caused by tiny quantum changes at the smallest levels. As these particles moved from denser areas to less dense ones, the fast expansion of the universe limited how far they could go. Faster particles, like those in hot dark matter, could travel further before the universe expanded too much, while slower particles, such as those in cold dark matter, couldn't move as far. This means that the free streaming length sets a limit on the size of structures that could form in the early universe. Hot dark matter would lead to the formation of large structures, like superclusters, which would eventually break apart into galaxies. On the other hand, cold dark matter allows for smaller structures, like galaxies, to form first. Recent observations, especially deep field images of the universe, show that galaxies were the first to form, followed by clusters and superclusters as galaxies group together. This supports the idea that most dark matter is cold, not hot. This is also why neutrinos, which move almost at the speed of light and would be considered hot dark matter, cannot account for most dark matter. Dark matter refers to any type of matter that interacts with visible matter, like stars and planets, mainly through gravity. This means that dark matter might not be made of a completely new type of particle, but could, in theory, include regular matter like protons or neutrons. In fact, many objects familiar to astronomers, such as planets, brown dwarfs, red dwarfs, stars, white dwarfs, neutron stars and black holes, fall into this category. For example, when a black hole pulls in matter, it doesn't differentiate between regular matter, like protons, and other kinds of matter. Once it's inside the event horizon, all matter is treated the same. These hard-to-detect objects are grouped together as MACHOs, massive compact halo objects. Some scientists once thought that MACHOs made up the majority of dark matter, but this idea has since been largely rejected. There is strong evidence suggesting that most of dark matter is not made up of regular visible matter. First, if there were enough regular matter like gas or dust scattered around, we would be able to see it when it's lit up by the light from stars. However, we don't see this kind of matter in the quantities we would expect. Next, the Big Bang theory helps us understand how the elements we observe today were created. According to this theory, if there were more normal matter, called baryons, in the early universe, we would have seen a higher abundance of elements like helium, lithium, and other heavier elements. Based on what we observe, we know that only about 4 to 5% of the universe's total mass consists of this regular matter. However, large-scale studies of galaxies and other cosmic structures show that the total amount of matter is about 30% of what is needed to keep the universe stable. Further investigations have shown that only a small portion of dark matter seems to be in the form of regular hidden objects, like small planets or black holes, called MACHOs. Studies involving the bending of light by gravity, gravitational microlensing, suggest that these objects can't account for the majority of dark matter, as their masses fall within a range that excludes nearly all of the plausible candidates. Detailed studies of the cosmic microwave background, the faint radiation left over from the Big Bang, by missions like WMAP and Planck provide strong evidence that about 5/6 of the matter in the universe doesn't interact much with light or regular matter, except through gravity. This suggests that dark matter is largely invisible and can only be detected through its gravitational influence. If regular matter, called baryonic matter, doesn't account for most of dark matter, then dark matter must be made of something else, specifically non-baryonic matter. There are two main possibilities for non-baryonic dark matter: new, mysterious particles and ancient black holes from the early universe. Unlike regular matter, these non-regular particles don't help create the elements that formed during the Big Bang, a process known as Big Bang nucleosynthesis. Instead, we only notice them because of the gravitational effects they cause, such as how they bend light, called weak lensing. Some types of dark matter can even interact with each other, self-interacting dark matter, or with normal particles like WIMPs, weakly interacting massive particles. These interactions might produce detectable signs such as gamma rays and neutrinos, which scientists could possibly observe in direct detection. There are many different candidates for dark matter, each with its own strengths and weaknesses. WIMPs don't have a strict definition, but they are generally thought of as elementary particles that interact through gravity and possibly other weak forces, such as the weak nuclear force. Many theories suggest that WIMPs were created in the early universe in a similar way to regular particles. These particles would make up what's called cold dark matter. To explain how much dark matter we have today, the WIMP particles would need to be able to destroy each other in a specific way, which matches what would happen if they had masses around 100 billion electron volts and interacted through the electroweak force. This idea is often called the WIMP miracle, because it fits so well with predictions from supersymmetric theories, which extend the standard model of particle physics. A stable partner particle from supersymmetry has long been seen as a prime candidate for dark matter. Researchers are working hard to find WIMPs by looking for the products of their destruction, such as gamma rays, neutrinos, and cosmic rays coming from nearby galaxies. They also use experiments designed to directly detect WIMPs in laboratories by measuring their interactions with atomic nuclei, or by trying to create WIMPs in particle colliders like the Large Hadron Collider, LHC. However, in the early 2010s, experiments didn't find strong evidence for supersymmetry, and the LHC results cast doubt on the simplest WIMP ideas. Axions, another candidate for dark matter, are theoretical particles that were first proposed in 1978 by Frank Wilczek and Steven Weinberg. These particles were originally suggested to solve a problem in the theory of quantum chromodynamics, QCD, which explains how quarks and gluons interact. Axions are incredibly light and weakly interact with other particles, making them a perfect candidate for dark matter. They could be produced in the early universe and would remain present today, their abundance depending on their mass. Axions are thought to be so light that they could help explain some of the small-scale issues in the lambda CDM model, the leading cosmological model. The axion theory has gained traction in recent years, especially after WIMPs were not detected. The axion's extremely low mass means that quantum effects could potentially explain the small-scale mysteries of dark matter. Primordial black holes, another interesting idea, are thought to have formed in the very early universe, right after the Big Bang. During the period of rapid expansion known as inflation, incredibly dense regions of subatomic matter could have collapsed under their own gravity, creating black holes without the need for a star's death, as is the case with regular black holes. These black holes would predate the formation of the first stars and could have masses ranging from tiny, even as small as atoms, to incredibly large, far beyond typical stellar black holes. The concept of primordial black holes was first suggested in 1967 by Yakov Zeldovich and Igor Novikov, and later by Stephen Hawking in 1971. The idea quickly gained traction as a possible explanation for dark matter. One of the advantages of primordial black holes as dark matter candidates is that the theory behind black holes is already well established in physics, general relativity, and black holes themselves are already known to exist. However, creating primordial black holes might require complex conditions, such as exotic cosmic inflation or theories beyond the standard model of particle physics. In 2015, gravitational wave measurements from the detection of black hole mergers sparked renewed interest in primordial black holes as dark matter. Some black holes detected by these experiments had masses that seemed too large to be formed by the usual processes, like the collapse of a star. This suggested they could be primordial. However, a study that looked for signs of gravitational lensing from intermediate mass black holes, expected to be dark matter, found no evidence for them, although some researchers suggest this could be due to assumptions about the mass of these black holes. Further observations, like those made by the James Webb Space Telescope, may provide more clarity on this theory. Scientists once thought that incredibly small black holes, known as primordial black holes, might make up a significant portion of dark matter. However, the Voyager 1 spacecraft, which explored beyond the Sun's influence, measured the flow of positrons and electrons and found something surprising. The amount of particles detected was too low, and their energy levels were not what scientists expected. This led researchers to conclude that these tiny black holes are too rare to account for dark matter. Despite this, the idea of dense forms of dark matter continues to be researched, with new theories even suggesting ways to cool dark matter. As of 2018, the mystery remains unsolved. In 2019, further observations of the Andromeda Galaxy showed no signs of microlensing effects, which would be expected if tiny black holes were present, adding more doubt to their existence. However, there's still a gap in our understanding. There is a range of mass smaller than what we can currently detect with optical microlensing, where primordial black holes could potentially make up all of the dark matter. This area remains open for exploration and continues to challenge our understanding of the universe. If dark matter is made of particles that barely interact with anything, an important question arises: could these particles form objects like planets, stars, or black holes? Historically, the answer has been no, and there are two key reasons for this. It can't easily lose energy. Regular matter forms dense objects like stars and planets because it can lose energy in many ways. For example, when particles fall inward due to gravity, they can lose energy, which allows them to slow down and condense into more stable objects. Dark matter, however, doesn't seem to have the ability to lose energy because it doesn't interact with other matter strongly, except through gravity. Without ways to release energy, dark matter particles that start to get pulled inward would just heat up, speed up, and eventually escape, preventing the formation of compact objects. It doesn't interact in diverse ways. Regular matter interacts through multiple forces such as gravity, electromagnetism, and the strong nuclear force, allowing it to form complex structures like atoms, stars, and galaxies. For instance, inside stars, particles interact through nuclear fusion, emitting light and neutrinos. In dark matter, we don't see evidence for such interactions beyond gravity, and possibly some weak interactions, but this is still speculation. Without these varied interactions, dark matter doesn't have the ability to form the kinds of structures that regular matter does. If dark matter is composed of subatomic particles, these particles pass through every square centimetre of Earth millions or even billions of times every second. Many experiments are trying to test this idea. While WIMPs, weakly interacting massive particles, have been the most commonly searched for candidates, axions are also getting attention, especially with projects like the Axion Dark Matter Experiment, ADMX. Other possibilities include heavy particles from a hidden sector that only interact with regular matter through gravity. There are two main types of experiments investigating dark matter. Direct detection experiments. These look for signs that dark matter particles are scattering off atomic nuclei in a detector. The goal is to measure tiny energy shifts, a few thousand electron volts, caused by these interactions. When dark matter hits an atom, the atom might release energy in the form of light or vibrations, which can be detected. To do this well, these experiments need to be as isolated as possible from background interference, which is why they are often conducted deep underground, where cosmic rays don't interfere. Notable underground labs include Storwell Mine, Sudan Mine, and the Gran Sasso National Laboratory. These experiments often use two technologies: cryogenic detectors that measure heat from particle collisions in materials like germanium, noble liquid detectors that detect light produced when a particle hits liquids like xenon or argon. Some well-known experiments in these areas include CDMS, CREIST, Xenon, and LX. These detectors are especially good at telling dark matter apart from background particles, which mostly scatter off electrons, while dark matter particles scatter off atomic nuclei. Indirect detection experiments. These search for the effects of dark matter particles destroying each other or breaking down. There's currently no confirmed detection of dark matter in direct detection experiments, but these efforts have helped narrow down the possible properties of dark matter particles. One interesting claim comes from the Dharma Nai and Dharma Libra collaborations, which have noticed a yearly change in their data, possibly due to the Earth's movement through the dark matter cloud. However, other experiments such as LX and super CDMs have not seen the same effect, creating a bit of a mystery. There are also special experiments with directional sensitivity, which track the motion of dark matter particles based on the solar system's movement around the galactic center. This method tries to separate dark matter signals from background noise, which should be evenly spread out. These experiments, such as DMTPC and DRIFT, try to detect the direction in which dark matter is moving to help find possible signals. Indirect detection experiments aim to find signs of dark matter by looking for the results when dark matter particles self-destruct or break down in space. In certain areas with high amounts of dark matter, like the center of the Milky Way, two dark matter particles might collide and destroy each other, releasing gamma rays or pairs of normal particles and their opposites, antiparticles. Alternatively, if a dark matter particle is unstable, it might break down into normal particles or others, which could be detected indirectly through an unexpected burst of gamma rays, antiprotons or positrons, coming from areas with a lot of dark matter, like the Milky Way's center or distant galaxies. One of the challenges of this kind of search is that other space events could produce similar signals, so multiple signals from different sources are needed to confirm a dark matter discovery. Dark matter particles that pass through the Sun or Earth might interact with atoms and lose energy in the process. This could cause dark matter to build up at the centers of these celestial bodies, increasing the chances for collisions or destruction. These events could send out a special signal of high-energy neutrinos, which could serve as strong evidence of dark matter made of WIMPs, weakly interacting massive particles. Instruments like Amanda, IceCube, and Antares are actively searching for this signal. In addition, the detection of gravitational waves by LIGO in 2015 opened the door for observing dark matter in new ways, especially if it exists as early black holes. Several experiments have tried to detect dark matter emissions, such as those from destruction or breakdown. For example, The energetic gamma-ray experiment telescope spotted more gamma rays in 2008 than expected from the Milky Way, but scientists believe this was due to errors in estimating the telescope's sensitivity. The Fermi Gamma Ray Space Telescope is continuing this search and, in 2009, it observed a puzzling extra amount of gamma rays from the centre of the Milky Way. This could be a sign of dark matter destruction or an unknown group of pulsars. In 2012, a deeper analysis of Fermi data suggested a 130 giga-electronvolts signal from the Milky Way centre, which was interpreted as a possible result of WIMP destruction. At even higher energies, ground-based telescopes have set limits on dark matter destruction in dwarf galaxies and galaxy groups. The Pamela experiment, launched in 2006, detected an unusual amount of positrons, which might come from dark matter or pulsars, though no similar excess of antiprotons was found. Similarly, the Alpha Magnetic Spectrometer aboard the International Space Station observed high-energy cosmic rays in 2013, possibly linked to dark matter destruction. Another approach to finding dark matter involves trying to create it in a laboratory. Experiments like those at the Large Hadron Collider, LHC, may detect dark matter particles formed during proton collisions. Since dark matter doesn't interact much with regular matter, it might be spotted indirectly by noticing large amounts of missing energy and momentum that escape detection, while other particles from the collision are measured. The LEP experiment, using a similar method but probing the interaction between dark matter and electrons, also provides limits on dark matter. Any discovery of dark matter in such experiments must be verified by findings from indirect or direct detection methods to confirm that the new particle is truly dark matter. Since dark matter has yet to be identified, many alternative theories have emerged to explain the same cosmic events. General relativity, the theory that supports much of the evidence for dark matter, is well tested on the scale of the solar system, but hasn't been fully proven on galactic or cosmic scales. Some scientists suggest that changing general relativity could eliminate the need for dark matter. Well-known alternatives include MOND, modified Newtonian dynamics, TVES, a version of MOND, FR gravity, negative mass, dark fluid, and entropic gravity, among others. A key challenge for these alternative theories is that the evidence for dark matter comes from many independent sources. While it might be possible to explain a single observation, explaining all the evidence without dark matter is very difficult. Still, some alternatives have had limited success, like the 2016 test of gravitational lensing and entropic gravity, and a 2020 measurement supporting MOND. Despite these successes, most astrophysicists believe that while changes to general relativity could explain some of the observations, the overall data suggests that dark matter must exist in some form. When we gaze deep into the night sky, we're not just seeing space, we're actually looking back in time. The light coming from faraway galaxies has travelled for millions, and in many cases, even billions of years before finally reaching Earth. Because the universe is constantly growing and stretching in all directions, the farther away a galaxy is, the older the light we are seeing from it. It's like watching a cosmic time machine in action. But there's a limit to how far we can see. This limit is known as the cosmological horizon. Think of it as a giant invisible bubble that surrounds us. It marks the edge of what is observable from Earth. Beyond this boundary, the light from extremely distant galaxies hasn't had enough time since the beginning of the universe to reach us. So we can't see what lies past that point, no matter how powerful our telescopes become. Now, here's where things get really interesting. Although nothing can move faster than the speed of light through space, space itself is not bound by that rule. It can stretch and expand at any speed. This means that distant galaxies can be carried away by the expanding fabric of space faster than their light can travel toward us. As a result, the light they emit gets stretched so much that it becomes invisible to our eyes. It gets red-shifted beyond detection. Eventually, this light disappears entirely from view. So the cosmological horizon doesn't mean that the universe ends at that point. Not at all. It just means that we can't see any farther than that limit. Not yet, and maybe never. There could be countless galaxies, stars, cosmic clouds, and even mysterious structures far beyond that horizon. but they remain hidden from us simply because their light hasn't had enough time to get here. This whole region that we can see is called the observable universe, but it's just a small piece of the total universe, like one island in an endless ocean. We don't know how big the universe truly is, or what's out there beyond what we can observe. Some scientists even believe that the universe could be infinite. Right now, scientists believe that the universe is about 13.8 billion years old. Because light has a limited speed, we can only observe things whose light has travelled no more than 13.8 billion years to reach us. But here comes a surprise. The actual distance to those farthest galaxies is much bigger than 13.8 billion light years. Why? Because as that light travelled toward us, the space in between kept expanding. This means those galaxies are now about 46 billion light years away from us. That might seem confusing at first, but it makes sense when we remember that space itself is stretching as time goes on. It's like walking on an escalator that's moving in the opposite direction. You move, but the ground beneath you moves too. Another twist in this story is that the universe isn't just expanding, it's accelerating. That means space is growing faster and faster over time. Because of this, some galaxies that we can see right now may one day slip out of sight forever. Their light will be stretched so much by the expanding universe that it will fade away, red-shifted beyond what we can detect. So, even though the size of the observable universe increases as more light reaches us, the number of galaxies we can actually observe might decrease in the distant future. Some galaxies are just moving away too fast due to the stretching of space. Everything we know about the universe, every star, every galaxy, every cosmic event, comes from the light that has already reached us. But there is so much more beyond the horizon, beyond our current reach. It's a silent, mysterious part of the cosmos that we may never see, no matter how long we wait. However, this horizon is not the end of the universe. It's simply the boundary of what we can currently observe. Beyond that horizon, the universe probably continues on, maybe forever. But we can never see it directly. No matter how much time passes, the light from those faraway regions will never reach us. They are cut off by the ever-expanding fabric of space. This idea that there is something beyond what we can ever see has fascinated scientists for many decades. People have wondered and speculated about what might lie in those unreachable regions of the cosmos. Some think the universe beyond the horizon might look just like what we see here. This idea is based on the cosmological principle, which says that, on very large scales, the universe is homogeneous and isotropic. In simpler terms, it looks the same in all directions and at every location. If this principle is correct, then if we could somehow peek beyond the observable universe, we would probably find more of the same. More galaxies, more stars, more nebulae, and more cosmic structures that look very much like the ones near us. In that case, the part of the universe we can observe would be just a small patch in a much larger, perhaps infinite, cosmic landscape. But not everyone agrees. Some scientists suggest that beyond the horizon, the universe might not be the same at all. While the observable universe appears fairly smooth and evenly spread out when viewed on a grand scale, there might be differences in other regions we cannot see. Some areas could be packed with galaxies and dark matter, while others might be almost completely empty. These invisible variations, though hidden from us, could hold important clues about how the universe formed and how it works. Even though we can't see these faraway regions, their mere possibility stretches our imagination. What if the laws of physics change out there? What if the fundamental forces behave differently? One bold and fascinating idea comes from inflationary theory, which describes a period of extremely rapid expansion just after the Big Bang. According to this theory, during those first tiny fractions of a second, space didn't just expand, it exploded outward faster than the speed of light. Some versions of this theory suggest that this inflation could have happened in different places at different times, creating bubble universes, each its own separate cosmos. These bubbles could have different physical laws, different types of matter, or even different numbers of dimensions. Our observable universe would just be one such bubble in a vast multiverse, a collection of countless universes, each possibly as big and complex as our own. If this theory is true, then beyond our horizon might lie not just more of our universe, but entirely different universes sealed off from us forever. They might be strange and alien in ways we can hardly imagine, places where gravity works differently, or where time flows in a different way. Even if the universe beyond the horizon is similar to ours, the expansion of space still affects it. The universe is growing larger all the time, with galaxies moving farther apart because space itself is stretching. The galaxies that are already beyond the cosmological horizon are moving away from us faster than the speed of a light due to this expansion, not because they are speeding through space, but because the space between us and them is growing. Over time, even more regions of the universe will drift beyond our reach. This is because of a mysterious force called dark energy, which is causing the expansion of the universe to speed up. If this acceleration continues, then in the distant future, more and more galaxies will move beyond the horizon and disappear from view forever. Eventually, the universe could become a lonely and fragmented place, where clusters of galaxies are so far apart that they can no longer interact or even see each other. Each region would be cut off, isolated in its own pocket of space, with no way to send or receive information from the others. Is the universe infinite? All of this leads to an even deeper question. Is space infinite, or is it expanding into something else? It's hard to even picture. We're used to thinking of things having edges, like a balloon or a table, but space might be different. If the universe is infinite, then it has no edge at all. It stretches out forever in every direction. In that case, even though space is already endless, the distances between galaxies in that infinite space are still increasing because of expansion. But there's another possibility. Some scientists think the universe could be finite but unbounded. That means it has a certain size but no edge you can fall off. Think of the surface of a balloon. It's finite. You can measure its size. But if you keep walking along it, you'll never hit an edge. You'll just go around in a loop. The universe might be like that, just in 3 dimensions instead of 2. So, is the universe expanding into something bigger? Like a box getting larger inside a room? Not quite. In everyday life, things expand into something. But in cosmology, space itself is expanding, and it's not expanding into anything. Space and time are part of the universe itself. There's no outside that we know of. However, if the multiverse idea is correct, our universe might be just one part of a much larger superstructure, an endless sea of universes. Still, the expansion we observe doesn't require us to believe that our universe is growing into this larger multiverse. The stretching of space can happen within the universe itself, without needing an outside to grow into. Now let's zoom in, not out, to the tiniest possible scales. According to quantum theory, the fabric of space is not smooth and empty. Instead, it's a restless, buzzing foam full of energy. Scientists call it quantum foam. At these unbelievably tiny scales, far smaller than atoms, space is constantly fluctuating. Tiny particles flicker into and out of existence in mere fractions of a second. It's like a sea of invisible activity, hidden beneath everything we see. To us, space feels solid and still, but on this scale, it's more like a storm. So what if the universe is infinite at large scales, but made up of tiny grains of energy and motion at small scales? That would mean space is both endless and full of tiny, unpredictable behavior. Some scientists are exploring the idea that these two extremes, quantum mechanics at the smallest level and cosmic expansion at the largest, might somehow be connected. Could the way space expands be influenced by the jittery nature of quantum foam? Could the tiniest building blocks of space shape the fate of the entire universe? That's still an open question. But it's one of the biggest mysteries in science. How to connect the world of the very small with the cosmos of the very large. And as long as humans are around to ask questions, the mystery of what lies beyond the horizon will continue to inspire wonder. The shape of the universe plays a huge role in how everything works on the grandest scale imaginable. At the heart of this is a concept called curvature, which describes how space itself might be bent or curved. Scientists have spent many decades trying to figure out what the overall shape of the universe is. Is it flat, like a giant sheet? Is it closed, like the surface of a sphere? Or is it open, like a saddle that curves outward? These are the 3 main possibilities for the geometry of the entire cosmos. Even though it's hard for us to imagine curved space, after all, we live in a world where space looks flat, this idea is actually very important when it comes to understanding how the universe expands and changes over time. The concept of curved space comes from Albert Einstein's famous theory of general relativity, which he published more than 100 years ago. According to this theory, massive objects like stars, planets, and galaxies bend the space around them, and that bending is what we experience as gravity. On smaller scales, like inside our own solar system, this warping of space is tiny. But when you zoom out to the scale of the entire universe, the overall curvature could be much more significant, and it could shape the future of everything. So, what do these three possible shapes, flat, closed, and open, actually mean? In a flat universe, space stretches out endlessly in every direction without curving in or out. Imagine drawing a triangle on a perfectly flat sheet of paper. The angles of that triangle will always add up to exactly 180 degrees. In a flat universe, the same rule applies, even on the largest possible scales. This kind of universe would have just the right amount of mass and energy, not too much and not too little. That perfect balance would mean the universe expands steadily, without collapsing back in on itself or racing away uncontrollably. In a closed universe, space curves inward like the surface of a sphere. If you could travel in one direction far enough, you would eventually end up back where you started, just like flying around the Earth. A closed universe would have more than enough mass and energy. Its strong gravity would slow the expansion over time, eventually stopping it altogether. After that, gravity would pull everything back inward, shrinking the universe down until it ends in a powerful event called the Big Crunch, where all matter and energy collapse back together. In an open universe, space curves outward like a saddle or a potato chip. This type of universe wouldn't have enough mass and energy to ever stop expanding. Instead, it would keep stretching forever, getting bigger and bigger. In this scenario, galaxies would continue to drift farther apart, and the universe would never come back together. Interestingly, if you drew a triangle in an open universe, the angles would add up to less than 180 degrees, and parallel lines would slowly drift away from each other. Each of these shapes leads to a very different future for the universe. In a flat universe, expansion would slow down over time but never quite stop. In a closed universe, expansion would stop and then reverse, ending in a collapse. In an open universe, expansion would go on forever but gradually slow down. One of the biggest goals in modern cosmology, the study of the universe's origins and structure, has been to figure out which of these shapes our universe actually has. To do this, scientists have studied something called the cosmic microwave background, or CMB, which is the faint glow left over from the Big Bang nearly 14 billion years ago. By measuring tiny variations in the CMB, they've been able to estimate the curvature of space on the largest possible scales. So far, all the measurements suggest something amazing. The universe is incredibly flat. That doesn't mean it's perfectly flat, just that if there is any curve at all, it's so small we can't detect it with today's technology. Still, this discovery is very important. A nearly flat universe means the total amount of matter and energy in the cosmos is very close to a special critical value. If that amount were even slightly higher or lower, the universe would have turned out closed or open instead. This raises a big question. How did the universe end up being so perfectly balanced? One possible answer comes from the theory of cosmic inflation. According to this idea, right after the Big Bang, the universe went through a brief but unbelievably fast expansion, much faster than the speed of light. This happened within a tiny fraction of a second. During that time, any original curves in space would have been stretched flat, just like how inflating a wrinkled balloon smooths it out. Thanks to inflation, the universe may look flat today even if it didn't start out that way. But even though the universe seems flat, that doesn't mean it will expand at a steady pace forever. In the late 1990s, astronomers made a shocking discovery. The expansion of the universe is speeding up, not slowing down. Something mysterious called dark energy is causing space itself to stretch faster and faster. This means that even in a flat universe, the future might not be calm and steady. Instead, Galaxies could race away from each other faster and faster, disappearing from view over billions of years. The discovery of dark energy completely changed how scientists think about the fate of the universe. It showed that the shape or curvature of space isn't the only thing that matters. The energy driving the expansion also plays a huge role. So, even though current evidence says we live in a flat universe, there's still much we don't know. It's possible that the universe is slightly curved, just not enough for us to detect yet. If that's the case, the difference might only show up across distances far larger than we can currently observe. Also, on smaller scales, like around stars, galaxies, and black holes, the warping of space by gravity is very real. Massive objects bend the space around them, bending light and affecting how other things move. But this local curvature doesn't change the overall shape or expansion of the entire universe. As the universe continues to expand, something truly astonishing is happening. Galaxies that are far away from us are moving even farther at faster and faster speeds. This isn't because they're flying through space like rockets. Instead, space itself, the very fabric of the universe, is stretching, and it's carrying those galaxies along for the ride. This stretching of space is not slowing down. In fact, it's speeding up. Scientists call this the accelerating expansion of the universe, and it means that over time, galaxies are receding, or moving away, more and more quickly. The farther a galaxy is from us, the faster it appears to be fleeing into the distance. One day, some of these galaxies will be moving away so quickly that they will be travelling faster than the speed of light. Now, this might sound impossible, because we often hear that nothing can move faster than light. But here's the trick. The galaxies themselves are not breaking any cosmic speed limits. It's the space between us and them that is growing. This is perfectly allowed by the laws of physics. You can imagine it like raisins in a rising loaf of bread. The raisins aren't moving on their own, but the dough, space, is stretching and increasing the distance between them. This distinction is important because it helps us understand the future of our universe, and it's both fascinating and a little bit lonely. As space keeps expanding, those distant galaxies will drift farther and farther from us. Eventually, they will be moving away so quickly that even the light they emit won't be able to reach Earth. That means they'll disappear from our view, not because they stop existing, but because their light can no longer keep up with the expanding space. They will cross what scientists call the cosmic horizon, the ultimate boundary of what we can ever hope to see. This process is already underway. Even now, there are galaxies so far away that the light from them is only just now arriving at Earth, after travelling for billions of years. As time passes, those galaxies will get even farther, and the light they send will be stretched out more and more by the expansion of space. This stretching of the light is known as redshift, and it shifts the light to longer wavelengths, moving it toward the red end of the spectrum. The faster a galaxy recedes, the more redshifted its light becomes. Eventually, the light from these galaxies will become so stretched that it will no longer be visible, not even with the most advanced and sensitive telescopes. It will be stretched beyond the visible spectrum, into microwave or even radio waves, and then beyond that too until it's completely undetectable. Fast forward billions of years into the future, and most of the galaxies in the universe will have passed beyond our cosmic horizon. We won't be able to see them anymore. The only galaxies that will still be visible to us will be the ones that are gravitationally connected to our own, like members of a tightly knit family. These galaxies belong to what we call the local group, a small cluster of galaxies that includes the Milky Way, the Andromeda Galaxy, and a few smaller ones nearby. Because of the pull of gravity between them, these galaxies won't drift apart like the others. Instead, over time, they will move closer together and eventually merge into one enormous galaxy. But beyond our little corner of the universe, everything else, all the other galaxies, stars, and cosmic wonders, will quietly fade from view, slipping into the darkness. This paints a picture of a future that is more and more isolated. As each distant galaxy disappears from view, it takes with it all the information it carried, its light, its history, its role in the grand cosmic story. Future astronomers, living trillions of years from now, may look into the sky and see only the merged galaxy that used to be the Milky Way and its neighbours. They might never know that a vast universe once existed beyond it, filled with countless galaxies. In the early days of the universe, galaxies often collided and merged, sparking bursts of star formation and dramatic changes. But as time marches on and galaxies move farther apart, these cosmic encounters will become rare. The universe will settle into a much quieter and more solitary existence. And in the far, far future, long after the last distant galaxy has slipped beyond the cosmic horizon, the universe will be an entirely different place. The stars in our galaxy will continue to shine for billions of years, but eventually even they will burn out. No new stars will be born. The universe will grow colder and darker. This final stage is known as the heat death of the universe, a time when everything becomes still, with no energy left to fuel stars or galaxies, and no way for life or light to continue. So far, the expansion of the universe does not change the laws of physics, but it stretches the way they play out on large cosmic scales. The fundamental laws, like gravity, thermodynamics, and quantum mechanics, still hold. But the conditions under which they operate are changing. Some scientists do wonder whether, in the extreme far future or in other parts of a possible multiverse, the laws of physics might be slightly different. It's a mystery we haven't solved yet. For now, though, the universe is expanding according to the rules we know, even if those rules lead us to a lonely, silent cosmos. As the universe keeps expanding, and not just expanding, but speeding up in that expansion, some scientists are beginning to wonder, could this ever-growing stretch of space actually change the very laws of physics themselves? This is a bold and fascinating question. It challenges the long-standing belief that the most basic building blocks of nature, the so-called constants of physics, never change. These constants include things like the speed of light, the strength of gravity, and the fine structure constant, which affects how light interacts with matter. In most scientific theories, these values are assumed to be fixed, never changing, and permanent. They are like the solid foundation upon which all the rules of the universe are built. But what if that foundation isn't as unshakable as we once thought? To understand this idea more deeply, we need to look at what these constants actually do. The speed of light, for example, is not just about how fast light moves, it also limits how quickly any kind of information or signal can travel from one place to another. It sets the ultimate speed limit for the universe. Then there's gravity, controlled by something called the gravitational constant. This determines how strongly objects with mass pull on each other, whether it's the Earth holding the Moon in orbit or the Sun pulling the planets around it. Without this constant, there would be no galaxies, no stars, and no planets. Another key player is the fine structure constant. This one governs how light and charge particles, like electrons and protons, interact. It plays a huge role in chemistry, in the way atoms hold together, and in how matter forms and behaves. Even a tiny change in this constant could make the universe look completely different. It could mean no atoms, no stars, and maybe no life. Now here's where things get even more interesting. As the universe expands, especially under the mysterious force called dark energy, space itself is being stretched like a growing balloon. This cosmic stretching increases the distances between galaxies and affects the shape of the universe on a grand scale. But could this expansion also change the laws that control everything within it? Some scientists think it's possible. They suggest that maybe the constants we measure today were not always the same. Perhaps billions of years ago, the strength of gravity or the electromagnetic force was slightly different. If that were true, it would mean the early universe might have had very different conditions, changing how stars and galaxies first formed. Before stars, before space, before time itself, there was nothing. Or maybe something. Then suddenly everything began. In a tiny fraction of a second, the universe exploded into being. It was hot, dense, and full of energy. This is what we call the Big Bang. But if the Big Bang created the universe, what caused the Big Bang? Scientists have searched for answers for decades. They've found ancient light still travelling through space. They've seen galaxies moving apart and time stretching like rubber. In 1964, they discovered a strange glow coming from every direction, a leftover signal from the beginning. But even now, the moment before the Big Bang remains a mystery. Could there have been something before everything? And if so, what? The story of the universe, as understood by modern science, begins not with an explosion in space, but with the expansion of space itself from an incredibly hot, dense state. This foundational idea is known as the Big Bang theory. It describes how our universe evolved from its earliest moments to the vast, complex cosmos we observe today. The theory does not attempt to explain what existed before this moment, nor what caused it, but rather provides a comprehensive framework for the universe's development after its initial state. It is a scientific model built upon a bedrock of observational evidence and theoretical predictions, which has been refined over many decades. The conceptual seeds of the Big Bang theory were sown in the early 20th century, a time of profound shifts in scientific thought. Albert Einstein's theory of general relativity, published in 1915, revolutionized our understanding of gravity, space, and time. It proposed that gravity is not a force acting at a distance, but rather a curvature of space-time caused by mass and energy. When scientists began to apply Einstein's equations to the entire universe, they found that a static, unchanging universe, as was commonly believed at the time, was unstable. Einstein himself initially added a cosmological constant to his equations to force a static solution, a decision he would later call his biggest blunder. Independent of Einstein's initial preference for a static universe, several scientists began to explore the implications of a dynamic cosmos. In 1922, Russian physicist Alexander Friedmann developed solutions to Einstein's equations that described an expanding universe. His work, however, was not widely known in the West at the time. The crucial observational evidence began to emerge from the realm of astronomy. Vesto Slipher, an American astronomer, had been observing the spectra of spiral nebulae, which we now know are galaxies, since 1912. He found that most of these nebulae were moving away from Earth at very high speeds, indicated by a shift in their light towards the red end of the spectrum, a phenomenon known as redshift. It was a Belgian priest and physicist, Georges Lemaître, who, in 1927, independently derived the expanding universe solutions from general relativity and, crucially, connected them to Slipher's observations. Lemaître proposed that the universe began from a single, extremely dense point, which he called the primeval atom. He suggested that this atom then expanded and diversified, eventually forming the universe we see. His work, initially published in an obscure Belgian journal, gained wider recognition when translated into English in 1931. The most compelling observational evidence came from the American astronomer Edwin Hubble. Working at the Mount Wilson Observatory in California, Hubble, along with his assistant Milton Humason, made groundbreaking measurements of the distances to these spiral nebulae. By 1929, Hubble announced his discovery. The further away a galaxy was, the faster it appeared to be moving away from us. This relationship, now known as Hubble's law, provided powerful empirical support for the idea of an expanding universe. If everything is moving away from everything else, it implies that, in the past, everything must have been much closer together. This was a pivotal moment, shifting the scientific consensus from a static to a dynamic universe. The term Big Bang itself was coined in 1949 by British astronomer Fred Hoyle during a BBC radio broadcast. Hoyle was a proponent of the rival steady-state theory, which proposed that the universe was eternal and unchanging, with new matter continuously being created to fill the gaps left by expansion. Hoyle used Big Bang somewhat derisively to describe Lemaître's theory, intending to ridicule its seemingly abrupt beginning. Ironically, the catchy name stuck and became the widely accepted term for the theory it was meant to discredit. While the observational evidence for expansion mounted, theoretical work continued to strengthen the Big Bang model. In the 1940s, George Gamow, along with his students Ralph Alpher and Robert Herman, made key predictions based on the hot, dense early universe. They reasoned that if the universe started from such extreme conditions, it would have been hot enough for nuclear fusion to occur in its earliest moments, leading to the formation of light elements like hydrogen and helium in specific proportions. Furthermore, they predicted that the residual heat from this early hot phase should still be detectable today, as a faint glow of microwave radiation permeating the entire universe. This prediction, made in 1948, would become one of the most significant pieces of evidence for the Big Bang. The accidental discovery of this cosmic background radiation in 1964 by Arno Penzias and Robert Wilson at Bell Labs provided the smoking gun. They were working with a new horn antenna and kept detecting a persistent uniform static or noise that they could not eliminate. It came from every direction in the sky, regardless of the time of day or year. Simultaneously, researchers at Princeton University, led by Robert Dick, were independently searching for this very radiation, unaware of Penzias and Wilson's discovery. When the two groups connected, it became clear that Penzias and Wilson had stumbled upon the cosmic microwave background, CMB, the faint afterglow predicted by Gamow and his colleagues. This discovery effectively sealed the fate of the steady-state theory and cemented the Big Bang as the leading cosmological model. The Big Bang theory, therefore, is not a description of an explosion that happened at a specific point in space, with matter flying outwards into an empty void. Instead, it describes the expansion of space itself, carrying galaxies and all matter along with it. Imagine a balloon being inflated. Dots drawn on the surface move further apart as the balloon expands, but no single dot is at the centre of the expansion, and the dots are not moving through the balloon's surface, but rather the surface itself is growing. Similarly, in the universe, every point appears to be the centre of the expansion, and galaxies are not rushing through pre-existing space, but the fabric of space-time between them is stretching. This stretching causes the light from distant galaxies to be redshifted, providing the primary observational evidence for this ongoing cosmic expansion. Over the decades, further observations and theoretical advancements have continued to refine and support the Big Bang model. The observed abundances of light elements in the universe, such as hydrogen, helium, and lithium, precisely match the predictions made by the Big Bang nucleosynthesis theory, which describes element formation in the first few minutes after the Big Bang. The large-scale structure of the universe, with its vast cosmic web of galaxies and voids, also aligns with predictions from the Big Bang model, especially when combined with the concept of dark matter and dark energy. While the Big Bang theory provides an incredibly successful framework for understanding the universe's evolution from a tiny fraction of a second after its beginning, the question of what initiated this expansion, or what existed before, remains a profound area of ongoing scientific inquiry and speculation. One of the most profound and counterintuitive aspects of observing the universe is that when we look out into space, we are simultaneously looking back in time. This seemingly magical ability is not due to any special properties of our telescopes, but rather a fundamental consequence of the finite speed of light. Light, the fastest thing we know, travels at a specific, measurable speed through the vacuum of space. This speed is approximately 300,000 kilometers per second, or about 186,000 miles per second. While this speed seems incredibly fast in our everyday experience, the distances in the cosmos are so immense that light takes a considerable amount of time to travel from its source to our eyes or our instruments. Consider the most familiar example, the Sun. The light we see from the Sun left its surface approximately 8 minutes and 20 seconds ago. This means that if the Sun were to suddenly vanish, we would not know about it for over 8 minutes. We're always seeing the Sun as it was in the recent past, not as it is in the present moment. This principle extends to every object we observe in the universe. The further away an object is, the longer its light has been travelling to reach us, and consequently, the further back in time we are seeing it. To manage the immense distances involved in astronomy, scientists use a unit called the light year. A light year is not a measure of time, but a measure of distance. It is the distance that light travels in 1 Earth year. This distance is approximately 9.46 trillion kilometers, or about 5.88 trillion miles. Using this unit, we can grasp the scale of the cosmos. For instance, the nearest star to our solar system, Proxima Centauri, is about 4.2 light-years away. This means that the light we receive from Proxima Centauri left that star 4.2 years ago. We are seeing it as it was 4.2 years in the past. Now, extend this concept to galaxies. The Andromeda Galaxy, our closest large galactic neighbour, is about 2.5 million light-years away. When we gaze at the Andromeda Galaxy through a telescope, we are seeing light that began its journey 2.5 million years ago. This light originated when early humans were just beginning to evolve on Earth. The implications are staggering. Every image of a distant galaxy is a snapshot from the past. This principle is the cornerstone of observational cosmology, allowing astronomers to piece together the history and evolution of the universe. Telescopes, in essence, become time machines. By observing objects at progressively greater distances, we're effectively looking at different epochs in cosmic history. The most powerful telescopes, like the Hubble Space Telescope and more recently the James Webb Space Telescope, are designed to peer deep into the universe, capturing light from objects billions of light-years away. For example, when astronomers observe galaxies that are 10 billion light-years away, they are seeing those galaxies as they appeared 10 billion years ago, when the universe was only a few billion years old. At these immense distances, we're observing the universe in its infancy. We can see the earliest, most primitive galaxies, which look very different from the mature, well-formed spiral and elliptical galaxies we see closer to us. These early galaxies are often smaller, more irregular, and undergoing rapid bursts of star formation. By comparing these ancient galaxies with closer, younger ones, scientists can trace the evolutionary pathways of galaxies over cosmic time. The furthest back in time we can see with a light is to the cosmic microwave background, CMB radiation. This faint glow, detected across the entire sky, is light that was emitted approximately 380,000 years after the Big Bang, when the universe had cooled enough for the first stable atoms to form. Before this time, the universe was so hot and dense that light could not travel freely. It was constantly scattered by free electrons and protons, making the universe opaque, like a dense fog. When the universe cooled and atoms formed, electrons combined with nuclei, and the universe became transparent. The light from that moment, now stretched and cooled by billions of years of expansion, is what we detect as the CMB. It represents the baby picture of the universe, the oldest light we can ever hope to observe directly. Beyond the CMB, our understanding relies purely on theoretical models, as no light from earlier epochs can reach us. However, the CMB itself provides invaluable information about the conditions of the early universe, including its temperature, composition, and slight variations in density that eventually grew into the large-scale structures we see today. Different types of telescopes allow us to observe different wavelengths of light, each revealing unique aspects of the universe's past. Optical telescopes observe visible light, showing us stars and galaxies as we typically imagine them. Radio telescopes detect radio waves, which can penetrate dust clouds and reveal regions of star formation or distant active galaxies. X-ray telescopes observe high-energy X-rays, allowing us to study phenomena like black holes and hot gas in galaxy clusters. Each wavelength provides a different window into the past, painting a more complete picture of cosmic evolution. The ability to look back in time is not just a fascinating curiosity, it is a critical tool for testing and refining cosmological models, including the Big Bang theory. If the Big Bang theory is correct, then the universe should have looked different in the past, and these differences should be observable. The fact that we see galaxies evolving over time, the presence of the CMB, and the distribution of light elements all provide strong confirmation of the universe's dynamic history, as described by the Big Bang model. Without the finite speed of light, and our ability to measure and interpret it, our understanding of the universe's origins and evolution would be vastly more limited, confined to only the present moment of cosmic existence. The expansion of the universe is not something we can directly see in the way we observe an object moving away from us in everyday life. Instead, scientists infer this expansion from a crucial piece of evidence: the redshift of light from distant galaxies. To understand redshift, we first need to briefly consider the nature of light itself. Light is a form of electromagnetic radiation, which travels in waves. Like all waves, light waves have a wavelength, the distance between two consecutive crests or troughs, and a frequency, the number of waves that pass a point in a given amount of time. The colour of visible light depends on its wavelength. Red light has the longest wavelength, while violet light has the shortest. The phenomenon of redshift is an example of the Doppler effect, which is familiar from sound waves. Imagine an ambulance siren. As the ambulance approaches you, the sound waves are compressed, leading to a higher pitch. As it moves away, the sound waves are stretched out, resulting in a lower pitch. The same principle applies to light waves. If a light source is moving towards an observer, the light waves it emits are compressed, causing their wavelength to shorten. This shift towards shorter, bluer wavelengths is called blue shift. Conversely, if a light source is moving away from an observer, the light waves are stretched, causing their wavelength to lengthen. This shift towards longer, redder wavelengths is called redshift. In astronomy, redshift is a critical tool. When astronomers analyze the light from stars and galaxies, they use a spectroscope to break the light down into its component colors, creating a spectrum. This spectrum contains dark lines or bright lines at specific wavelengths, which are like fingerprints of the chemical elements present in the star or galaxy. For example, hydrogen atoms absorb or emit light at very precise known wavelengths. If a galaxy is moving away from us, these characteristic spectral lines will be shifted towards the red end of the spectrum, compared to where they would be if the galaxy were stationary. The amount of this redshift directly tells us how fast the galaxy is receding. The systematic observation of redshift in distant celestial objects began in the early 20th century. Vesto Slipher, an American astronomer at the Lowell Observatory, was one of the pioneers in this field. Starting in 1912, he meticulously measured the radial velocities, motion towards or away from us, of various spiral nebulae, which were then thought to be gas clouds within our own Milky Way galaxy. To his surprise, Slipher found that the vast majority of these nebulae were exhibiting significant redshifts, meaning they were moving away from Earth at tremendous speeds. By 1917, he had measured the velocities of 25 nebulae, and only a few showed blue shift. This was a puzzling observation at the time, as it implied a general outward motion from our position. The true significance of Slipher's redshifts became clear with the work of Edwin Hubble. Working at the Mount Wilson Observatory in California in the 1920s, Hubble made two monumental contributions. First, he definitively established that many of these spiral nebulae were not gas clouds within our galaxy, but were, in fact, independent galaxies far beyond the Milky Way. He did this by identifying a type of variable star called Cepheid variables in some of these nebulae, which allowed him to accurately determine their distances. Second, and most crucially for the Big Bang theory, Hubble combined his distance measurements with Slipher's velocity measurements. In 1929, he announced his groundbreaking discovery. There was a direct relationship between a galaxy's distance from us and its recession velocity. The further away a galaxy was, the faster it was moving away. This relationship is now famously known as Hubble's law. It can be simply stated as velocity equals Hubble's constant multiplied by distance. This linear relationship was a profound revelation. It was not just that things were moving away, but that the rate of their recession increased with distance. Hubble's law provided the strongest observational evidence yet for an expanding universe. If all galaxies are moving away from each other, and the further ones are moving faster, it implies that the space between them is stretching. It's crucial to understand that this is not like an explosion, where fragments fly outwards from a central point. Instead, it's the fabric of space itself that is expanding, carrying the galaxies along with it, much like dots drawn on the surface of an inflating balloon. As the balloon expands, the dots move further apart, but no single dot is at the center of the expansion, and the dots themselves are not moving on the surface, but the surface itself is growing. Similarly, in the universe, there is no central point of expansion. Every observer, no matter where they are located, would see all other galaxies receding from them. The redshift observed in distant galaxies is therefore not just a measure of their speed through space, but a cosmological redshift, caused by the stretching of the light waves as the space they travel through expands. As the universe expands, the wavelength of the light travelling through it gets stretched, making it appear redder by the time it reaches our telescopes. This cosmological redshift is a direct signature of the universe's ongoing expansion. The discovery of the redshift distance relationship, formalized as Hubble's law, provided powerful support for the Big Bang model, which inherently predicts an expanding universe. It showed that the universe is not static but dynamic and evolving. The rate of this expansion, quantified by Hubble's constant, also allows scientists to estimate the age of the universe. By running the movie backward, if we know how fast things are expanding now, we can calculate how long it would have taken for everything to have been compressed into a very small, dense state. Current estimates, based on the most precise measurements of the Hubble constant and other cosmological parameters, place the age of the universe at approximately 13.8 billion years. The universe, as described by the Big Bang theory, began in an incredibly hot and dense state. As it expanded, it cooled. A crucial prediction of this model, made decades before its discovery, was that the residual heat from this early fiery period should still be detectable today as a faint uniform glow of microwave radiation permeating all of space. This ancient light, often called the cosmic microwave background, or CMB, is the most compelling single piece of evidence supporting the Big Bang. It is essentially the universe's baby picture, showing us what the cosmos looked like when it was only a few 100,000 years old. The idea that such radiation might exist dates back to the 1940s. George Gamow, along with his students Ralph Alpha and Robert Herman, were working on the theory of Big Bang nucleosynthesis, which describes how the first light elements were formed in the early universe. Their calculations indicated that if the universe had been hot and dense enough to fuse hydrogen into helium in its first few minutes, it must have been filled with intense radiation. As the universe expanded and cooled over billions of years, this radiation would have stretched to longer wavelengths, eventually becoming microwaves. In 1948, Alpha and Herman specifically predicted that this leftover radiation should have a temperature of about 5 Kelvin, or 5 degrees above absolute zero, a temperature that would correspond to microwave wavelengths. Their prediction, however, went largely unnoticed by the broader scientific community for many years. For the first 380,000 years after the Big Bang, the universe was a scorching hot opaque plasma. It was so hot that electrons were not bound to atomic nuclei. Instead, free electrons and atomic nuclei, mostly protons and helium nuclei, moved independently. Light or photons could not travel far in this environment without colliding with these free electrons. Imagine trying to walk through an extremely dense fog. You can only see a short distance. The early universe was like this, but for light. Photons were constantly scattering off the charged particles, making the universe effectively opaque. This period is often referred to as the photon epoch. As the universe continued to expand, it cooled. When the temperature dropped to approximately 3000 Kelvin, a critical event occurred. This was about 380,000 years after the Big Bang. At this temperature, the free electrons had slowed down enough to be captured by the atomic nuclei, forming the first stable neutral atoms, primarily hydrogen and helium. This process is known as recombination, though it is a bit of a misnomer because electrons and nuclei were combining for the first time, not recombining. With the electrons now bound within atoms, they were no longer free to scatter photons. Suddenly the universe became transparent to light. The photons that had been trapped and constantly scattering were now free to travel across the cosmos without interruption. These are the photons we detect today as the cosmic microwave background. Over the subsequent 13.8 billion years, as the universe continued its vast expansion, these photons have travelled immense distances. The expansion of space has stretched their wavelength considerably. What was once visible or near-infrared light, with a temperature of 3000 Kelvin, has been stretched so much that its wavelength is now in the microwave portion of the electromagnetic spectrum. Its temperature has cooled to a mere 2.725 Kelvin, or about 2.725 degrees above absolute zero. This is why it is referred to as microwave background radiation. The actual discovery of the CMB was serendipitous. In 1964, two American radio astronomers, Arno Penzias and Robert Wilson, were working at Bell Telephone Laboratories in Holmdel, New Jersey. They were testing a new, highly sensitive horn antenna designed for satellite communication and radio astronomy. Their goal was to eliminate all sources of noise from their receiver. They meticulously checked their equipment, removed pigeon droppings from the antenna, and even considered the possibility of radar from New York City. Despite their best efforts, they kept detecting a persistent uniform low-level static or hiss that came from every direction in the sky, day and night, regardless of the time of year. It was a faint, steady signal that they could not explain or eliminate. Unbeknownst to Penzias and Wilson, a group of physicists at Princeton University, led by Robert Dicke, along with James Peebles, P.G. Roll and David Wilkinson, were independently working on the theoretical implications of the Big Bang. They had in fact rediscovered the prediction made by Gamow, Alpha and Herman, that if the universe began with a hot Big Bang, there should be a faint uniform background of microwave radiation left over. The Princeton team was actually building an antenna to search for this very signal. Through a chance phone call, Penzias learned about Dicke's work, and Dicke learned about Penzias and Wilson's unexplained noise. The connection was immediately clear. Penzias and Wilson had accidentally discovered the cosmic microwave background, the ancient echo of the Big Bang. Their discovery, published in 1965, earned them the Nobel Prize in Physics in 1978. The CMB is incredibly uniform across the entire sky, with variations in temperature of only about 1 part in 100,000. This uniformity is a strong confirmation of the Big Bang's initial homogeneity. However, the tiny variations, or anisotropies, are equally important. These slight temperature differences represent minuscule density fluctuations in the early universe. These tiny ripples, amplified by gravity over billions of years, eventually grew into the vast cosmic structures we see today, such as galaxies, clusters of galaxies, and the large-scale cosmic web. Without these initial seeds of inhomogeneity, the universe would be a featureless, uniform expanse of gas. Subsequent dedicated missions have provided increasingly precise measurements of the CMB. The Cosmic Background Explorer, or COBE satellite launched by NASA in 1989, confirmed that the CMB has a perfect blackbody spectrum, exactly as predicted for thermal radiation from the early universe. This was a crucial test. COBE also detected the tiny temperature fluctuations, providing the first clear evidence of the seeds of cosmic structure. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, provided much higher resolution maps of these fluctuations, allowing scientists to determine key cosmological parameters with unprecedented accuracy, including the age of the universe, its composition of ordinary matter, dark matter, and dark energy, and the geometry of space. Most recently, the European Space Agency's Planck satellite, launched in 2009, produced the most detailed maps of the CMB to date, further refining these measurements and providing even tighter constraints on cosmological models. The cosmic microwave background is not just a relic, it is a powerful probe of the early universe. Its existence, its blackbody spectrum, its uniformity, and its tiny anisotropies all align perfectly with the predictions of the Big Bang theory. It provides a direct observational window into the universe when it was only 380,000 years old, long before the first stars and galaxies had formed. It confirms the universe was once hot, dense, and opaque, and that it has been expanding and cooling ever since. Without the discovery and detailed study of the CMB, the Big Bang theory would remain a compelling hypothesis, but with it, it stands as the overwhelmingly accepted scientific model for the evolution of our cosmos. The Big Bang theory not only explains the expansion of the universe and the existence of the cosmic microwave background, but it also provides a precise account for the observed abundance of the lightest chemical elements in the cosmos. The universe, as we observe it today, is overwhelmingly composed of hydrogen and helium, with trace amounts of lithium. The Big Bang theory accurately predicts the specific proportions of these elements, a process known as Big Bang nucleosynthesis, or BBN. This agreement between theoretical prediction and observational fact serves as another powerful pillar supporting the Big Bang model. To understand BBN, we must go back to the very early universe, specifically the first few minutes after the Big Bang. At this time, the universe was incredibly hot and dense, far too hot for stable atomic nuclei to form. Instead, it was a rapidly expanding and cooling soup of fundamental particles: protons, neutrons, electrons, positrons, neutrinos, and photons. The temperature was so extreme, reaching billions of degrees Kelvin, that protons and neutrons could freely convert into one another. the balance between protons and neutrons was primarily determined by the universe's temperature and the slight mass difference between them. As the universe cooled, the conversion of neutrons to protons became less favourable, leading to a slight excess of protons. For every 7 protons, there was approximately 1 neutron. This ratio is crucial for the subsequent formation of light elements. The actual process of nucleosynthesis began when the universe was only about 1 second old and had cooled to a temperature of about 10 billion Kelvin. At this point, the strong nuclear force, which binds protons and neutrons together, became effective. However, the universe was still hot enough that any newly formed atomic nuclei would be immediately broken apart by high-energy photons. This situation is often referred to as the deuterium bottleneck. Deuterium, an isotope of hydrogen with 1 proton and 1 neutron, is the first step in the formation of heavier elements. But at temperatures above approximately 900 million Kelvin, deuterium nuclei are instantly shattered by energetic photons. Nucleosynthesis could only truly begin when the universe had cooled sufficiently to overcome this deuterium bottleneck. This occurred when the universe was roughly 3 minutes and 46 seconds old, and its temperature had dropped to around 900 million Kelvin. At this temperature, deuterium nuclei could finally survive long enough to fuse further. Once deuterium formed, it quickly combined with other protons and neutrons to build up heavier nuclei. The primary reactions during BBN involved deuterium fusing with protons to form helium-3, and then helium-3 fusing with other nuclei to form helium-4. Helium-4, with 2 protons and 2 neutrons, is an exceptionally stable nucleus, and it was the main product of Big Bang nucleosynthesis. The process was very efficient at converting almost all available neutrons into helium-4. Since there was roughly 1 neutron for every 7 protons, and each helium-4 nucleus requires 2 neutrons, this meant that for every 2 neutrons, there would be 2 protons to form 1 helium-4 nucleus. The remaining 6 protons would stay as individual hydrogen nuclei. This leads to a predicted mass ratio of about 75% hydrogen and 25% helium-4. Beyond helium-4, only trace amounts of other light elements were formed. Some helium-3 and deuterium nuclei did not fuse into helium-4 and remained in their original state. A tiny fraction of lithium-7 was also produced, primarily through the fusion of helium-4 and helium-3, or from the decay of beryllium-7. However, the conditions in the early universe were not suitable for the formation of elements heavier than lithium. The universe was expanding and cooling too rapidly. By the time heavier nuclei like carbon or oxygen could have formed through further fusion reactions, the temperature and density had dropped too low, and the nuclear reactions effectively ceased. All the heavier elements we see today, from carbon to iron and beyond, were forged much later in the cores of stars through stellar nucleosynthesis and supernova explosions. The remarkable aspect of Big Bang nucleosynthesis is the precision with which its predictions match observations. Astronomers measure the abundance of these light elements in the most pristine ancient environments they can find in the universe. This includes distant quasars, which are powered by supermassive black holes in early galaxies, and old metal-poor stars in the halos of galaxies. These environments are chosen because they have undergone minimal stellar processing. That is, their material has not been significantly altered by the nuclear fusion processes occurring in stars, which would change the elemental compositions. The observed cosmic abundance of helium-4 is consistently found to be around 24 to 25% by mass, which aligns almost perfectly with the BBN predictions. The abundance of deuterium is also a crucial test. Because deuterium is easily destroyed in stellar interiors, its primordial abundance is a sensitive probe of the conditions during BBN. Observations of deuterium in distant gas clouds, illuminated by quasars, show an abundance that is also in excellent agreement with the Big Bang model's predictions. Similarly, the observed amount of lithium-7, though subject to some complexities in measurement and theoretical understanding, generally falls within the expected range. The success of Big Bang nucleosynthesis in predicting the primordial abundances of light elements is a powerful validation of the Big Bang model. It demonstrates that the universe was indeed hot and dense enough in its early stages for these nuclear reactions to occur, and that it cooled and expanded at a rate consistent with the observed cosmic expansion. Furthermore, the precise values of these abundances are sensitive to the amount of ordinary matter, or baryonic matter, in the universe. The agreement between BBN predictions and observations allows cosmologists to determine the density of baryonic matter in the universe, which is found to be only about 4 to 5% of the total mass-energy content. This finding provides independent evidence for the existence of dark matter and dark energy, which constitute the vast majority of the universe's mass and energy, respectively. In essence, the light elements serve as fossil records from the universe's infancy. Their measured proportions across the cosmos are a direct consequence of the physical conditions that existed just minutes after the Big Bang. The fact that the Big Bang theory can explain these abundances with such accuracy provides a compelling and quantitative confirmation of its validity, reinforcing its position as the leading scientific explanation for the origin and evolution of our universe. The very first moments of the universe, immediately following the Big Bang, represent a period of extreme conditions where our current understanding of physics is pushed to its absolute limits. While direct observation of this epoch is impossible, theoretical models extrapolated from our knowledge of particle physics and general relativity allow us to paint a speculative yet scientifically informed picture of this unimaginably hot and dense beginning. This period encompasses timescales so brief they are difficult to comprehend, stretching from the Planck time to fractions of a second. The earliest conceivable moment we can discuss is the Planck epoch, which spans from time 0 up to approximately 10 to the power of minus 43 seconds after the Big Bang. At this incredibly tiny fraction of a second, the universe was compressed into a space smaller than a proton, and its temperature was an astounding 10 to the power of 32 Kelvin. In such extreme conditions, all 4 fundamental forces of nature — gravity, electromagnetism, the strong nuclear force, and the weak nuclear force — are thought to have been unified into a single superforce. Our current theories of physics, particularly general relativity, which describes gravity, and quantum mechanics, which describes the other 3 forces, break down at this scale. To fully understand the Planck epoch, a complete theory of quantum gravity is required, which scientists are still striving to develop. Theories like string theory and loop quantum gravity are attempts to bridge this gap. As the universe expanded and cooled slightly beyond the Planck time, gravity is thought to have decoupled or separated from the other 3 fundamental forces. This marked the beginning of the Grand Unification epoch, which lasted until approximately 10 to the power of minus 36 seconds. During this period, the strong, weak, and electromagnetic forces were still unified into a single, grand unified force. The universe was still extraordinarily hot and dense, but the temperature had dropped enough for distinct physical properties to begin to emerge. This epoch is also where the theory of cosmic inflation is often placed. Although inflation will be discussed in detail in another chapter, it is important to note its timing here. If it occurred, inflation was an incredibly brief period of exponential expansion, stretching the universe by a factor of at least 10 to the power of 26 in an almost unimaginably short time, perhaps from 10 to the power of minus 36 seconds to 10 to the power of minus 32 seconds. This rapid expansion would have smoothed out any initial irregularities and set the stage for the uniform and flat universe we observe today. Following the Grand Unification epoch, at around 10 to the power of minus 12 seconds, the universe entered the electroweak epoch. During this phase, the strong nuclear force separated from the electroweak force, leaving only the electromagnetic and weak nuclear forces still unified. The temperature had cooled to approximately 10 to the power of 15 Kelvin, which is still vastly hotter than the core of the hottest stars. At these energies, particles like quarks, leptons, such as electrons and neutrinos, and their antimatter counterparts were abundant. They existed in a hot, dense soup, constantly colliding and transforming into one another. A critical event during this early period, perhaps around 10 to the power of minus 11 seconds, was the breaking of the electroweak symmetry. This is when the electromagnetic force and the weak nuclear force separated, becoming the distinct forces we recognize today. This separation is associated with the Higgs mechanism, which gives mass to fundamental particles. Before this point, particles were massless, but after the electroweak symmetry breaking, they acquired mass through their interaction with the Higgs field. By approximately 10 to the power of minus 6 seconds, the universe had cooled to about 1 trillion Kelvin. This marked the beginning of the quark epoch, or hadron epoch. At this temperature, quarks, the fundamental building blocks of protons and neutrons, were still free and unconfined. The universe was filled with a hot, dense quark-gluon plasma, a state of matter where quarks and gluons, the particles that carry the strong force, moved freely, much like electrons in a metal. However, as the universe continued to expand and cool, the strong force became strong enough to bind quarks together. This process, called hadronization, occurred around 10 to the power of -6 seconds. Quarks combined to form composite particles called hadrons, primarily protons and neutrons. For every proton and neutron formed, there was also an antiparticle, antiproton and antineutron. A crucial puzzle in cosmology relates to this period, the matter-antimatter asymmetry. In the very early universe, matter and antimatter should have been produced in equal amounts. When matter and antimatter particles meet, they annihilate each other, converting their mass entirely into energy, photons. If matter and antimatter had been perfectly symmetrical, the universe would now be filled only with radiation, with no particles left to form stars, galaxies, or life. However, observations show that our universe is overwhelmingly composed of matter, with very little antimatter. Scientists believe that during these first moments, a tiny subtle asymmetry must have existed, perhaps 1 part in 1 billion, favouring matter over antimatter. This slight imbalance, known as baryogenesis, allowed a small residue of matter to survive the annihilation process, eventually forming everything we see today. The exact mechanism for this asymmetry is still an active area of research, potentially involving new physics beyond the standard model of particle physics. By 1 second after the Big Bang, the universe had cooled to about 10 billion Kelvin. At this point, the initial chaos had settled somewhat. The vast majority of matter-antimatter annihilation was complete, leaving behind the residual matter. Protons and neutrons were now stable, distinct particles. The universe was still too hot for atomic nuclei to form, but it was ready for the next crucial stage, Big Bang nucleosynthesis, where these protons and neutrons would begin to fuse into the first light elements, setting the stage for the formation of stars and galaxies billions of years later. The study of these first moments is highly theoretical, relying on the standard model of particle physics, which has been rigorously tested in particle accelerators like the Large Hadron Collider. While these accelerators cannot recreate the extreme energies of the very first instant of the Big Bang, they can probe conditions that existed fractions of a second later, allowing physicists to extrapolate backward in time with increasing confidence. Understanding these initial conditions is vital because they set the fundamental parameters for the universe's subsequent evolution, determining its composition, structure, and ultimate fate. The standard Big Bang model, while remarkably successful in explaining the universe's evolution from a very hot, dense state, faced several significant puzzles in the late 20th century. These challenges concerned observations of the universe's large-scale properties that seemed too finely tuned or too uniform to be explained by the standard model alone. To address these issues, a groundbreaking theoretical concept known as cosmic inflation was proposed. Inflation posits that the universe underwent an incredibly brief but extraordinarily rapid period of exponential expansion immediately after the Big Bang. This expansion was so powerful that it stretched the fabric of space itself by an immense factor, far exceeding the subsequent more gradual expansion we observe today. The idea of inflation was first proposed by American physicist Alan Guth in 1980, building on earlier work by others. Guth was initially trying to solve the problem of magnetic monopoles, hypothetical isolated magnetic charges predicted by some grand unified theories, which should have been abundant in the early universe but have never been observed. As he worked on this problem, he realized that a period of exponential expansion could solve not only the monopole problem, but also 2 other major cosmological puzzles, the flatness problem and the horizon problem. Let us first delve into the concept of this rapid expansion. Inflation is theorized to have occurred extremely early in the universe's history, perhaps starting as early as 10 to the power of -36 seconds after the Big Bang, and ending by about 10 to the power of minus 32 seconds. This means it lasted for an unimaginably short duration, less than a trillionth of a trillionth of a trillionth of a second. During this fleeting moment, the universe is believed to have expanded by a factor of at least 10 to the power of 26, and possibly much, much more. To visualize this, imagine a region of space smaller than a proton, expanding to the size of a grapefruit in that minuscule time, or even larger. This expansion was driven by a hypothetical energy field, often called the inflaton field, which possessed unusual properties causing it to exert a repulsive gravitational force, effectively pushing space apart at an accelerating rate. When the inflaton field eventually decayed, its energy transformed into the hot, dense matter and radiation that filled the universe, initiating the standard Big Bang expansion we know. One of the key problems inflation solves is the flatness problem. Observations of the cosmic microwave background, CMB, have shown that the universe's geometry is remarkably flat. In cosmology, flat refers to a universe where the paths of parallel lines never converge or diverge, much like a flat piece of paper. A curved universe, by contrast, would be like the surface of a sphere, positive curvature, or a saddle, negative curvature. Einstein's theory of general relativity shows that the geometry of the universe depends critically on its total energy density. For the universe to be flat, its total energy density must be incredibly close to a specific critical density. Any deviation from this critical density, even a tiny one in the early universe, would have been magnified by expansion over billions of years, leading to a universe that was either very closed, curved like a sphere, and would have recollapsed quickly, or very open, curved like a saddle, and would have expanded so rapidly that structures could not form. The observed flatness is astounding, requiring the universe's initial density to be within 1 part in 10 to the power of 60 of the critical density. Inflation elegantly solves this. Just as stretching a wrinkled balloon to immense size makes its surface appear flat from any small section, inflation stretches any initial curvature of space so dramatically that the observable universe appears perfectly flat. The second major puzzle inflation addresses is the horizon problem. The cosmic microwave background radiation, which provides a snapshot of the universe when it was about 380,000 years old, appears remarkably uniform in temperature across the entire sky. This means that regions of the universe that are now separated by vast distances, so vast that light could not have travelled between them, even over the age of the universe, exhibit nearly identical temperatures. In the standard Big Bang model without inflation, these regions would have been causally disconnected. That is, they could not have exchanged information or heat. So, how did they come to have the same temperature? Inflation resolves this by proposing that all the regions we observe today originated from an incredibly tiny, causally connected patch of space before inflation began. This tiny patch was in thermal equilibrium, meaning it had a uniform temperature. Inflation then rapidly expanded this small, uniform region to astronomical scales, making it appear as if widely separated areas of the sky are in thermal contact, even though they are now beyond each other's light horizon. A third problem that inflation resolves is the magnetic monopole problem. Some grand unified theories, GUTs, which attempt to unify the strong, weak and electromagnetic forces at very high energies, predict the existence of magnetic monopoles, hypothetical particles that carry an isolated north or south magnetic pole, unlike conventional magnets which always have both. These monopoles would have been produced in vast quantities in the extremely hot early universe, and if they existed, they should be easily detectable today. However, despite extensive searches, no magnetic monopoles have ever been found. Inflation offers a solution. The rapid exponential expansion would have diluted the density of these monopoles to such an extent that their current number density in the observable universe would be virtually zero, making them effectively undetectable. Beyond solving these cosmological puzzles, inflation also provides a mechanism for the origin of structure in the universe. During inflation, tiny quantum-scale fluctuations in the inflaton field were stretched to macroscopic sizes. These microscopic quantum jitters, which are an inherent part of quantum mechanics, became macroscopic density variations. After inflation ended, these slight density enhancements acted as the seeds of cosmic structure. Over billions of years, gravity amplified these initial density differences, pulling more matter into the slightly denser regions, which eventually collapsed to form the first stars, galaxies, and the large-scale cosmic web we observe today. The pattern of these density fluctuations, as imprinted on the cosmic microwave background, is remarkably consistent with the predictions of inflation. For instance, CMB maps show a nearly scale-invariant spectrum of fluctuations, meaning that variations in density occurred on roughly all scales, which is a key prediction of inflationary models. The specific pattern of polarization in the CMB, particularly the B-mode polarization, is also a target for future observations, as it could provide direct evidence of gravitational waves generated during inflation. While inflation theory has become an integral part of the Big Bang model, and its predictions are strongly supported by observations from missions like COBE, BUMAP, and Planck, it is important to remember that it is still a theory. The exact nature of the inflaton field remains unknown, and there are various different models of inflation. However, the basic framework of inflation provides such elegant solutions to fundamental cosmological problems that it is widely accepted by the scientific community as the leading extension to the standard Big Bang theory. It transforms the Big Bang from a moment of unexplained initial conditions into a more comprehensive narrative that addresses why the universe possesses the large-scale properties we observe. In the earliest moments of the universe, immediately following the Big Bang, the cosmos was a place of unimaginably extreme conditions. It was incredibly hot and dense, so much so that matter as we know it could not exist. Instead, the universe was filled with a fundamental soup of pure energy and elementary particles, constantly interacting and transforming into one another. This transformation from raw energy into the building blocks of all matter is a crucial part of the universe's early story. The foundation of this process lies in Albert Einstein's famous equation, E mc2, which describes the equivalence of mass and energy. This equation tells us that mass can be converted into energy, and, critically for the early universe, energy can be converted into mass. In the superheated environment of the very early cosmos, photons or particles of light carried enormous amounts of energy. When two sufficiently energetic photons collided, their energy could spontaneously convert into a pair of particles, a particle and its corresponding antiparticle. For instance, two high-energy photons could produce an electron and its antimatter twin, a positron. This process was happening constantly throughout the universe. So, in the first fractions of a second after the Big Bang, the universe was not empty space but a churning, seething plasma. This plasma was a dense mix of fundamental particles such as quarks, which are the building blocks of protons and neutrons, leptons, which include electrons and neutrinos, and their respective antiparticles, along with a vast sea of energetic photons. These particles were moving at relativistic speeds, meaning their speeds were a significant fraction of the speed of light, and they were constantly colliding, creating new particles and antiparticles, and then annihilating back into pure energy. Let us trace this process through time as the universe expanded and cooled. In the first instance, from the Planck epoch up to perhaps 10 to the power of -6 seconds, the universe was a quark-gluon plasma. At these extreme temperatures, individual quarks were not bound together. They existed freely, along with gluons, which are the force-carrying particles for the strong nuclear force that binds quarks. The universe was a hot, dense fluid where quarks and gluons moved independently, constantly being created and annihilated. As the universe continued to expand, its temperature rapidly dropped. Around 1 microsecond, 1/1,000,000th of a second after the Big Bang, the temperature had cooled to approximately 2 trillion Kelvin. At this critical temperature, the strong nuclear force became strong enough to confine quarks. This process is called hadronization. Quarks could no longer exist freely and instead bound together to form composite particles called hadrons. The most familiar hadrons are protons, which are made of 2 up quarks and 1 down quark, and neutrons made of 1 up quark and 2 down quarks. This was a pivotal moment, as the basic constituents of atomic nuclei were now formed. During this period of particle creation and annihilation, a fundamental imbalance played a critical role in the universe's ultimate fate: the matter-antimatter asymmetry. According to our current understanding, energy should have produced equal amounts of particles and antiparticles. For instance, every time an electron was created, a positron, anti-electron, should also have been created. When a particle encounters its antiparticle, they annihilate each other, converting their entire mass back into energy. If there had been a perfect balance between matter and antimatter, all of the particles and antiparticles produced in the early universe would have annihilated each other, leaving behind a universe composed only of photons and neutrinos, with no ordinary matter to form stars, planets, or life. However, our universe is clearly dominated by matter. There are stars, galaxies, and people, and very little antimatter. This implies that there must have been a tiny, yet incredibly significant asymmetry in the early universe, favouring matter over antimatter. For every billion antiparticles, there was roughly 1,000,000,001 particles. This minuscule excess of matter, perhaps generated through processes like baryogenesis, which is still an active area of theoretical and experimental research, was what survived the annihilation epoch. As the universe continued to cool, the remaining particles and antiparticles annihilated each other, with a tiny surplus of matter, particles being the only survivors. This surviving matter is what makes up everything we see today. After the formation of protons and neutrons, and the general annihilation of antimatter, the universe continued to cool. Electrons, being much less massive than protons and neutrons, could still be readily created and annihilated by photons for a longer period. It wasn't until the universe was about 1 second old that the temperature dropped below the threshold for creating electron-positron pairs. At this point, most electrons and positrons annihilated, leaving behind a residual population of electrons, balancing the positive charge of the protons. Neutrinos, which are very light and interact only via the weak nuclear force, also decoupled from the rest of the matter and radiation around this time, forming a cosmic neutrino background that is difficult to detect but is another relic of this hot, dense epoch. So, by approximately 1 second after the Big Bang, the particle soup had largely resolved into its more familiar constituents. The universe was still a very hot, dense plasma, but it was now primarily composed of protons, neutrons, electrons, and photons, along with a vast number of neutrinos. These were the raw ingredients for the next stages of cosmic evolution, including Big Bang nucleosynthesis, where protons and neutrons would fuse to form the first light atomic nuclei, paving the way for the later formation of atoms, stars, and galaxies. The transformation from pure energy to this initial particle content was a fundamental step in shaping the universe we inhabit. The universe around us is governed by 4 fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These forces dictate how particles interact, how atoms form, how stars shine, and how galaxies cluster together. At first glance, these forces appear distinct, operating in different ways and at vastly different strengths and ranges. However, a cornerstone of modern physics, particularly the study of the very early universe, is the idea of unification, that these seemingly distinct forces were once, under conditions of extreme energy and temperature, unified as a single fundamental force. As the universe expanded and cooled from its initial hot state, this unified force broke into the separate forces we observe today. Let us first briefly describe each of these 4 forces as they appear in our present-day, relatively cool universe. Gravity. This is the force of attraction between any 2 objects with mass or energy. It is the weakest of the 4 forces but has an infinite range. It governs the motion of planets around stars, the formation of stars and galaxies, and the large-scale structure of the entire universe. Electromagnetism. This force governs the interactions between electrically charged particles. It is responsible for all chemical reactions, the behavior of light, electricity, and magnetism. It holds electrons in orbit around atomic nuclei, forming atoms and molecules. Like gravity, it has an infinite range, but its strength is vastly greater than gravity. strong nuclear force. This is the strongest of the four forces, but it acts only over incredibly short distances, typically within the nucleus of an atom. It is responsible for binding quarks together to form protons and neutrons, and for holding these protons and neutrons together within atomic nuclei. Without the strong force, atomic nuclei would fly apart due to the electromagnetic repulsion between positively charged protons. Weak nuclear force. This force is responsible for certain types of radioactive decay, such as beta decay, where a neutron transforms into a proton, or vice versa. It plays a crucial role in nuclear fusion processes in stars, including our Sun, but it has a very short range, even shorter than the strong force, and is significantly weaker than the strong and electromagnetic forces. The concept of force unification is not new to physics. A major triumph in the 19th century was James Clerk Maxwell's unification of electricity and magnetism into a single theory of electromagnetism. Before Maxwell, electricity and magnetism were considered separate phenomena, but he showed they were two different manifestations of the same underlying force, with light itself being an electromagnetic wave. Building on Maxwell's success, physicists in the 20th century began to wonder if the other forces could also be unified. The first major step beyond electromagnetism came in the 1960s and 70s with the electroweak unification. Sheldon Glashow, Abdus Salam, and Steven Weinberg independently developed a theory that showed that at very high energies, the electromagnetic force and the weak nuclear force are not separate, but are two aspects of a single electroweak force. This unification was a monumental achievement, as it demonstrated that forces could indeed merge under specific conditions. This theory predicted the existence of new force-carrying particles, the W and Z bosons, which were later experimentally discovered at the European Organisation for Nuclear Research, or CERN, in the 1980s, providing strong confirmation of the electroweak theory. The energies required for electroweak unification correspond to temperatures that existed in the universe when it was only about 10 to the power of minus 12 seconds old, or 1/1,000,000,000 of a second after the Big Bang. At this incredibly hot stage, particles interacted via the unified electroweak force. As the universe cooled below this critical temperature, the electroweak force broke into the distinct electromagnetic and weak forces we observe today. The next ambitious step in unification is the development of grand unification theories, or GUTS. These speculative theories aim to unify the electroweak force with the strong nuclear force. If a GUT is correct, then at even higher energies, corresponding to temperatures found when the universe was perhaps 10 to the power of minus 36 seconds old, these three forces, electromagnetic, weak, and strong, would have been unified into a single, grand unified force. At these energies, the universe would have been too hot for individual protons and neutrons to form, existing instead as a quark-gluon plasma. As the universe cooled through this epoch, the grand unified force would have broken down, first separating the strong force from the electroweak force, and then the electroweak force further splitting into the electromagnetic and weak forces. GUTS makes several predictions, such as proton decay and the existence of magnetic monopoles, none of which have been definitively observed yet, which means that either these theories are incorrect, or the phenomena occur at rates too rare for us to detect with current technology. The ultimate goal for physicists is to achieve a theory of everything, or TOEU, which would unify all four fundamental forces, including gravity, into a single, comprehensive framework. Such a unification is thought to have occurred at the very highest energies, corresponding to the Planck epoch, which existed up to approximately 10 to the power of minus 43 seconds after the Big Bang. At these unimaginably high temperatures, 10 to the power of 32 Kelvin, gravity would have been as strong as the other forces and unified with them. Developing a theory that successfully integrates gravity with quantum mechanics, which describes the other three forces, is one of the most significant unsolved problems in physics. Theories like string theory and loop quantum gravity are leading candidates for such a quantum theory of gravity and a potential theory of everything. The early universe serves as the only natural laboratory where such extreme energies and temperatures existed, allowing for these force unifications to occur. By studying the remnants of the Big Bang, such as the cosmic microwave background, and by probing high-energy interactions in particle accelerators, scientists hope to find clues that will lead to a complete understanding of how these fundamental forces were unified in the universe's first moments, and how they subsequently separated to shape the physical laws that govern our cosmos today. The idea of forces uniting in the hot, dense early universe is a powerful concept that underscores the deep interconnectedness of physical reality. As the universe continued its rapid expansion after the Big Bang, its temperature steadily decreased. This cooling was essential for the formation of the first stable atomic nuclei and, later, the first complete neutral atoms. This process occurred in two distinct phases. First, the creation of light atomic nuclei during Big Bang nucleosynthesis, and then, much later, the formation of neutral atoms during recombination. Big Bang nucleosynthesis, or BBN, began when the universe was only about 3 minutes and 46 seconds old. Before this time, the universe was too hot, with temperatures exceeding billions of Kelvin for atomic nuclei to hold together. Instead, it was a dense plasma of fundamental particles, primarily protons, neutrons, electrons, positrons, and a vast sea of energetic photons. Protons and neutrons could interconvert, but as the universe cooled, the conversion of neutrons into protons became less favourable, leading to a slight excess of protons. For every 7 protons, there was approximately 1 neutron. This precise ratio was critical for what was to follow. The initial hurdle for nucleosynthesis was the deuterium bottleneck. Deuterium, an isotope of hydrogen containing 1 proton and 1 neutron, is the simplest compound nucleus and the essential stepping stone for building heavier elements. However, at temperatures above approximately 900 million Kelvin, the high-energy photons in the universe would immediately smash apart any newly formed deuterium nuclei. This meant that even though protons and neutrons were present, they could not combine to form stable nuclei until the universe cooled sufficiently. Once the temperature dropped below this critical threshold, around 3 minutes and 46 seconds after the Big Bang, deuterium nuclei could finally survive. This opened the floodgates for a rapid series of nuclear fusion reactions. Deuterium quickly combined with other protons and neutrons to form heavier isotopes. For example, a deuterium nucleus could fuse with another proton to form helium-3, which has 2 protons and 1 neutron. Helium-3 could then fuse with a neutron to form helium-4, which has 2 protons and 2 neutrons, or with another deuterium nucleus to form helium-4. Helium-4 is an exceptionally stable atomic nucleus, and the nuclear reactions during BBN were highly efficient at producing it. Because each helium-4 nucleus requires 2 protons and 2 neutrons, and neutrons were relatively scarce compared to protons, the 1:7 ratio, virtually all available neutrons were incorporated into helium-4 nuclei. The remaining protons, which constituted the vast majority of the baryonic matter, remained as individual hydrogen nuclei. This process continued for about 17 minutes, effectively ending around 20 minutes after the Big Bang, when the universe had expanded and cooled so much that the density and temperature were too low for further nuclear fusion to occur. The result of Big Bang nuclear synthesis was a universe composed of approximately 75% hydrogen and 25% helium-4 by mass, with only trace amounts of deuterium, helium-3 and lithium-7. No heavier elements like carbon, oxygen or iron were formed during this period. The universe simply did not remain hot and dense enough for a sufficient duration to build up these more complex nuclei. The conditions for forming elements beyond lithium require the extreme pressures and temperatures found only in the cores of stars, which would not form for hundreds of millions of years. The predicted abundances of these light elements are one of the strongest pieces of evidence supporting the Big Bang theory. Astronomers observe the cosmic abundances of hydrogen, helium, and lithium in the most pristine ancient regions of the universe, such as distant gas clouds and the oldest stars, which have not been significantly altered by later stellar processes. The measured proportions match the BBN predictions with remarkable accuracy. This agreement confirms that the universe was indeed hot and dense enough in its early stages for these specific nuclear reactions to occur, and that it expanded and cooled at a rate consistent with our current cosmological models. Furthermore, the precise values of these abundances are sensitive to the amount of ordinary matter, or baryonic matter, in the universe. The success of BBN in matching observations provides a strong constraint on the total amount of baryonic matter, indicating it makes up only about 4 to 5% of the universe's total mass energy content. While the nuclei of the first elements were formed within the first 20 minutes, the universe was still too hot for these nuclei to capture electrons and form complete neutral atoms. Free electrons still roamed independently, constantly scattering photons. This state persisted for a much longer period. The universe remained an opaque ionized plasma, much like the interior of a star, where light could not travel freely. The second crucial phase, known as recombination, occurred much later, approximately 380,000 years after the Big Bang. By this time, the universe had continued to expand significantly, and its temperature had dropped to about 3000 Kelvin, roughly the temperature of the surface of a cool star. At this critical temperature, the kinetic energy of the free electrons was low enough that they could be captured by the positively charged atomic nuclei, protons and helium nuclei, to form stable neutral atoms. The term recombination is a bit misleading, as it was the first time electrons and nuclei combined, not a recombination. As electrons combined with nuclei, the universe underwent a dramatic transformation. With electrons now bound within atoms, they were no longer free to scatter photons. The universe suddenly became transparent to light. The photons that had been trapped and constantly scattering within the opaque plasma were now free to travel across the cosmos without interruption. These photons, released at the moment of recombination, are what we detect today as the cosmic microwave background radiation. Its uniform distribution and specific temperature of 2.725 Kelvin are direct evidence of this event. The formation of these first neutral atoms, primarily hydrogen and helium, marked the end of the plasma era and the beginning of the dark ages of the universe. For the first time, matter was organized into stable, neutral structures. This transition was fundamental because it allowed light to travel freely, and it also set the stage for the next major phase of cosmic evolution: the gravitational collapse of this neutral gas to form the first stars and galaxies. Without the birth of these first atoms, the universe would have remained an undifferentiated plasma, incapable of forming the complex structures we observe today. Following the formation of the first neutral atoms during the epoch of recombination, the universe entered a period known as the Cosmic Dark Ages. This era, spanning from approximately 380,000 years after the Big Bang to roughly 300 million to 500 million years later, is characterized by the absence of light sources in the visible spectrum. While the universe was no longer an opaque plasma, it was a largely featureless expanse of neutral gas, primarily hydrogen and helium, with no stars or galaxies yet to illuminate it. The onset of the Dark Ages was marked by the decoupling of matter and radiation. Before recombination, photons were constantly interacting with free electrons, making the universe opaque. Once electrons combined with atomic nuclei to form neutral atoms, these photons were free to travel unimpeded. This moment, 380,000 years after the Big Bang, is when the cosmic microwave background (CMB) radiation was released. As the universe continued to expand, these CMB photons stretched to longer wavelengths and cooled, eventually becoming the faint microwave glow we detect today. During the Dark Ages, the CMB was the only significant source of radiation, and its temperature continued to drop, meaning it provided less and less light in the visible range. During this long stretch of cosmic history, the universe was indeed dark. There were no stars shining, no galaxies blazing with starlight. The gas was almost entirely neutral, meaning its atoms had their full complement of electrons. This neutral gas, predominantly hydrogen and helium, was distributed relatively uniformly throughout space. The small density fluctuations that were imprinted on the cosmic microwave background, originating from quantum fluctuations in the very early universe, were still present, but they were very subtle. The dominant force at play during the Dark Ages was gravity. While the gas was largely uniform, the tiny overdensities, or regions where the gas was slightly denser than average, began to slowly attract more matter due to their slightly stronger gravitational pull. This process of gravitational collapse was incredibly slow during the Dark Ages because the universe was still relatively smooth, and the gravitational forces were weak over the vast distances. An essential component influencing this gravitational collapse was dark matter. Dark matter is a mysterious substance that does not interact with light or other electromagnetic radiation, making it invisible to telescopes. However, it does interact gravitationally. Cosmological models suggest that dark matter makes up about 27% of the universe's total mass-energy content, far more than ordinary baryonic matter. During the Dark Ages, dark matter began to clump together under its own gravity, forming invisible structures known as dark matter halos. These halos acted as gravitational scaffolding, providing the initial gravitational wells into which the ordinary neutral gas could slowly fall. Without dark matter, the gravitational pull of ordinary matter alone would have been insufficient to form structures within the observed timescale of the universe. The temperature of the neutral gas during the Dark Ages continued to fall from the initial 3000 Kelvin at recombination. It eventually reached a minimum of around 10 Kelvin, or 10 degrees above absolute zero, after about 10 million to 100 million years. After this point, as the first structures began to form and contract, the gas within these collapsing regions would start to heat up again due to compression. The chemical composition of the universe during the Dark Ages was extremely simple. It consisted almost exclusively of hydrogen and helium, with only trace amounts of lithium. There were no heavier elements like carbon, oxygen, or iron, as these elements are forged in the interiors of stars and supernova explosions, which had not yet occurred. This lack of heavier elements meant that the cooling mechanisms for the gas were very limited. In the present-day universe, heavier elements act as efficient coolants, allowing gas clouds to radiate away energy and collapse more easily. In the Dark Ages, the primary coolant was molecular hydrogen, H2, which is less efficient than heavier elements. This limited cooling had implications for the properties of the first stars that would eventually form. Observing the Dark Ages directly is extremely challenging. Since there were no stars or galaxies emitting visible or ultraviolet light, conventional telescopes cannot see this period. However, scientists are exploring various indirect ways to probe this era. One promising avenue is through the detection of the 210 centimeter line of neutral hydrogen, also known as the hydrogen line, or spin-flip transition. This specific radio wavelength is emitted when the spin of the electron in a neutral hydrogen atom flips. By observing the redshifted 210 centimeter line from different points in the universe, astronomers hope to map the distribution of neutral hydrogen during the Dark Ages and study how the first structures began to emerge. Projects like the Low Frequency Array, or LOFAR, and the Square Kilometre Array, or SKA, are designed to detect these faint signals. The Dark Ages were a crucial transitional period. It was a time when the universe was literally dark, but beneath the quiet, expanding expanse, the seeds of future cosmic structures were slowly germinating. Gravity, guided by the distribution of dark matter, was patiently gathering the primordial gas into progressively denser clumps. This gradual accumulation of matter laid the groundwork for the universe's next major cosmic revolution, the ignition of the very first stars, which would end the Dark Ages and usher in the era of Ryanization and the formation of galaxies. Without this long, quiet period of gravitational growth, the universe would not have been able to build the complex cosmic tapestry we observe today. The Cosmic Dark Ages, a period of profound darkness lasting for hundreds of millions of years, eventually came to an end with the ignition of the very first stars. These pioneering celestial bodies, often referred to as Population 3 stars, were fundamentally different from the stars we see in the night sky today. Their formation marked a pivotal moment in cosmic history as they began the process of illuminating the universe, forging the first heavy elements and setting the stage for the formation of galaxies. The birth of these first stars was a direct consequence of the gravitational collapse that slowly unfolded during the Dark Ages. As discussed, the universe during this era was filled with a relatively uniform distribution of neutral hydrogen and helium gas, along with the invisible scaffolding of dark matter halos. These dark matter halos, formed by the gravitational clumping of dark matter, created gravitational potential wells into which the ordinary baryonic gas could slowly fall. Within these dark matter halos, regions of slightly higher gas density began to attract more and more surrounding gas. As the gas accumulated, its density increased, and the gravitational pull became stronger, leading to a runaway collapse. However, the process was not as straightforward as in the modern universe. The primordial gas consisted almost entirely of hydrogen and helium, with only trace amounts of lithium. Crucially, there were no heavier elements, which astronomers refer to as metals. In the modern universe, metals play a vital role in cooling gas clouds, allowing them to fragment into smaller, denser clumps that can form stars of various sizes. Without these efficient coolants, the primordial gas had fewer ways to radiate away the heat generated by gravitational compression. The primary cooling mechanism available to the primordial gas was the formation and excitation of molecular hydrogen, or H2. Hydrogen atoms could combine to form H2 molecules, which could then radiate energy away, allowing the gas cloud to cool and contract further. However, H2 is not a very efficient coolant compared to metals. This limited cooling meant that the gas clouds had to be much more massive before they could collapse sufficiently to form stars. As a result, the first stars are predicted to have been extraordinarily massive. Theoretical models suggest that population 3 stars typically had masses ranging from tens to hundreds, or even thousands of times the mass of our Sun. Some models even propose that the very first stars could have been as massive as 100,000 solar masses. This immense mass had profound implications for their characteristics and lifespans. Because of their enormous mass, population 3 stars were incredibly hot and luminous. Their cores reached extreme temperatures and pressures, causing nuclear fusion reactions to proceed at a furious rate. They burned through their hydrogen fuel much more quickly than smaller stars. Consequently, their lifespans were incredibly short, lasting only a few million years, compared to the billions of years our Sun is expected to live. The death of these massive first stars was as dramatic as their birth. They ended their lives in spectacular supernova explosions. These were not just any supernova. They were likely a specific type known as pair instability supernova for the most massive ones. In such an explosion, the star completely disintegrates, leaving no remnant behind. These first supernovae were crucial because they were the universe's first cosmic factories for heavier elements. Inside the cores of these massive stars, nuclear fusion had forged elements up to iron. The supernova explosions then dispersed these newly created heavier elements, such as carbon, oxygen, nitrogen, and silicon, into the surrounding intergalactic medium. This chemical enrichment was essential, as these metals would later become the building blocks for subsequent generations of stars, planets, and eventually life. The supernovae of the first stars also had another profound impact. They contributed to the reionization of the universe. After recombination, the universe was filled with neutral hydrogen and helium. The ultraviolet light emitted by the first stars was energetic enough to strip electrons from these neutral atoms, reionizing the intergalactic medium. This process was gradual, starting in localized bubbles around the first stars and galaxies, and eventually spreading throughout the cosmos. By about 1 billion years after the Big Bang, the universe was largely reionized, making it transparent to ultraviolet light once again. This reionization epoch is another critical phase in cosmic evolution, and its timing and progression are actively studied using observations of distant quasars and the cosmic microwave background. Directly observing population 3 stars is extremely challenging because of their short lifespans and the vast distances involved. They existed billions of years ago, and their light is incredibly faint and redshifted. Current telescopes, even the most powerful ones like the James Webb Space Telescope, are pushing the limits to detect the faint light from the very first galaxies which would contain these stars. While individual population 3 stars have not yet been definitively observed, their existence is inferred from the properties of the cosmic microwave background, the observed abundances of light elements, and the presence of heavier elements in later generations of stars. The chemical composition of the oldest stars we can observe today, known as population 2 stars, shows very low abundances of metals, consistent with them having formed from gas that was only slightly enriched by the supernovae of population 3 stars. The first stars were cosmic pioneers. They ended the long darkness, initiated the chemical enrichment of the universe and began the process of reionization. Their short, violent lives set in motion a chain of events that led to the formation of the galaxies, stars, and planets we see today, ultimately making the universe a more complex and hospitable place. The formation of the first galaxies represents a crucial stage in the evolution of the universe, transforming a relatively smooth, dark expanse of gas into the complex, luminous structures we observe today. This process, which began hundreds of millions of years after the Big Bang, was driven primarily by gravity, with a pivotal role played by the mysterious substance known as dark matter. The standard cosmological model, often referred to as lambda CDM, lambda for dark energy and cold dark matter, provides the framework for understanding how these structures emerged through a hierarchical process, where smaller clumps of matter merged and grew into larger ones. The seeds of galaxy formation were sown much earlier, during the epoch of cosmic inflation, when tiny quantum fluctuations in the very early universe were stretched to macroscopic scales. These fluctuations manifested as minute variations in the density of matter and energy, imprinted on the cosmic microwave background. During the subsequent Dark Ages, as the universe expanded and cooled, these slight overdensities began to exert a stronger gravitational pull on surrounding matter. Crucially, the vast majority of the matter in the universe is not the ordinary baryonic matter, protons, neutrons, electrons, that makes up stars and galaxies, but rather dark matter. Dark matter, which accounts for about 27% of the universe's mass-energy content, does not interact with light or other electromagnetic radiation, making it invisible to telescopes. However, it does interact gravitationally. Because dark matter does not experience the electromagnetic forces that would cause ordinary gas to exert pressure and resist collapse, it was able to clump together much earlier and more efficiently than ordinary matter. During the Dark Ages, dark matter began to coalesce under its own gravity, forming invisible structures known as dark matter halos. These halos were the first large-scale structures to emerge in the universe. They varied in size, from small clumps with masses equivalent to 1 million suns to much larger ones. These dark matter halos acted as gravitational scaffolding, creating the potential wells into which the ordinary baryonic gas, primarily hydrogen and helium, could slowly fall. The process of gas accumulating within these dark matter halos was gradual. As the neutral gas fell into the gravitational embrace of a dark matter halo, it became compressed and heated. For stars to form, this gas needed to cool down so that it could become dense enough to collapse further. In the early universe, without the presence of heavier elements, which act as efficient coolants in modern gas clouds, the primary cooling mechanism for the primordial gas was the formation and excitation of molecular hydrogen, H2. This limited cooling meant that the gas clouds had to be quite massive before they could cool sufficiently to initiate star formation. The very first stars, known as population 3 stars, formed within these early, relatively small dark matter halos. These stars were typically much more massive than our Sun, burning through their fuel rapidly and ending their lives in spectacular supernova explosions within just a few million years. These supernovae were vital as they dispersed the first heavy elements, forged in the star's cores, into the surrounding gas. This chemical enrichment was a critical step, as these newly synthesized metals would later enable more efficient cooling in subsequent generations of gas clouds, allowing for the formation of smaller, more diverse stars. The earliest galaxies were not the grand, spiral or elliptical structures we see today. Instead, they were likely much smaller, irregular clumps of stars and gas, forming within the most massive and densest of the early dark matter halos. These nascent galaxies, sometimes referred to as proto-galaxies or mini-halos, were the building blocks of larger galaxies. The process of galaxy formation is thought to be hierarchical, meaning that small structures formed first, and then merged over cosmic time to create progressively larger ones. As the universe continued to evolve, these early mini-halos and proto-galaxies, still embedded within their dark matter halos, began to attract each other through gravity. They collided and merged, a process that was particularly frequent in the early universe when structures were closer together. These mergers were violent events, disrupting existing stellar orbits, triggering bursts of star formation, and leading to the growth of larger, more complex galaxies. Each merger brought in more gas, more stars, and more dark matter, contributing to the overall growth of the galactic structures. The role of dark matter in this hierarchical formation is paramount. Without its gravitational influence, ordinary matter alone would not have been able to clump together quickly enough to form the observed large-scale structures in the universe. The pressure exerted by the hot gas in the early universe would have prevented it from collapsing into structures on the scales of galaxies. Dark matter, by providing the initial gravitational scaffolding without being affected by pressure or electromagnetic forces, allowed the first structures to form, which then served as the gravitational anchors for ordinary matter. Observations from powerful telescopes like the Hubble Space Telescope and, more recently, the James Webb Space Telescope provide direct evidence for this hierarchical formation. These telescopes can peer deep into the universe, allowing astronomers to observe galaxies as they appeared billions of years ago, when the universe was much younger. They reveal numerous small, irregular, and often interacting galaxies in the early universe, which are consistent with the idea that larger galaxies formed through the mergers of smaller ones. The most distant galaxies observed are often small and appear to be actively forming stars, indicating they are in their early stages of development. Over billions of years, this process of gravitational collapse and hierarchical merging continued. Smaller galaxies merged to form larger ones, and these larger galaxies then grouped together to form galaxy clusters and superclusters, creating the vast cosmic web of filaments and voids that spans the universe today. The dark matter halos continued to grow, encompassing these larger structures. The properties of galaxies, such as their shape, size, and star formation rates, are influenced by their environment and their merger history. For example, elliptical galaxies are thought to be the result of multiple major mergers, while spiral galaxies may have experienced fewer significant merger events. In essence, galaxy beginnings were not a singular event but a continuous process driven by gravity and dark matter. From the initial quantum fluctuations, dark matter provided the gravitational framework for the first halos. Within these halos, primordial gas cooled and collapsed to form the first massive stars. The supernovae of these stars enriched the universe with heavier elements. Subsequently, these early small stellar systems and their dark matter halos merged repeatedly, building up the larger, more diverse galaxies that populate the universe today, a process that continues even in the present epoch. To understand our place in the vastness of the universe, it is helpful to consider our cosmic address, a hierarchical description that places our home planet within progressively larger structures, from our immediate neighborhood to the observable limits of the cosmos. This journey through scale provides a profound sense of perspective on the immense distances and structures that comprise the universe. Our journey begins on Earth, a rocky planet orbiting a star. Earth is the third planet from the Sun, a yellow dwarf star. The Sun, along with its 8 planets, numerous dwarf planets, asteroids, comets, and other celestial bodies, forms our solar system. The solar system is a relatively small, gravitationally bound system located in one of the spiral arms of a much larger structure. The solar system resides within the Milky Way galaxy. The Milky Way is a barred spiral galaxy, a vast collection of hundreds of billions of stars along with gas, dust, and dark matter, all bound together by gravity. Our Sun is located in the Orion Arm, one of the smaller spiral arms of the Milky Way, approximately 27,000 light-years from the galactic center. To give a sense of scale, the Milky Way galaxy is estimated to be about 100,000 light-years in diameter and approximately 1,000 light-years thick. The Sun orbits the galactic center once every 230 million years, a period known as a cosmic year. From our vantage point within the disk, we see the collective light of billions of stars as a hazy band across the night sky, which is why it is called the Milky Way. The Milky Way galaxy is not alone in the universe. It is part of a small cluster of galaxies known as the Local Group. The Local Group is a gravitationally bound collection of over 50 galaxies, though most of these are dwarf galaxies. The two largest and most dominant members of the Local Group are the Milky Way and the Andromeda Galaxy. The Andromeda Galaxy, a large spiral galaxy, is about 2.5 million light-years away and is on a collision course with the Milky Way, with a predicted merger occurring in about 4.5 billion years. Other notable members of the local group include the Triangulum Galaxy, the Large Magellanic Cloud, and the Small Magellanic Cloud, the latter two being satellite galaxies of the Milky Way. The local group itself spans approximately 10 million light-years across. The local group, in turn, is a small component of an even larger structure, a supercluster of galaxies. For many years, the local group was considered part of the Virgo supercluster, a massive collection of galaxy clusters centered on the Virgo cluster, which is about 54 million light-years away. The Virgo supercluster contains thousands of galaxies and spans roughly 110 million light-years. Our local group is located near the edge of this supercluster, and we are gravitationally attracted towards its center. However, more recent and detailed mapping of the universe's large-scale structure has revealed that the Virgo supercluster is itself just a lobe of an even grander, more extensive supercluster, which has been named the Laniakea supercluster. The name Laniakea means immense heaven in Hawaiian. Discovered in 2014, the Laniakea supercluster is defined by the gravitational flow of galaxies towards a common center of mass, a region known as the Great Attractor. The Laniakea supercluster is truly enormous, containing approximately 100,000 galaxies and spanning about 500 million light-years across. Our local group is located near the edge of Laniakea, and we are, along with thousands of other galaxies, slowly being pulled towards the Great Attractor. Beyond the Laniakea supercluster, the universe continues to unfold into an intricate web-like pattern of galaxy clusters, superclusters, and vast, nearly empty regions called voids. This large-scale structure is often referred to as the cosmic web. Galaxies and clusters are concentrated along filaments, which are like cosmic threads, while between these filaments lie immense voids where galaxies are scarce. This cosmic web is the largest known structure in the universe, stretching for billions of light-years. The largest structure we can observe is the observable universe itself. This is not the entire universe, which may be infinite in extent, but rather the portion of the universe from which light has had enough time to reach us since the Big Bang. Because the universe is approximately 13.8 billion years old, and light travels at a finite speed, the maximum distance from which we can receive light is about 13.8 billion light-years in any direction. However, due to the ongoing expansion of the universe, the actual distance to the most distant objects whose light we are now receiving is much greater, estimated to be around 46.5 billion light-years in every direction from us. This means the diameter of the observable universe is approximately 93 billion light-years. Within this immense observable universe, there are estimated to be hundreds of billions, possibly even trillions of galaxies, each containing hundreds of billions of stars. Each of these stars may host its own system of planets. The sheer scale is almost incomprehensible. Our Earth is a tiny speck of dust orbiting an average star, which is one of hundreds of billions of stars in a galaxy that is one of dozens in a small group, which is part of a larger supercluster, itself embedded within the vast cosmic web that fills the observable universe. Understanding our cosmic address provides a crucial perspective. It highlights that we are not at the center of the universe, nor are we particularly special in a cosmic sense. Our existence is part of a grand narrative of cosmic evolution, from the Big Bang to the formation of stars, galaxies, and ultimately complex life. This hierarchical view of the cosmos underscores the vastness and complexity of the universe, reminding us of the ongoing scientific quest to explore and understand our place within it. The Big Bang Theory provides a highly successful framework for understanding the evolution of our universe from an incredibly hot, dense state to its current vast and complex form. It explains the expansion of space, the cosmic microwave background radiation, and the abundance of light elements with remarkable accuracy. However, despite its triumphs, the Big Bang Theory, in its current form, encounters a fundamental limitation when attempting to describe the very first instant of the universe, the concept of a singularity. This edge of knowing represents a boundary beyond which our current laws of physics, particularly general relativity, break down. leaving crucial questions about the universe's ultimate origin unanswered. A singularity, in the context of general relativity, is a point where the density of matter and the curvature of space-time become infinite. According to the standard Big Bang model, if we extrapolate the universe's expansion backward in time, all matter and energy would converge to an infinitely dense point at time zero. This is often referred to as the initial singularity. While mathematically convenient, an infinite density and infinite curvature are problematic for physics. Infinities generally signal that a theory is incomplete or being applied beyond its valid domain. When general relativity predicts a singularity, it essentially tells us that it can no longer describe what is happening at that point. It is a mathematical breakdown, not necessarily a physical description of reality. One of the key figures in understanding this limitation was Stephen Hawking, who, along with Roger Penrose, developed the singularity theorems in the 1960s and 70s. These theorems demonstrated that, under very general conditions, assuming general relativity is correct and that the universe contains a reasonable amount of matter and energy, an initial singularity is an unavoidable consequence of the universe's observed expansion. This means that if we trace the universe back far enough, we inevitably arrive at a point where the density and curvature of space-time become infinite, and the concept of space and time, as we understand them, ceases to exist. The problem with the singularity is that it prevents us from asking what happened before, or what caused it. If all of space and time originated from this singular point, then the very concept of before becomes meaningless within the framework of general relativity. The theory simply cannot provide answers to these questions because its equations no longer apply. It is like trying to use a map that only shows roads to describe the ocean. It is the wrong tool for the job. The breakdown of general relativity at the singularity points to the need for a more comprehensive theory, one that can seamlessly integrate gravity with quantum mechanics. General relativity is a classical theory, meaning it describes gravity on large scales, but it does not account for the quantum nature of reality at extremely small scales. Quantum mechanics, on the other hand, describes the behavior of particles and forces at the atomic and subatomic level, where uncertainties and probabilities dominate. At the Planck scale, which is an unimaginably tiny length, about 10 to the power of minus 35 meters, and time, about 10 to the power of minus 43 seconds, quantum effects of gravity are expected to become dominant. The initial singularity of the Big Bang occurs precisely at this Planck scale, where both general relativity and quantum mechanics are simultaneously relevant, and neither theory alone is sufficient. This is where the quest for a theory of quantum gravity becomes paramount. Such a theory would aim to unify general relativity with quantum mechanics, providing a consistent description of gravity at extremely small scales and high energies. Leading candidates for a theory of quantum gravity include string theory and loop quantum gravity. These theories offer potential ways to resolve the singularity problem. String theory, for instance, proposes that fundamental particles are not point-like, but are instead tiny, vibrating one-dimensional strings. At the Planck scale, these strings would smear out the singularity, preventing infinite densities from arising. In some string theory models, the Big Bang might not be the absolute beginning, but rather a transition from a previous state, perhaps a collision of higher dimensional branes. This could potentially eliminate the singularity by replacing it with a finite, albeit extreme event. Loop quantum gravity, another approach, suggests that space-time itself is not continuous, but is granular, made up of discrete loops, or atoms of space-time at the Planck scale. In this framework, the singularity might be replaced by a big bounce, where the universe contracts to a minimum but finite size before rebounding into expansion, avoiding infinite density. This would imply that our universe is part of a cyclic process, with no true beginning or end. The edge of knowing also extends to the very early universe before the electroweak epoch, particularly the period of cosmic inflation. While inflation theory successfully addresses several puzzles of the standard Big Bang model, such as the flatness and horizon problems, it does not explain what caused inflation itself or what existed before it. Inflationary models typically require an inflaton field to drive the exponential expansion, but the precise nature of this field and its initial conditions are still unknown. Some inflationary scenarios, particularly chaotic inflation, suggest that inflation might be eternal, leading to a multiverse where new universes are constantly being spawned. If this is the case, then our Big Bang is just one event in a much larger, eternally inflating cosmos, pushing the ultimate origin question to a higher level of complexity. Furthermore, the edge of knowing encompasses the fundamental constants of nature. The values of these constants, such as the strength of gravity, the mass of an electron, or the speed of light, appear to be finely tuned for the existence of stars, galaxies, and life. If these constants were even slightly different, the universe might be radically different or incapable of supporting complex structures. The Big Bang theory does not explain why these constants have their particular values. Some physicists appeal to the anthropic principle or the multiverse concept to address this, suggesting that we simply find ourselves in a universe where these values are suitable for our existence, and other universes might have different values. However, these are philosophical arguments rather than direct scientific explanations derived from a fundamental theory. In essence, the initial singularity of the Big Bang represents a boundary for our current physical theories. It is the point where general relativity, our best description of gravity on large scales, breaks down. Overcoming this limitation requires a quantum theory of gravity, which is one of the most challenging and active areas of research in theoretical physics. Until such a theory is developed and experimentally verified, the very first instant of the universe will remain shrouded in mystery, an ultimate edge of knowing that continues to inspire scientific inquiry. The question, what caused the Big Bang, naturally leads to an even more profound and challenging inquiry. What was there before the Big Bang? This question, however, immediately confronts a fundamental conceptual hurdle. The notion that time itself, as we understand it, may have begun with the Big Bang. If time originated with the universe's expansion, then the concept of before becomes meaningless in a physical sense, posing a significant challenge to both scientific and philosophical thought. In the framework of general relativity, space and time are not separate, fixed entities, but are interwoven into a single fabric called spacetime. This fabric is dynamic, capable of being stretched, warped, and curved by the presence of mass and energy. The Big Bang theory describes the evolution of this spacetime fabric from an initial, extremely dense and hot state. According to the Standard Model, if we trace the expansion of the universe backward in time, we arrive at a point where spacetime itself collapses to an infinitely dense singularity. At this singularity, not only does matter become infinitely compressed, but the very fabric of spacetime ceases to exist in a meaningful way. If spacetime itself began at the Big Bang singularity, then there was no before in the temporal sense. Time, as a dimension along which events unfold, would have emerged with the universe. This is a difficult concept to grasp because our human experience is deeply rooted in a linear progression of time, where every event has a preceding cause. We intuitively think of a beginning as something that must have been preceded by something else. However, if time itself is a property of the universe, and the universe began at the Big Bang, then asking what happened before is akin to asking what is north of the North Pole. The question loses its meaning within the defined coordinate system. This idea was famously articulated by Stephen Hawking, who suggested that asking what happened before the Big Bang is like asking what is south of the South Pole. There is nothing south of the South Pole because the concept of south breaks down at that point on the globe. Similarly, the concept of before breaks down at the Big Bang singularity. This perspective implies that the universe, along with time, simply came into existence at that point, and there is no prior physical state or temporal dimension to discuss. However, this interpretation is based on general relativity, which, as discussed, breaks down at the singularity. The search for a quantum theory of gravity aims to resolve this breakdown and might offer alternative perspectives on the nature of time at the very earliest moments. If a quantum theory of gravity eliminates the singularity, replacing it with a finite, albeit extreme state, then the concept of before might regain some physical meaning, though perhaps not in the conventional sense. One theoretical possibility that addresses time before time is the Big Bounce hypothesis. This idea, often explored within the framework of loop quantum gravity, suggests that the Big Bang was not the ultimate beginning, but rather a rebound from a previous contracting universe. In this cyclic model, the universe undergoes an endless series of expansions and contractions. A previous universe would have contracted to an extremely dense but finite state, avoiding the singularity, then bounced back into expansion, leading to our current Big Bang. If the Big Bounce is correct, then there was indeed a before, a previous cosmic cycle, and time would have existed continuously through the bounce, albeit in a highly compressed and extreme form. This model offers a way to avoid the problem of an absolute beginning of time. Another approach comes from certain models within string theory and M theory, which propose higher dimensions and the existence of branes, multi-dimensional membranes. In some brane cosmology scenarios, our universe is a three-dimensional brane existing within a higher dimensional space. The Big Bang, in this context, could be the result of a collision between two such branes, or a brane emerging from a higher dimensional bulk. In these models, time might exist in the higher dimensional space even before the brane collision that created our universe. This would mean that before our Big Bang, there was a different kind of reality, operating in higher dimensions, with its own temporal progression. The concept of an eternal inflation also touches upon the idea of time before time. In some inflationary models, inflation, once it starts, never truly ends everywhere. Instead, it continues indefinitely in some regions, constantly spawning new bubble universes within a vast, ever-inflating multiverse. In this scenario, our Big Bang would be just one such bubble universe emerging from a larger, eternally inflating background. Time in the larger multiverse could be continuous, with our universe's beginning being a local event within that larger temporal framework. Philosophically, the idea of time having a beginning is deeply challenging. It forces us to reconsider our fundamental assumptions about causality and existence. If there was no time before the Big Bang, then the concept of a cause in the traditional sense becomes problematic. A cause typically precedes its effect in time. If there is no time, there can be no temporal precedence. This leads to questions about whether the universe caused itself, or if the concept of causation needs to be redefined for the very origin of existence. Ultimately, the question of time before time remains one of the most profound and unanswered questions in cosmology and philosophy. Our current scientific models, primarily general relativity, suggest a beginning of time at the Big Bang singularity. However, the limitations of these models at extreme conditions motivate the search for a quantum theory of gravity, which might offer new insights such as a big bounce or a higher dimensional reality, where time could have a more continuous existence. Until such a theory is developed and confirmed, the nature of time at the universe's origin will continue to be a subject of intense speculation and research. Quantum mechanics is a fundamental theory in physics that describes the behavior of matter and energy at the smallest scales, particularly at the level of atoms and subatomic particles. Unlike classical physics, which describes the world in terms of definite positions and momenta, quantum mechanics introduces concepts that are often counterintuitive and probabilistic. Understanding its basic principles is crucial for comprehending the conditions of the very early universe, where quantum effects were dominant and profoundly shaped the cosmos. One of the core principles of quantum mechanics is quantization. This means that certain physical quantities, such as energy, angular momentum, and electric charge, do not exist in continuous values but rather in discrete packets, or quanta. For example, an electron in an atom can only occupy specific energy levels. It cannot exist at any energy in between. When an electron moves from one energy level to another, it absorbs or emits a specific quantum of energy, typically in the form of a photon. This concept was first introduced by Max Planck at the turn of the 20th century to explain black-body radiation, and it revolutionized physics. Another fundamental concept is wave-particle duality. Quantum mechanics posits that particles, such as electrons and photons, can exhibit properties of both waves and particles. For instance, light can behave as a wave, demonstrating phenomena like diffraction and interference, but it can also behave as a particle, photon, carrying discrete packets of energy. Similarly, Electrons, which we typically think of as particles, can also exhibit wave-like behaviour, as shown in electron diffraction experiments. This duality means that the traditional distinction between waves and particles breaks down at the quantum level. The Heisenberg uncertainty principle is a cornerstone of quantum mechanics. Formulated by Werner Heisenberg, it states that there are fundamental limits to the precision with which certain pairs of physical properties of a particle, such as its position and momentum, can be known simultaneously. The more precisely you measure one property, the less precisely you can know the other. This is not a limitation of our measuring instruments, but an inherent property of nature at the quantum scale. For example, if you know an electron's exact position, its momentum becomes completely uncertain, and vice versa. This principle has profound implications for the vacuum itself. According to quantum mechanics, even seemingly empty space, or the quantum vacuum, is not truly empty. Instead, it is a hive of activity, constantly fluctuating with the spontaneous creation and annihilation of virtual particles. These particle-antiparticle pairs briefly pop into existence from the vacuum, exist for an incredibly short time, and then disappear back into the vacuum, all in accordance with the uncertainty principle. While these virtual particles cannot be directly observed, their effects are measurable, for example, in the Casimir effect. This concept of a dynamic, fluctuating vacuum is highly relevant to the early universe. The probabilistic nature of quantum mechanics is another key departure from classical physics. Unlike classical physics, which predicts definite outcomes for events, quantum mechanics predicts the probabilities of various outcomes. For example, when an electron is in a superposition of states, a combination of multiple possible states simultaneously, we cannot know its exact state until it is measured. The act of measurement collapses the wave function, forcing the electron into a single definite state. This inherent randomness and the role of observation are central to the quantum world. The relevance of these quantum mysteries to the early universe is profound. In the very first moments after the Big Bang, the universe was incredibly small, dense, and hot. It was compressed to scales where quantum effects were not just relevant but absolutely dominant. The entire observable universe, which is now billions of light years across, originated from a region that was smaller than a subatomic particle. At these scales, the classical laws of physics, particularly general relativity, which describes gravity on large scales, break down. This is where the need for a quantum theory of gravity arises. To fully understand the Planck epoch, from time 0 to 10 to the power of minus 43 seconds, where all four fundamental forces were unified, and quantum effects of gravity were significant, a theory that successfully combines quantum mechanics with general relativity is essential. Without it, we cannot fully describe the initial conditions of the universe or resolve the singularity problem. Theories like string theory and loop quantum gravity are attempts to achieve this unification. Furthermore, quantum mechanics plays a crucial role in the origin of structure in the universe, particularly through the theory of cosmic inflation. Inflation proposes that the universe underwent an extremely rapid, exponential expansion in its earliest moments. During this inflationary period, tiny microscopic quantum fluctuations in the energy field driving inflation, the inflaton field, were stretched to macroscopic scales. These quantum jitters, which are inherent uncertainties in the quantum vacuum, became the seeds of all the large-scale structures we see today. The slight overdensities caused by these stretched quantum fluctuations eventually grew, under gravity, into the galaxies, galaxy clusters, and the vast cosmic web. The observed pattern of temperature fluctuations in the cosmic microwave background radiation is remarkably consistent with the predictions of inflation, reinforcing the idea that quantum mechanics played a fundamental role in shaping the universe's structure. The matter-antimatter asymmetry, another puzzle of the early universe, may also find its explanation in quantum mechanics. While the precise mechanism is still unknown, theories of baryogenesis suggest that subtle quantum processes in the very early universe, perhaps involving interactions beyond the standard model of particle physics, led to a slight excess of matter over antimatter, allowing our matter-dominated universe to exist. In classical physics, a vacuum is understood as simply empty space, a region devoid of matter or energy. If one were to remove all particles, all radiation, and all fields from a given volume, what would remain, according to classical thought, is nothingness. Picture a cosmos so old that distance loses meaning, and history thins into pure geometry. In that austere silence, a radical proposal appears, not as myth, but as mathematics. We are used to endings that leave wreckage, debris to sift, ruins to date, a last scene to remember. But the far future may offer something stranger. Not a final event, but a limit where ordinary descriptions stop applying. In that limit, the universe does not simply grow empty, it grows scaleless. When no stable bound systems remain, the very tools of measurement, clocks, rulers, and the rhythms that anchor before and after can become impossible to define. That is where Roger Penrose begins his wager, an idea called conformal cyclic cosmology. It asks whether the deepest future can be re-expressed through a change of geometric perspective, as the kind of beginning we once thought belonged only to the past. This documentary follows the question where it becomes uncomfortable. If expansion and entropy drive the cosmos toward uniformity, why did the early universe appear so smooth, so low in gravitational disorder, and so precisely poised for structure to form? We will walk through the mainstream forecast with no shortcuts. Accelerated expansion, fading gradients, and the slow exile of galaxies beyond each other's horizons. We will linger where the last reservoirs of complexity persist, and where even temperature becomes a word without a practical instrument. Then we turn to the heart of the mystery, light. Massless particles trace paths that do not carry proper time, and a universe dominated by them may have no preferred scale at all. Penrose claims that this scale-free simplicity is not merely poetic, it is a symmetry. In conformal geometry, angles and causal structure survive rescaling, while absolute size evaporates like an unneeded coordinate. If that symmetry truly governs the final state, an astonishing move becomes thinkable. The infinite future of one cosmic era can be compressed to a boundary, and that boundary can be matched to a new origin. But elegant mathematics is not an ending, evidence is. The cosmos has left as a backlight the microwave afterglow so uniform that its tiny imperfections became a map of everything that followed. Conformal cyclic cosmology suggests that this sky might also contain faint scars from an earlier era, subtle patterns that would not be expected if our beginning was the first of its kind. We will examine those claims with the discipline they demand, because the microwave sky is a battlefield of statistics. Foregrounds must be stripped away, pipelines must be tested, and coincidences must be separated from predictions. And beyond observation lies a deeper obstacle: black holes, quantum fields, and the fate of information. Hawking radiation makes horizons evaporate, but the last stages press against quantum gravity, where certainty becomes expensive. So our journey is not a promise of a cycle, and not a sermon against one. It is an investigation into what after could mean when time depends on mass, and when geometry may be the only thing left that still counts. By the end, the question will feel less like science fiction, and more like a mirror held to our assumptions. If the universe can be described without scale, then perhaps the boundary between conclusion and origin is thinner than intuition allows. One fact remains: whatever answer survives. Our cosmology is a story written in light, and in the farthest chapters, light may be all that remains to write with. We begin at the edge of the last usable energy, then trace entropy's logic toward a scale-free future where clocks fail. From there, we return to the first dawn and finally to the microwave sky, where any echo of a previous era must either appear or vanish under scrutiny. Imagine a time so far ahead that every familiar landmark of the cosmos has expired. Not just civilizations, not just planets, but the engines that make structure possible: stars, gradients, and the steady flow of usable energy. Cosmology calls this destination heat death, and it is less an explosion than a quiet arithmetic. Entropy rises, free energy falls, and the universe approaches a state where nothing useful can happen. In that far horizon, drama is replaced by bookkeeping, and the numbers drift toward equilibrium. Heat death is not a poetic phrase, it is the thermodynamic end state of an expanding universe that keeps mixing and thinning, while gravity slowly runs out of new ways to clump matter. Maximum entropy means the remaining energy is spread too evenly to drive work. Minimal free energy means no gradients remain to power stars, chemistry, or memory, because every difference that once mattered has been diluted away. The cosmos becomes dominated by thin radiation and inert matter, drifting through an ever larger space-time. Even cold becomes a subtle word here, because temperature is not just low, it is irrelevant to doing anything. Endings matter in cosmology because they test what our laws actually mean. A theory that explains beginnings but cannot follow the future is incomplete, especially when the future is a long, clean extrapolation of known physics. The universe is our only laboratory at the largest scale, and its fate is a prediction we can compare across models, parameters, and assumptions. The stakes are not personal survival. The stakes are whether time, causality, and geometry keep their meaning when the last sources of order are gone. When the universe becomes almost featureless, we learn which parts of our descriptions were essential, and which were merely convenient. The standard story begins with abundance and ends with exhaustion, and it does so in stages that are slow enough to feel almost timeless. In the near future, star formation slows as galaxies run out of cold gas, and as feedback from earlier generations heats what remains. The brightest, shortest lived stars vanish first, and the sky becomes redder and dimmer as long-lived, cooler stars dominate. Over trillions of years, stellar nurseries shut down, and galaxies stop making new light, because the raw material for fusion is either locked away or too diffuse. What remains are long-lived dwarf stars, stellar remnants, and the slow rearrangement of orbits, as gravity keeps shuffling the same pieces. Visually, the change is not a sudden blackout. Spiral arms lose their glittering blue knots, and the bright, dusty lanes that once marked starbirth fade into a smoother, older glow. Clusters that once looked like cities of fire become suburbs of embers, with wide, dark gaps between them. The universe still contains stars, but it contains fewer reasons for anything to change quickly. Time stretches, and the sky's palette shifts toward deep reds and faint infrared, like a photograph left too long in the sun. As the fuel runs out, the cosmic inventory shifts from living stars to leftovers. White dwarfs cool toward blackness as they radiate away their stored heat, sliding down a thermal curve that takes longer than most cosmic eras. Neutron stars spin down as magnetic braking drains their rotational energy, and their once lighthouse beams go quiet. Any remaining heat leaks away, photon by photon, into an expanding sea of background radiation. Planets become frozen rocks, then slowly eroded by rare impacts, cosmic rays, and the steady sputtering of atoms from their surfaces. Even stable matter is not guaranteed to last if protons decay, as some grand unified theories suggest, because then the very idea of solid becomes temporary. The timeline is uncertain, but the direction is not, and the arrow points toward dispersion. There is historical weight behind this arrow. In the 19th century, thermodynamics taught physicists that heat flows from hot to cold and never naturally reverses, and that insight became a cosmic forecast once general relativity and expansion entered the picture. The second law is not merely a rule of engines, it is a statement about probability, about how many microstates correspond to disorder compared with order, and the universe has an overwhelming statistical bias toward the bland. Heat death is that bias written on the largest canvas. Galaxies themselves do not last as coherent cities of stars. Encounters and mergers rearrange them, and gravitational interactions fling many objects into intergalactic space, where they drift as lonely points in a nearly empty dark. Within bound groups, close passes act like slingshots, trading energy until many stars are ejected and only the tightest systems remain. The expansion of the universe isolates bound groups from one another, making each island of matter increasingly alone. In the far future, most of the observable universe becomes unreachable, not because light fails, but because space grows between us and carries distant regions beyond any future signal. The cosmic horizon becomes less a line we could cross, and more a limit on what can ever matter to us. Eventually, the dominant actors are black holes. They are the densest repositories of mass and the deepest sinks of entropy, because their horizons hide information in a way that looks, from outside, like irretrievable loss. In a fading cosmos, black holes become the final engines, not because they create order, but because they store energy and release it slowly through subtle processes. They swallow stray matter, merge in rare but titanic collisions, and settle into quiet as gravitational waves ripple outward and then thin into insignificance. For a time, they are the last places where something still happens, and the last places where the universe still has a center of activity. To picture this era, imagine a black sky with almost no stars, punctuated only by occasional faint glows from accretion. Brief, localized fireworks as a wandering remnant falls into a horizon. Then the fireworks stop. What remains are black holes as silent masses, each surrounded by emptiness so vast that even the idea of a neighborhood loses meaning. The universe becomes a sparse museum of extreme objects, and the exhibits are separated by distances that grow faster than any traveler could cross. Then even black holes are not forever. Hawking radiation predicts that black holes leak energy as quantum fields fluctuate near the horizon, producing particles that escape as if the hole had a temperature. The process is unimaginably slow for large holes, but the mathematics is clear, and the rate depends strongly on mass. A stellar mass black hole would take far longer than today's cosmic age to evaporate, while a supermassive one would endure for timescales that dwarf even that. Over vast spans, black holes evaporate, shedding mass into thin radiation, and their temperatures rise as they shrink. The final flashes are brief and small compared with the age that precedes them, like a match struck after eons of darkness. After the last evaporation, the universe is close to a pure bath of low-energy photons and other nearly massless particles. Any remaining matter is either extremely dilute or absent, depending on the true stability of particles and the fate of any long-lived remnants. Temperature trends toward a limit set by expansion, and density trends towards zero, because volume grows while content thins. This is the classic quiet fade-out. It is the end written by thermodynamics, with no dramatic curtain call, only a long approach to sameness. The universe does not stop so much as it loses the ability to do anything distinguishable. But heat death raises a deeper problem than darkness. Time is not just a number on a page. Time is measured by change, and change is tracked by clocks, and clocks require physical processes that repeat or decay at a definable rate. If everything massive is gone, and only massless particles remain, what counts as a clock? If nothing can form a stable bound system, what defines duration? When we say later in such a world, later than what, and measured by which rhythm? In ordinary physics, mass sets scales. Mass gives atoms their sizes through quantum mechanics, sets decay rates through particle interactions, and anchors rulers and clocks by providing stable bound states. With only radiation, the universe has motion but no preferred rest frame, and no natural yardsticks. Because scale becomes slippery, photons always move at light speed, and they do not carry an internal ticking like a spinning planet or a vibrating atom. In that limit, the question becomes unsettling. Does time still have operational meaning, or is it only a coordinate we keep writing out of habit, like a label on an empty map? This is where the documentary's mystery enters, because the far future is not merely a destination but a stress test. The standard model says the universe asymptotically approaches a featureless state, and that is that, with dynamics fading into near nothing. Yet some physicists ask whether the far future could be reinterpreted, not as a terminal state, but as a boundary that can be mapped into something new. The idea sounds like metaphysics until it becomes geometry, because geometry decides what counts as the same when scales disappear. Under the right lens, an ending might be mathematically indistinguishable from a beginning, not by miracle but by symmetry. One proposal makes that claim with unusual boldness. Conformal cyclic cosmology, or CCC, argues that the universe is not a one-time story. It is a sequence of aeons, each beginning with a Big Bang-like event and ending in an ultra-dilute, radiation-dominated future, where the last structures dissolve. The bridge between aeons is not a bounce of matter. It is a rescaling of space-time itself, a change of the ruler rather than a reversal of the arrow. CCC starts from a specific observation about massless physics. For particles with no mass, only angles and light cones matter, not absolute distances, because there is no rest frame in which a particle can sit and define a scale. The equations become conformally invariant, meaning the geometry can be stretched without changing the essential behavior of those fields. In an extreme future where everything effectively behaves as massless, CCC says the universe loses its intrinsic scale. If scale disappears, infinity can be reinterpreted, because infinitely large is a statement that depends on having a yardstick. In that picture, the infinite future of one aeon can be conformally squashed into a finite boundary. That boundary can then be identified with the Big Bang of the next aeon, because both are dominated by radiation and lack a meaningful scale. The claim is not that the same matter cycles back, or that galaxies return like seasons. The claim is that the causal structure of spacetime continues, while the notion of size resets and the bookkeeping of distances is replaced. The last light becomes the first light, once geometry is allowed to change its ruler, and once late stops meaning what it used to. The idea depends on a crucial condition. Massive particles must either decay, lose mass, or become irrelevant compared with radiation, because mass would reintroduce a scale and spoil the conformal trick. CCC often leans on the possibility that rest mass might fade in the deep future, or that only massless degrees of freedom matter at the boundary, even if some massive relics technically persist. This is not established physics. It is a hypothesis about what survives when the universe has run out of structure, and about which terms in the equations still count. CCC turns that uncertainty into a doorway, and it invites us to ask whether mass is permanent or emergent. The guide and provocateur behind CCC is Roger Penrose. He is a Nobel laureate celebrated for work on black holes and the deep geometry of spacetime, including theorems that made gravitational collapse mathematically unavoidable under broad conditions. He's also known for resisting fashionable consensus when he thinks the math points elsewhere, even when the alternative is hard to test. Penrose has a reputation for ideas that are elegant, difficult, and sometimes infuriating. His proposal matters even if it is wrong, because it forces cosmology to define what it means by an end and what counts as an explanation. Penrose's contrarian streak is not mere contrariness. CCC is framed as a conservative extension of known principles, especially the behaviour of light and the role of conformal geometry, which has a long pedigree in relativity. It tries to avoid speculative new fields that drive a bounce, and instead uses the universe's own dilution as the mechanism that makes the mapping possible. The model asks us to take the far future seriously, not as an afterthought, but as a boundary condition that shapes the whole story. It also asks us to accept that what looks like infinite time might be a coordinate artifact, an illusion produced by insisting on a ruler that no longer exists. A cyclic model must face a hard requirement. It must leave traces that can be checked, because otherwise it is only philosophy dressed in equations. CCC claims it does. Penrose and collaborators have argued that violent events in the previous aeon, like supermassive black hole mergers, could leave imprints that survive the conformal mapping. Those imprints would appear as subtle patterns in the cosmic microwave background, the oldest light we can observe because the CMB is our earliest photograph of a hot, dense universe. The CMB becomes a potential message from before our beginning, written not in words but in statistics. The proposed signals are often described as low-variance circles or other anomalous structures in the CMB. The claim is that these features could be echoes of energy released before our Big Bang, compressed into our early universe, and then stretched across the sky. The counterclaim is that the CMB is a noisy statistical field, and that apparent patterns can emerge by chance when humans search a complex map for shapes. Different analyses reach different conclusions depending on methods, simulations, and assumptions about foregrounds and noise. The evidence is disputed, and that dispute is part of the story, because it shows how hard it is to separate cosmic meaning from statistical coincidence. So the tension is set. Mainstream cosmology predicts a quiet fade-out, with heat death as the final state and no sequel, because entropy has nowhere left to climb. CCC suggests the fade-out is not the end, because scale evaporates and geometry can identify the far future with a new beginning, without violating local physics. One view treats the universe as a one-way thermodynamic process. The other treats the end as a conformal boundary that can be turned into a page break, where the next chapter begins with the same kind of light. This tension is not only about preference, it is about what we consider physical, and about which questions are meaningful when the usual measuring tools vanish. If time requires clocks, and clocks require mass, then a massless future challenges the meaning of time itself. If scale is not absolute, then infinity may not be a wall, but a misreading of the map. If the CMB contains genuine anomalies, then the early universe might carry scars from a previous aeon, faint fingerprints in ancient radiation. If it does not, CCC may still be a useful provocation that clarifies why the standard story is so compelling and why thermodynamics feels so final. The hook is simple and unsettling. What if the universe's final, cold breath is not an ending but a disguised beginning? What if the last black hole's evaporation is not the last event, but the last event we can describe using our current rulers, clocks, and intuitions? In that case, the end of everything is not a point in time. It is a change in what time can mean, and in what counts as a measurable fact. To follow this mystery, we need two things. We need the standard ending in full detail, because any alternative must match it where it works, and must respect the same thermodynamic constraints. And we need to understand what physics survives when structure is gone, because CCC lives in that limit, where only light cones and angles remain. The next step is to walk through the orthodox timeline of cosmic decay, from fading starlight to evaporating horizons, and ask what remains when the universe runs out of clocks. Heat death is the mainstream endgame because it follows two stubborn facts that refuse to negotiate. The universe expands, and the second law of thermodynamics favours higher entropy states over lower ones. Put together, those facts imply a future where usable differences fade, slowly, relentlessly, until almost nothing can happen. Entropy is not just messiness, and it is not a moral label pinned to disorder. In physics, entropy is a count of microscopic configurations consistent with the same macroscopic appearance. It is the number of hidden ways a system can be arranged while still looking, from afar, like the same thing. That definition matters because macro is what we can measure, while micro is what we usually cannot. A thermometer reads one number, yet the molecules beneath it can be arranged in countless patterns. Entropy is the bridge between those levels, and it turns ignorance into a precise quantity. Imagine a deck of cards laid out in perfect order on a felt table under bright studio lights. There are very few arrangements that look exactly like that tidy sequence, yet there are astronomically many that look scrambled. If you shuffle blindly, you almost always move toward the more numerous outcomes, because probability leans heavily toward the common. Now scale that intuition up to gases, plasmas, and galaxies, and the logic stays the same. A state is not one arrangement, but an entire family of arrangements that share the same visible summary. The summary might be pressure and temperature, or it might be density and expansion rate across cosmic space. That statistical bias becomes the arrow of time in physics, and it does so without any need for intention. The future is the direction in which the number of compatible microstates typically increases. We experience later as the direction where more arrangements are available, and therefore where change is more likely. This is why irreversibility feels so absolute, even though the underlying laws can be time-symmetric. Newton's equations and even quantum dynamics do not demand that a cup must shatter rather than reassemble. The second law emerges because the reassembly would require an absurdly special coordination among countless microscopic degrees of freedom. A useful way to picture this is a landscape of possibilities, with valleys representing common states and narrow ridges representing rare ones. Ordered arrangements sit on those ridges, precarious, unlikely, and easily lost. Once a system tumbles into a broad valley of high multiplicity, it is not forbidden to climb back up, but it is fantastically improbable. In everyday life, entropy rises because systems exchange energy and information with surroundings. A hot mug cools because it shares energy with the room, and the room shares it with the wider building. In cosmology, the surroundings are the rest of the universe, and the rest is unimaginably large. The key idea is free energy, not energy itself, because raw energy can be useless without structure. Complexity needs gradients that can be tapped, like hot versus cold or dense versus sparse. A waterfall matters because of height difference, and a battery matters because of chemical separation. In thermodynamic language, it is the ability to extract work that counts, and that ability is always conditional. Work requires a path from high potential to low potential, and it requires constraints that prevent immediate equalization. Without constraints, energy spreads out too smoothly, and nothing can be steered. When gradients flatten, the ability to do work collapses, even if energy still exists in abundance. Heat death means usable differences become too rare to matter, not that the universe runs out of energy. Energy remains, but it becomes trapped in forms that cannot be organized into engines. Classical thermodynamics was built on boxes, pistons, and steam engines, where the container is fixed and the walls stay put. Cosmology adds a twist that classical thermodynamics did not face. The container is not fixed because space-time itself grows. The box is the geometry, and the geometry changes. That change is not a metaphor, and it is not a motion through space like debris flying outward. In general relativity, expansion is encoded in the metric, the rule that tells you what distances mean. The scale factor grows, and with it the separation between co-moving points, points that are simply carried along by the cosmic flow. Expansion matters because it dilutes matter and stretches radiation, and both effects weaken interaction. As volume increases, densities fall, collisions become rarer, and reaction rates slow. Even processes that are possible in principle become irrelevant in practice, because the universe becomes too thin to keep them going. Visually, you can imagine a glowing fog of particles that slowly spreads out across a darkening stage. At first, sparks collide, fuse, and scatter light in every direction. Later, the same fog becomes so rarefied that the sparks almost never meet, and the stage looks empty even though it is not. The cosmic microwave background already shows this cooling trend in a measurable, almost intimate way. Its temperature drops as the scale factor grows, because photon wavelengths are stretched by expansion. A photon's energy is tied to its wavelength, so redshift is not just a color change, it is a draining of usable energy. Today the microwave background is about 2.7 Kelvin, a faint afterglow that fills every direction like a whisper. In the deep future, that glow will slide to longer and longer wavelengths, becoming radio, then something even more diffuse. The universe does not turn off, but it becomes harder to distinguish from silence. If you could watch that background with impossible patience, you would see its spectrum glide downward like a note falling below hearing. Peaks shift, intensities thin, and the sky's last uniform light becomes a stretched, cold haze. It is a visual quieting that mirrors the thermodynamic one. In the far future, the average temperature trends toward near zero, but the approach is subtle and never quite simple. It does not guarantee absolute zero, because horizons and quantum fields complicate the limit. Even empty space in modern field theory is not truly empty. Its lowest energy state still seethes with fluctuations. Those fluctuations are not free energy waiting to be harvested at will, because they do not provide a stable gradient. They are jitter without a handle, and they average out when you try to build a macroscopic machine. Yet they remind us that nothing is a physical medium with rules, not a blank void. Maximum entropy in an expanding space-time is not a single frozen picture, like a gas perfectly mixed in a sealed room. It is an asymptotic approach where no remaining process can create new, large gradients. The universe can keep changing in tiny ways, yet the changes stop producing new structure that matters on macroscopic scales. Gravity seems like the enemy of heat death because it clumps matter into stars and galaxies, creating striking contrast. Yet gravity also has its own entropy story, and it drives structure toward black holes. In a gravitating system, uniform can be low entropy because there are many more ways to be clumpy than perfectly smooth. A smooth gas cloud can lower its ordinary thermal entropy by collapsing, because the gas becomes more ordered locally. The total entropy still rises because gravitational degrees of freedom open vast new possibilities. In plain terms, gravity creates new ways for the universe to be, and those ways overwhelmingly involve concentrated structures. This is why the universe can form galaxies and stars while still obeying the second law. Local order grows by spending gradients and exporting entropy outward. A star shines by turning concentrated nuclear fuel into a flood of low-grade photons, and those photons carry entropy away into surrounding space. You can picture it as a trade. A small region becomes organized, but only by making the outside more disorganized. The star's core is a furnace with a steep gradient, while the interstellar medium is a sink that accepts the waste heat. The arrow of time is written in that outward flow. The standard timeline is a sequence of diminishing energy sources, and it reads like a slow dimming of cosmic options. Each era ends when its dominant gradients are exhausted or locked away. The universe does not choose to end an era, but the bookkeeping of free energy eventually closes the account. First comes the stelliferous era, when stars shine and chemistry has steady power across billions of years. Fusion turns mass into radiation, and starlight maintains temperature differences between illuminated surfaces and cold space. Planets, atmospheres, oceans, and any complex chemistry are parasitic on that steady gradient. In this era, the night sky is crowded, and the universe is visually busy with luminous disks and spiral arms. Gas clouds collapse, ignite, and blow winds back into their galaxies, enriching them with heavier elements. Those elements matter because they make rocky planets, complex molecules, and the intricate chemistry that depends on them. The physics of fusion is itself a story of gradients and barriers, because nuclei must overcome electrostatic repulsion. In stellar cores, pressure and temperature are high enough for quantum tunneling to help reactions proceed. The result is a slow leak of binding energy into space, controlled, long-lived, and astonishingly productive. Star formation slows as cold gas is consumed, heated or expelled by feedback from supernovae and active galactic nuclei. Galaxies age into populations of long-lived red dwarfs and fading remnants. The bright, massive stars die quickly, leaving behind a quieter, redder cosmos dominated by smaller, steadier suns. On timescales of trillions of years, most luminous stars are gone, and the cosmic light budget collapses. The sky becomes a record of leftover objects rather than ongoing creation. What remains are dim red dwarfs, occasional mergers, and the slow cooling of stellar corpses. Imagine the visual palette shifting as well, from brilliant blue-white points to a deep ember-red sparsity. The bright nebulae fade because there are fewer ultraviolet sources to excite them. Even the concept of a galaxy changes, as spiral arms lose their contrast and become ghostly stellar halos. Then comes the degenerate era, dominated by white dwarfs, neutron stars, and brown dwarfs. These are not engines, but embers cooling in slow motion, each one a compact archive of past fusion. Their internal pressure is supported by quantum mechanics, electron degeneracy in white dwarfs, neutron degeneracy in neutron stars. Degeneracy pressure is strange because it is not thermal, and it does not require heat to persist. It arises from the Pauli exclusion principle, which limits how tightly identical fermions can be packed into the same quantum states. In plain terms, matter resists compression because its quantum seating chart runs out of available seats. White dwarfs radiate away stored heat and approach black dwarf states over unimaginable durations. Their glow fades from white to red to infrared, until they are almost indistinguishable from the cold background. Neutron stars spin down and lose magnetic energy, and their once fierce beams become quiet, intermittent, then absent. Brown dwarfs, too small to sustain hydrogen fusion, cool steadily after their brief early warmth. They become dark spheres drifting through expanding space, occasionally perturbed by passing masses. In this era, the universe still contains matter, but matter increasingly lacks the gradients needed to stay interesting. Planetary systems, if they remain bound, become dynamically unstable over immense times, because gravity never truly rests. Encounters and resonances eject bodies into interstellar and intergalactic space. A planet can be thrown outward like a coin flicked from a table, leaving its star behind forever. In dense regions, gravitational interactions act like a long casino game played with orbital energy. Energy is traded until many objects are flung out and only tight binaries survive. The winners are compact pairs, white dwarf binaries, neutron star binaries, because tight systems are harder to disrupt. Even those binaries are not permanent in the deepest sense, because they can radiate energy away. Gravitational waves carry orbital energy into the void, and the orbit shrinks. Over colossal spans, some pairs merge, producing brief flashes of heat and motion, rare punctuation marks in a mostly quiet epoch. The details depend on uncertain physics, including whether protons decay, a question that ties cosmology to particle theory. If proton decay occurs, even degenerate matter dissolves into leptons and radiation. The very atoms that make up white dwarfs would not be eternal, and solidity would be a temporary illusion. If protons are stable, matter can persist longer, but it still becomes isolated and inert as expansion separates everything. Either way, the supply of accessible free energy keeps shrinking. The universe is not running out of stuff, but it is running out of ways to make that stuff do anything coordinated. The next era is shaped by black holes, which become the dominant structured objects in the long run. They are the natural endpoints of collapse and the deepest sinks of entropy. When matter falls past a horizon, the outside universe loses access to its detailed configuration, and that loss has a thermodynamic price. Black hole entropy is not a metaphor, and it is not optional if we take quantum theory seriously. Bekenstein and Hawking showed that a black hole has an entropy proportional to horizon area. That result links gravity, thermodynamics, and quantum physics in a single, unsettling equation. The area law is startling because it scales like surface, not volume, and it defies ordinary intuition. It suggests the information capacity of a region is tied to boundaries in space-time. In a sense, that is precise, not poetic. The horizon behaves like a storage surface for microscopic degrees of freedom. If you visualize it, the black hole is less like a bottomless pit and more like a boundary with bookkeeping. The horizon is a one-way membrane for classical signals, yet it also acts like a thermodynamic object with temperature and entropy. The universe, in effect, keeps accounts on surfaces. For cosmology, the practical result is clear and measurable in principle. Supermassive black holes dominate the entropy budget of the observable universe today. Even though they occupy tiny volumes, their horizon areas are enormous, and entropy counts possibilities, not size. That dominance matters because it reframes what maximum entropy means in a universe with gravity. The universe can increase entropy dramatically by making and growing black holes. Collapse is not a rebellion against the second law. It is one of the most efficient ways to satisfy it. As galaxies evolve, black holes merge and accrete, then settle into quiet. The last major entropy production events are likely gravitational and horizon-driven. Visually, the universe's final fireworks are not bright invisible light, but deep in space-time itself, ripples, mergers, and the swallowing of matter. At this point, expansion is not just background scenery behind the drama. It becomes a causal filter that decides which regions can ever interact again. If the expansion accelerates, it does more than spread things out. It draws boundaries around what can influence what. Dark energy appears to drive accelerated expansion in our current data, inferred from supernova surveys and the large-scale structure of galaxies. If it remains constant, the universe approaches a De Sitter-like future. That phrase is technical, but the picture is simple. Exponential stretching that never lets up. Acceleration creates an event horizon, a boundary beyond which signals sent now never reach us. It is not a wall in space, but a limit on causal contact. Light can still travel locally, yet the space between distant regions grows so fast that the light never closes the gap. Over time, galaxy groups become isolated islands, each one gravitationally bound and surrounded by expanding emptiness. Distant galaxies redshift away and cross the horizon, leaving each bound region increasingly alone. The sky, from within any one island, becomes emptier not because galaxies vanish, but because they become unreachable and undetectable. The image is hauntingly simple. A local cluster still has stars, remnants, and a central black hole. Yet beyond it, the cosmos becomes a black curtain. The most distant galaxies do not explode or disappear. They just slide beyond the limit where any message can return. What does universe mean when most of it is causally inaccessible? This isolation raises the stakes for any future-to-beginning connection we might imagine. If regions cannot communicate, any global reset must be geometric rather than dynamical. You cannot rely on matter mixing across the cosmos if the cosmos has fractured into causally separated domains. In an accelerating universe, even the meaning of temperature of empty space changes in a way that feels almost like a trick. Horizons carry an associated temperature and entropy, like black holes. A De Sitter horizon has a faint thermal character, implying that even nothing comes with a minimal thermodynamic signature. That temperature is extraordinarily small, yet conceptually it is huge, because it ties cosmic expansion to thermodynamic limits. It suggests the future vacuum is not merely cold, but thermally textured by geometry. Even if no atoms remain, spacetime itself still sets a faint statistical background. So maximum entropy is not simply everything mixed in one box at one uniform temperature. It is a balance between matter, radiation, black holes, and horizon structure in expanding spacetime. The end state is not a tidy equilibrium snapshot, but a regime where no new macroscopic contrast can be sustained. Then comes the key reversal of intuition, the turn that makes the story eerie rather than merely quiet. Black holes do not last forever, even though nothing classical escapes them. Their apparent permanence is a classical illusion, and quantum theory refuses to cooperate with that illusion. Hawking radiation arises from quantum fields near the horizon, where the vacuum behaves like an active medium. The vacuum is not empty, and fluctuations can produce escaping particles with a thermal spectrum. The popular story speaks of particle pairs, yet the deeper point is that curved spacetime reshapes what nothing means. From far away, the black hole behaves as if it has a temperature inversely proportional to its mass. Large holes are colder, and they evaporate more slowly. Small holes are hotter, and their evaporation accelerates as they lose mass, like a candle that burns faster as it shrinks. For stellar mass black holes, evaporation times are immense compared with today's age, dwarfing the age of stars. For supermassive black holes, the times can reach around 10-100 years, a number so large it breaks ordinary intuition. Written out, it is a 1 followed by 100 zeros, a timescale beyond any familiar comparison. During most of that time, nothing dramatic happens from an outside perspective, and the universe continues its slow dilution. The black hole very slowly loses mass, and the surrounding universe keeps thinning. The background temperature keeps dropping, and eventually the black hole becomes warmer than its environment, making net evaporation inevitable. As the black hole shrinks, its temperature rises and the evaporation accelerates, shifting the emitted spectrum to higher energies. The final stage is brief compared with the eons that precede it. In that last instant, the black hole's remaining mass converts into a burst of particles, a final flare in a universe that has forgotten brightness. When the last black holes evaporate, the remaining content is mostly low-energy radiation and other nearly massless particles. Structure becomes a memory with no keeper. The last compact archives of complexity dissolve into a thin, nearly uniform bath of quanta moving at light speed. This is the dark era in the classic forecast, and it is dark in more than one sense. It is not a sudden blackout, but an asymptote toward featurelessness. The universe approaches emptiness the way a sound fades in a vast hall, not with a click, but with a long, thinning tail. The universe still has motion and fields, but it lacks engines that can run for long. Without gradients, there is no sustained complexity, no long-lived chemistry, and no stable ecology of change. You may still have particles, but you do not have the persistent differences that let particles build anything durable. Heat death is often misunderstood as a single moment when everything stops, like a machine switched off. In reality, it is a long approach where the rate of meaningful events trends towards zero. Events still occur, but they become so rare and so energetically small that the cosmos loses its narrative texture. Even the word cold becomes slippery in this limit, because temperature is an operational concept. Temperature can be defined for radiation, yet there may be no observers or devices to operationalize it. A thermometer is itself a physical system with internal degrees of freedom, and those degrees of freedom require gradients to function. The deeper issue is not darkness, but scale, and scale is normally anchored by mass. Physics is usually expressed with rulers, clocks, and masses that set reference units. We do not just talk about meters and seconds, we build them from stable processes, from atomic transitions to orbital periods. If the far future is dominated by massless particles, those reference units lose their anchors in a way that is easy to miss. Photons have no rest frame and no internal ticking that defines duration. A photon does not carry a built-in clock, and it does not provide a natural at-rest yardstick. Distance becomes hard to define without bound systems that can hold a rigid separation. Time becomes hard to define without repeatable processes that can serve as clocks. In a universe of free-streaming radiation, everything moves at one speed, and the usual notion of waiting becomes less physical. We can still write coordinates on a manifold, and mathematics will still allow us to label events. But coordinates are not measurements, and labels are not standards. Measurement requires physical standards that survive long enough to compare, and it requires localized systems that can store records. This is the crack in the wall where the central question returns, and it returns with sharper teeth. After heat death, does the universe truly end? Or can the far future connect to a new beginning? If the tools used to define after dissolve, what exactly are we claiming when we say time continues? The standard story assumes time keeps meaningfully flowing forever, even if nothing much happens. It assumes the far future is just more time, stretched thin but still operational. That assumption is usually left implicit, because in ordinary eras clocks exist and the assumption feels harmless. Yet if everything becomes effectively radiation, the laws gain a special symmetry that changes what scale means. Massless physics can be insensitive to overall scale, caring more about angles and light cones. In plain language, if nothing has rest mass, the universe can lose the physical meaning of how big, while keeping the meaning of what is connected to what. That symmetry hints at a strange possibility, and it is why the heat death story does not fully close the book. If scale stops being physical, then an infinitely large old universe might be redescribed without its usual yardsticks. A description without yardsticks can sometimes be mapped to a description of a different epoch, if the geometry allows it. To see why heat death became the default expectation, we need its historical spine, because this idea was not born in cosmology. 19th century thermodynamics turned irreversibility into a quantitative law, motivated by steam engines and the limits of industrial power. Clausius formalized entropy, and Kelvin popularized the idea of a heat death for the world, long before modern cosmology existed. Those early arguments were not about galaxies, but about coal, work, and the efficiency of machines. Carnot's insights showed that even ideal engines cannot convert heat into work without a temperature difference. Once that lesson was learned on Earth, it was almost inevitable that thinkers would ask whether the cosmos also spends its gradients. When general relativity and cosmic expansion arrived, the second law gained a cosmological stage that made the old worry feel scientific. The universe looked like a system evolving toward equilibrium, not away from it. Early debates about the fate of the cosmos began to sound like engineering, except the engine was space-time itself. Modern cosmology adds precision through the cosmic inventory, and it does so with data rather than philosophy. We track matter, radiation, dark matter, and dark energy, then extrapolate their dilution and interactions. The equations are simple in outline, yet the consequences stretch across timescales that dwarf the age of stars. The result is not a prophecy of doom, but a conservative extrapolation from what we measure today. If the parameters stay close to what we measure, gradients keep fading and horizons keep isolating. The forecast is not certain in every detail, but its direction is robust because it relies on expansion and statistics. Still, maximum entropy must be stated carefully, because it is easy to smuggle in the wrong picture. It does not mean every point has identical temperature at all times, because expansion keeps redshifting radiation. It means no available process can create new macroscopic order without an external gradient, and in the far future there is no external reservoir left to borrow from. Black holes make this logic feel final because they hoard entropy behind horizons, hiding microstates from the outside. Hawking evaporation then releases that entropy as diffuse quanta, erasing the last compact structures. The end is not an explosion, but a conversion. Dense, structured objects become thin, unstructured radiation. So the dread in heat death is not violence, and it is not catastrophe in the cinematic sense. The dread is the slow loss of contrast, as if the universe forgets how to draw edges. What once looked like a tapestry of galaxies becomes a nearly uniform field, with only faint stretched out remnants of earlier light. And wonder remains because the end is so clean, almost mathematically elegant in its austerity. The same laws that build stars also predict their exhaustion, and the same geometry that expands space also isolates it. The universe is not betrayed by its rules. It is carried to its conclusion by them. If everything ends as radiation, what remains to define distance, time, and scale? The question is not poetic, because physics depends on operational meaning. Without clocks, what is a second? And without bound matter, what is a meter? And without stable masses, what is a kilogram supposed to refer to? This is where Chapter 2 hands the story forward, and it does so by tightening the mystery rather than resolving it. The orthodox endgame is coherent, but it may also remove the very tools used to describe after. If the framework needed to speak about time dissolves, then forever becomes a claim that needs careful translation. The next step is to treat that removal as a clue rather than a dead end, because clues often look like absences. If time and scale depend on mass and clocks, then a massless future may blur endings and beginnings. The universe could approach a regime where the distinction between very large and very small loses physical bite. We return to the opening hook with sharper edges, and with a clearer sense of what is at stake. What if the universe's final cold breath is not an ending, but a disguised beginning? What if the last era does not merely follow the first, but can be related to it by a change in how scale is defined? We do not accept that answer yet, and we do not reject it either, because the mainstream accounting must be finished with discipline. We first finish the mainstream accounting, then ask what geometry allows when the accounting runs out. Only then can the story pivot from thermodynamic fate to the possibility of a deeper scale-free continuity. Heat death sounds like a thermal ending, yet it also threatens measurement itself, because measurement requires repeatable standards, not just surviving equations. In the usual picture, heat death means maximum entropy and minimal free energy, a cosmos where gradients have been erased and usable work has dwindled away. Stars have long burned out, galaxies have thinned, and the sky has dimmed into a near uniform bath of redshifted radiation. Even the last warm embers of structure fade, until what remains is mostly empty space and a whisper of long wavelength light. Yet CCC asks a sharper question beneath that familiar imagery. If the far future contains only massless particles, what does it even mean to compare durations, or to say that anything happens after anything else? If the far future contains only massless particles, physics may keep its formal relations while losing its operational anchors, which is where theory meets the stubbornness of experiment. We could still write symbols for meters and seconds, but nothing would remain to realize them in matter, not even in principle. A theory can be mathematically intact and still be physically mute if no system exists to instantiate its units. The unsettling thought is that the universe might still obey laws, while no longer containing anything that can act as a laboratory. In our current universe, most things we call real are anchored by mass, and that anchoring is more literal than it sounds. Mass allows rest, and rest allows stable systems that can store memory, whether that memory is a bit in a computer, a spin orientation in a crystal, or a chemical bond in a molecule. Even our most refined standards, like atomic clocks, rely on massive constituents held in stable configurations. When we picture a clock, we picture a device that resists being washed away by its surroundings, and that resistance is usually a story about mass and binding energy. Mass is also what lets a system have a rest frame that is not merely a coordinate choice, but a physical possibility for an object you can carry. A massive particle can be at rest in some frame, and that frame defines a local clock because the particle can carry a device that ticks along its own history. A massless particle cannot be at rest, because it always moves at sea, and there is no inertial frame in which it sits still. In the late universe imagined by CCC, the very notion of sitting still becomes harder to cash out. This difference is not philosophical, it is built into relativity's geometry, into the sign of the interval and the structure of space-time itself. Massive objects trace time-like paths, and massless quanta trace null paths, and those two kinds of paths sit on different sides of the same causal boundary. In a Minkowski diagram, time-like world lines live inside the light cone, while null world lines ride the cone's surface like a razor-thin edge. Visually, it is the difference between a path with thickness and a path that clings to the limit of what causality allows. Along a time-like path, proper time accumulates, and a wristwatch can in principle tick, recording a sequence of internal states. Proper time is not a convention. It is the invariant length of a world line measured by the space-time metric. Two observers can disagree about coordinate time, yet if they reunite, they agree on the proper time each has experienced. This is the famous twin paradox lesson, made precise by geometry rather than by storytelling. Along a null path, proper time is zero, in the strict relativistic sense, and that is a mathematical statement with operational consequences. The interval along a light ray is neither positive nor negative, and the metric assigns it no elapsed proper time at all. This is why the phrase "photons don't experience time" persists, even though it must be handled with care. The phrase is shorthand for a geometric fact, not a claim about what light feels. So we say, carefully, that for light there is no experienced passage of time, meaning no proper time along a null trajectory, not a claim about awareness. That is not a statement about consciousness. It is a statement about space-time intervals and what the geometry permits. It is also not a denial that light can be emitted, travel and be absorbed. It is a claim about the invariant time measured along that path. In a universe made only of such paths, the usual bookkeeping of before and after loses a familiar reference. Photons still have frequency, and fields still oscillate, and interactions still occur, even in a universe stripped to radiation and thin, rare encounters. A wave can have a period, and a quantum can carry an energy proportional to that frequency. Yet frequency is not a clock unless something can count cycles, store the count, and compare it to another count later. Without memory, repetition is not measurement, it is merely motion. A clock is a physical system that repeats, and that repetition must be stable across disturbances and across time, or else it cannot serve as a standard. Stability usually means a bound system with a characteristic energy scale. Because bound systems resist being smeared out by noise, a pendulum is stable because gravity and inertia define a restoring force, while an atom is stable because quantum mechanics quantizes its allowed states. The deeper point is that clocks are not abstract numbers, they are engineered islands of regularity. Atoms provide clocks because their transitions have fixed energies set by masses and charges, which is why spectroscopy became a backbone of modern physics. The electron mass and the fine structure constant set the scale of atomic spectra, and those spectral lines can be used as exquisitely repeatable references. When we define the second using the hyperfine transition of cesium, we are quietly relying on a hierarchy of masses and couplings that make that transition sharp. Historically, this shift, from Earth's rotation to atomic transitions, was a recognition that the cosmos is messy, while quantum structure is remarkably consistent. Molecules provide clocks because their vibrations depend on reduced masses and bonds, and those masses enter like weights on a spring. The frequencies of vibrational and rotational modes shift if masses change, because the inertia of the nuclei enters directly into the quantum energy levels. Even the chemistry of life, which feels so distant from cosmology, is a tapestry woven from mass scales. If those scales were absent, even the idea of a molecule would dissolve into unbound fields. Even a spinning planet is a clock because its inertia resists change, and because angular momentum provides a kind of persistence across eons of disturbance. Earth's rotation is not perfectly stable, yet it is stable enough that it once defined the day and anchored human timekeeping. Even a decaying particle is a clock because its lifetime is set by couplings and mass scales, and because exponential decay provides a statistical arrow of time. In every case, the universe gives you a repeatable process only because something is heavy enough, or bound enough, to keep repeating. Remove mass, and you remove the natural numbers that define size and duration, at least in the practical sense that physics can operationalize. You can still label events, yet you lose an intrinsic ruler for comparing them, because no bound systems remain to set a preferred scale. Without a scale, twice as long becomes a sentence without a referent. The mathematics still speaks, but the universe no longer supplies the objects that make its words testable. This is the vanishing of scale that CCC treats as a physical clue, rather than a mere mathematical trick. If nothing has rest mass, the universe may still have structure, but not absolute size because only ratios that do not require a fixed unit remain meaningful. The world becomes describable by shapes and causal relations, not by calibrated lengths. It is like keeping the outline of a drawing while throwing away the ruler that set its dimensions. Scale matters because it turns equations into predictions with units, and units are how theory meets observation. A mass implies a Compton wavelength, and that wavelength defines a characteristic length through quantum mechanics, even if we never measure it directly. The Compton wavelength is the scale at which localizing a particle costs enough energy to create new particles, so it marks a boundary between classical intuition and quantum field behavior. In a sense, it tells you when a particle stops behaving like a tiny billiard ball and starts behaving like a field that can spawn copies. A mass also implies a rest energy, and that energy sets characteristic times through quantum relations tying duration to frequency. The relation between energy and frequency, which we write as E equals h bar omega, turns a mass scale into a natural oscillation scale. In practice, masses seed the hierarchy of clocks we actually use, from nuclear transitions to atomic transitions to mechanical resonators. Remove those seeds, and the hierarchy collapses into a scale-free description that cannot be pinned down internally. In the deep future, CCC imagines those hierarchies dissolving, not with a bang, but with a slow loss of reference. The universe becomes dominated by radiation, and the remaining degrees of freedom behave as if massless, because any residual masses become negligible compared to the enormous stretching of wavelengths. The cosmos does not need to be literally empty, it needs to be empty of stable, massive standards. The imagery is stark: a black sky, no stars, and a faint uniform glow whose wavelength keeps lengthening beyond any conceivable detector. That claim is strongest if all massive particles decay, or if their masses effectively fade away as meaningful parameters. It is weaker if stable massive relics remain and keep a scale alive, because even a sparse population of massive particles could, in principle, carry clocks. The argument is therefore not only cosmological, but also particle physical. and it leans on what survives for unimaginably long times. CCC's future is built not only from galaxies and expansion, but from the deep question of what the standard model permits at extreme ages. Penrose argues that the relevant limit is what survives as the universe becomes empty and cold, when the last long-lived structures have either decayed or evaporated. In that limit, only the causal structure might remain physically meaningful, because causal structure does not require a ruler, only light cones. If the universe cannot define a meter, it may still define what can influence what. That is a minimal kind of reality, but it is not nothing. To make that idea precise, we need a minimal language for space-time geometry. General relativity is not a force law added to space. It is the rule for measuring intervals, an instruction manual for how clocks and rulers behave in the presence of energy and momentum. Historically, this was Einstein's radical move in 1915. Gravity is geometry, and free fall is not a push but a path. The triumph was that the same framework explained Mercury's orbit, the bending of starlight, and later, the expansion of the universe itself. The metric is that rule, a field that assigns a distance between nearby events, and it is the central object that turns coordinates into physics. It is written as a tensor, but its meaning can be stated plainly. It tells you how to compute the space-time interval from coordinate differences. From the metric we compute the space-time interval, and the interval tells us what can influence what, because it sorts separations into time-like, null, and space-like. In the documentary's visuals, this is where abstract symbols become geometry you can almost see. Time-like intervals allow slower-than-light travel and proper time for massive observers, which is why they correspond to possible histories of material objects. Null intervals define light rays, and they draw the light cones that bound causality, making a sharp distinction between what can be reached and what cannot. Space-like intervals separate events that cannot be connected without exceeding c, so they cannot be linked by any signal consistent with relativity. These categories are not labels we choose, they are the metric's classification of the world. The light cone is the border, and the metric decides where that border lies, event by event. Change the metric and you change the tilt and shape of light cones, which is why gravity can be described as the bending of causal structure. In a strong gravitational field, the future light cone can tip toward a black hole, making escape increasingly difficult. The picture is vivid. The cone leans, the allowed future narrows, and the geometry itself becomes a kind of trap. In ordinary cosmology, we treat the metric as giving both shape and scale, and we usually keep both without questioning the distinction. The scale factor grows, rulers stretch, wavelengths redshift, and clocks dilate in gravitational fields, so timekeeping becomes a story about geometry as much as machinery. The expanding universe is not objects moving through space like shrapnel. It is the metric itself changing so that distances between moving points increase. The same geometry that defines time also defines the way light thins and cools as it travels. CCC asks what happens when scale stops being part of the physical content, and it treats that loss as an actual physical regime rather than a mathematical curiosity. It focuses on a restricted geometry that keeps light cones fixed while allowing overall rescaling, because light cones encode causality, and causality may be all that survives. This is a subtle shift in what we treat as real in the description. It is also a shift in what we think can be measured when the measuring tools have disappeared. That restricted geometry is conformal geometry. A conformal transformation multiplies the metric by a smooth positive factor, changing lengths but preserving angles, and in spacetime the crucial angles are the null directions. The transformation can stretch or shrink every ruler, yet it cannot change which directions are light-like. In other words, it can change the scale of the drawing while keeping the causal arrows pointing the same way. Preserving angles means preserving the light cones, and therefore preserving causal structure, even while distances and durations are rescaled away. If two events can be connected by light before rescaling, they can after rescaling, because null paths remain null. Conformal geometry therefore keeps the skeleton of space-time, the network of possible influences, while discarding the flesh of absolute scale. It is a geometry that remembers who can talk to whom, but forgets how far apart they were. Many massless field equations in key limits are conformally invariant or close to it, which is why this symmetry is more than aesthetic. Maxwell's equations for electromagnetism have a special relationship to conformal symmetry in 4 dimensions, and massless wave equations often respect the same structure. Their behaviour depends on the light cone structure more than on absolute scale, which is why conformal diagrams can capture their essential propagation. This is also why light, in a deep sense, is the messenger that survives the loss of rulers. This is why Penrose treats massless physics as the natural language of the far future, where only radiation-like behaviour remains operational. If only massless quanta remain, the universe may become effectively conformal because the remaining dynamics do not care about overall rescaling. The claim is not that nothing happens, but that what happens can be described without a preferred unit. The lingering question is whether description without scale is still a full physical world, or a world stripped down to relations alone. The move sounds abstract, yet it has a concrete payoff for cosmology, because it changes what infinite time looks like on the page. If scale has no intrinsic meaning, then an infinite future can be compressed without changing causal relations, much as a map can distort distances while preserving directions. In a Penrose diagram, infinity can be drawn as a boundary you can point to, rather than a place you can never reach. The visual is a clean, elegant trick, but CCC insists it is more than a trick when clocks no longer exist. Penrose's picture starts with an expanding eon that asymptotically thins toward emptiness, with structure gradually erased by expansion and decay. As time goes on, matter becomes irrelevant, and radiation dominates what is left. Not because radiation gains energy, but because everything else becomes diluted or disappears. The cosmic microwave background, already cold today, would be redshifted to wavelengths larger than galaxies, then larger than clusters, then larger than the observable region itself. In the mind's eye, the last photons become so stretched that their oscillations are slower than any remaining process that could count them. In that asymptotic regime, the metric can be rescaled so the infinite future becomes a finite conformal boundary, a mathematical edge with physical intent. Infinity becomes an edge in a conformal diagram, drawn as a smooth surface rather than a distant horizon. Visually, it is like taking an endlessly stretching sheet and replotting it so its far end fits on the page. The sheet is still the sheet, but the scale markings have been erased. That edge is not a wall of matter, it is a surface where the old scale has been removed, leaving only the causal pattern behind. CCC then proposes matching that boundary to a new beginning, as if the universe's remote future and another universe's earliest moments are 2 descriptions of the same conformal geometry. The end is not a singular crash, it is a limit where our usual yardsticks dissolve. The transition is less like a collision, and more like a change in what counts as a meaningful comparison. The next aeon begins with a big bang that is also dominated by radiation and lacks intrinsic scale, at least in the earliest, most relativistic regime. In standard cosmology, the early universe is hot, dense, and filled with relativistic particles, so masses are often negligible compared to thermal energies. CCC leans on that similarity, suggesting that the beginning already resembles a massless world. In the visuals, the newborn cosmos is a bright, opaque plasma, where light and matter are locked together in a seething, almost uniform glow. The end and the beginning can be identified after conformal rescaling, which is the model's signature move. The match is not a time machine and not a recycling of material content. It is a geometric identification of boundaries. CCC's central claim is that what we call the far future can be re-expressed as a smooth starting surface for a new expansion. It is a proposal about geometry's continuity when scale has become physically meaningless. This is CCC's central claim about the universe after heat death, and it is meant to be read as a statement about what time requires. The far future is not followed by time in the usual sense. It is reshaped into a new start, because usual sense depends on clocks that no longer exist. The proposal is eerie precisely because it turns a physical absence into a mathematical permission. It asks whether the universe can keep causality while letting duration evaporate. The model is careful about what it does and does not assert, because the temptation to imagine literal cycles is strong. It does not recycle galaxies or preserve detailed structures across aeons, and it does not claim that the Milky Way returns in another cycle. Instead, it preserves causal structure and allows certain energetic events to leave faint transformed traces, because causal influence can, in principle, be carried by radiation. The continuity is subtle. like a watermark that survives when the paper is reprinted at a different scale. The continuity is geometric, not material, and that distinction is the heart of the narrative. If anything crosses from one eon to the next, it is not a chunk of matter but a pattern in the conformal structure, like a ripple that survives when the scale is erased. That is why CCCC discussions often focus on extremely energetic, extremely rare events, where the imprint might be robust under rescaling. The question becomes, what kinds of cosmic signatures are scale-free enough to persist? Yet a conformal matching raises an immediate question about thermodynamics, and it is the question that refuses to be charmed away. If the previous aeon ends at high entropy, why does the next begin in a low entropy state, with the extraordinary smoothness we infer from the cosmic microwave background? This is the biggest conceptual hurdle, because the second law is not optional, and any cyclic story must face it without hand-waving. If entropy is the price of time's arrow, how can the arrow be reset? The early universe was hot, but it was also remarkably uniform, and that combination is the puzzle's sharp edge. Temperature variations in the CMB are only at the level of tens of microkelvin on a 2.7 Kelvin background, which is a startling degree of smoothness for something that should have been chaotic. So why did the universe begin in such an ordered gravitational configuration, rather than in a lumpy state already filled with collapsed structures? The sky, when mapped in microwaves, looks like a near-perfect sphere with only tiny freckles of variation. Penrose's answer separates ordinary thermal entropy from gravitational entropy, and he argues that we have been mixing them too casually. In his view, the early universe was thermally hot but gravitationally ordered, and those are not contradictory statements. A gas can have high thermal entropy while the gravitational field remains smooth, because gravity's disorder is not about particle velocities, but about curvature patterns and clumping. Put simply, heat can be randomized while spacetime remains unusually unwrinkled. A smooth early cosmos has low gravitational entropy because gravity has not yet formed clumps and horizons, which are the gravitational equivalents of messy configurations. The specialness is not low temperature, it is low Weyl curvature, meaning the part of curvature associated with tidal distortions and the free gravitational field. In a universe filled with matter, gravity tends to amplify inhomogeneities, so smoothness is not the generic outcome. The fact that the early universe was smooth is therefore, in this view, a boundary condition of astonishing specificity. Weyl curvature measures the part of spacetime curvature tied to tidal distortion and gravitational radiation, and it is what remains when you subtract the curvature directly sourced by local matter density. It is what makes nearby geodesics shear and stretch, and it is what carries information about gravitational waves in vacuum. Penrose links growing Weyl curvature to the growth of gravitational entropy, because as structure forms, the gravitational field gains complexity in a way that resembles increasing disorder. The cosmos begins with a quiet gravitational field, then gradually learns to roar. Black holes then become the main carriers of gravitational entropy, because horizons hide enormous numbers of microstates behind a one-way boundary. The Baconstein, Hawking entropy, scales with horizon area, not volume, which is already a clue that gravity counts states differently. A single supermassive black hole can dominate the entropy budget of an entire galaxy, dwarfing the entropy of all its stars and gas. In the far future, those horizons are like vaults of disorder, storing the universe's gravitational bookkeeping. The late universe is high entropy largely because of gravity, not merely because particles are randomized in a thin gas. It is not merely that particles are randomized, it is that matter has collapsed into deep wells, and horizons have formed that sequester information from the outside. In that view, the arrow of time is written into the growth of cosmic structure as much as into the mixing of gases. The universe's history is a story of smoothness giving way to clumping, and clumping giving way to horizons. CC proposes that at the conformal boundary, when black holes have evaporated, the relevant gravitational degrees of freedom effectively vanish from the description that matters. Hawking radiation slowly bleeds mass and angular momentum away, and over fantastically long times black holes disappear into a thin bath of photons and other light particles. What remains is radiation with no scale, and without horizons the dominant repository of gravitational entropy is gone. The visuals here are haunting. A black hole's silhouette softens, then dissolves into a faint uniform glow. If the Weyl curvature is forced to zero, or becomes irrelevant at the boundary, the next aeon can begin smooth again, at least in the conformal sense CCC requires. The low entropy condition is then geometric, not miraculous, because it is tied to a boundary behavior of the gravitational field rather than to an improbable arrangement of matter. In Penrose's language, the universe begins with a constraint on the free gravitational field. The beginning is special not because matter is arranged just so, but because space-time itself is constrained to be unusually simple. This is a bold claim, and it is not universally accepted, which is part of what makes CCC feel like a live scientific mystery rather than a closed story. Many physicists question whether gravitational entropy can be reset without violating the second law, especially if one insists on a single global accounting across aeons. Others question whether the Weyl curvature hypothesis is a physical law or a boundary condition chosen to make the cycle work. The disagreement is not merely technical, it is about what counts as an explanation. The debate is partly about definitions and partly about dynamics, because gravity's microstates are still obscure. What exactly counts as gravitational microstates, and how do we count them in a quantum theory of gravity we do not yet possess? If we cannot define gravitational entropy precisely, then claims about its erasure or continuity remain suggestive rather than decisive. CCC in this sense sits at the edge of what we can currently formalize. The controversy deepens around mass itself, because mass is the very thing CCC wants to see fade from relevance. CCC often assumes that rest mass fades away in the far future, or becomes irrelevant compared with radiation, because any surviving mass would reintroduce a scale. Penrose's conformal matching works most cleanly when the late universe becomes effectively scale-free. The model therefore leans on a physical expectation that is plausible in outline but uncertain in detail. One motivation is that in an expanding, cooling universe, interactions weaken and massive particles may decay, leaving fewer and fewer stable anchors. Protons might not be eternal, depending on grand unified physics, and even electrons could be destabilized in speculative scenarios, though no evidence requires it today. Another motivation is that without mass, the conformal symmetry becomes exact, so the mathematical identification becomes physically natural. The tension is obvious. The cleaner the symmetry, the more the physics must cooperate, but we do not yet know that all masses can disappear, or that stable massive particles cannot survive forever, quietly keeping a ruler alive. Neutrinos have mass, and their tiny masses still define a scale, even if it is subtle. Dark matter might be massive and stable, and if it is, it could remain as a sparse but persistent population that never becomes truly irrelevant. Even a few enduring masses could, in principle, keep the concept of proper time operational for some observers. If any massive component persists, it can reintroduce a scale and complicate the conformal matching, because a scale-free boundary would no longer be exact. CCC must argue that such remnants do not matter at the boundary, either because they become so dilute that no bound systems survive, or because their influence can be absorbed into the conformal factor without physical consequence. The question is not only whether mass exists, but whether it can still function as a clockmaker. A lone particle is not a civilization, but it could still be a standard in principle. Some versions appeal to speculative physics where mass is not fundamental, or where coupling constants run so that masses effectively vanish in the far infrared. In the standard model, masses arise through the Higgs mechanism, which ties them to a field with a vacuum expectation value, so one can at least imagine scenarios where that effective scale changes. Critics see this as convenience rather than consequence, and they ask for a concrete dynamical pathway rather than a hoped-for symmetry. The model's elegance becomes, for skeptics, a warning sign. Still, CCC's appeal is that it uses known geometric tools rather than a new bounce mechanism, and it tries to make the transition conceptually minimal. It replaces a violent reset with a change of units that becomes physical when units lose meaning, and it tries to make the transition a statement about what can be operationally defined. The mystery is that the far future might be simpler than we assume, not because it is empty, but because it cannot carry standards. What remains is a universe that can still carry causal influence, but cannot carry calibrated time. If only light remains, then the universe may lose the ability to distinguish large from small, and that loss is not just aesthetic. A wavelength can be stretched without limit, but if no mass sets a comparison scale, the stretching is not something any internal observer can calibrate. The cosmos becomes a place where only conformal relationships survive, like a drawing that preserves angles but not distances, The documentary's camera lingers on expanding grids that keep their shape, while their scale markings fade to nothing. In that case, the phrase "after the universe ends" becomes ambiguous, and CCC takes that ambiguity seriously. After requires a clock, and a clock requires a stable scale, and scale requires something like mass or binding energy to make repetition meaningful. CCC turns that ambiguity into a proposal, treating the end of time as a regime where time cannot be operationally defined. The question becomes almost linguistic, but it is anchored in physics. What does later mean when nothing can count? The end of time is not a moment, it is a limit, approached as the universe empties and the last standards decay. It is a condition where the concept of duration loses its physical handle, even if the mathematics still contains a parameter called t. This is not a proof that the universe cycles, it is a reframing of what an ending means, and it asks whether our usual timeline is a coordinate choice that fails at the boundary. If time is what clocks measure, what is time when clocks are impossible? Penrose's conformal diagrams make the idea legible, and they give the narrative a visual spine. They show an eon as a region with light cones intact, and a boundary where scale is removed, so that the infinite future is drawn as a finite line. The next eon attaches at that boundary, inheriting causal structure but not inherited rulers, and the last light of one era becomes the first light of the next. The diagram looks calm, almost simple, which is part of its strange power. Even if CCC is wrong, it forces a hard audit of our assumptions, and that audit is valuable in its own right. We assume time continues because we can write t in equations, yet physics demands operational meaning, and operational meaning demands physical systems that can function as clocks. We assume entropy blocks any sequel, yet gravity's entropy is not the same as a gas in a box, and it may obey deeper bookkeeping than we currently understand. We assume the future is merely more of the same, yet CCC suggests the future might be a change in what can be defined. We assume mass is permanent, yet we do not know its ultimate fate, and we do not know whether the universe has hidden decay channels. Is mass an eternal property, or is it an emergent feature of a particular cosmic phase, tied to symmetry breaking and to the existence of bound states? If the universe can evolve into a phase where mass becomes irrelevant, then our intuition about permanence may be parochial. The thought is unsettling. Perhaps what we call substance is a temporary convenience of cosmic history. So the chapter's question is not whether light can travel forever, because travel is not the same as timekeeping. The question is whether a universe of only light can still define forever, or whether forever is a word that silently assumes a clock. The central question returns with sharper edges. After heat death, does the universe truly end, or can geometry connect the far future to a new Big Bang? And if geometry can do that, what does it mean for the arrow of time we live inside? To test CCC, we must compare it to the standard account of the beginning, because any alternative must match what our best data already demands. That means revisiting the Big Bang, and the problem inflation was designed to solve, because inflation is our best-known tool for explaining early smoothness and causal contact. If CCC can replace inflation, it must reproduce inflation's successes without its mechanism. If it can coexist with inflation, it must explain what each is doing that the other cannot. So we turn from the end that races clocks to the beginning that demanded them, and we return to the early universe where scale was set and where the first smoothness must be explained. We turn from the end of timekeeping to the first moments that made time measurable, and the central question returns in reverse. If the far future can become conformally simple, almost indifferent to scale, why was the beginning so sharply distinguished? In cosmology, that distinction is not poetic language, it is encoded in curvature, temperature, and the way horizons carve the sky. On screen, the familiar image of a fireball tries to intrude, but it misleads more than it teaches. The Big Bang is not an explosion into pre-existing emptiness, with debris flying outward from a center. It is the expansion of space itself, with distances between co-moving points increasing everywhere at once. In that framework, there is no central blast site, no privileged direction, and no outer edge to crash into. A better visual is a grid drawn across darkness, each square stretching as if the paper itself were being pulled. Galaxies are not shrapnel moving through space, they are markers embedded in space as it grows. The recession we measure is largely geometric, encoded in the metric that general relativity assigns to the universe. When we say the universe expands, we mean the scale factor changes, and with it the meaning of distance. Even the redshift is not a Doppler trick alone. It is the stretching of wavelengths as spacetime stretches. This idea has a history that is quieter than the popular myth, and it unfolded through argument as much as observation. In the 1920s, Georges Lemaitre combined Einstein's equations with astronomical redshifts and proposed an expanding cosmos. Einstein had first introduced a cosmological constant to hold the universe static, then reportedly called it a blunder when expansion became plausible. Edwin Hubble's observations then revealed a linear relationship between distance and recession speed, and the implication was hard to ignore. The universe had not always looked the way it looks now, and the past was denser. The Big Bang model, in its modern sense, is a description of an early hot, dense state and its subsequent cooling. It is a framework for how the universe evolves once it is already expanding and filled with matter and radiation. It is not, by itself, a complete story of the absolute beginning, and it does not automatically explain why the initial conditions had their particular values. Even the word beginning becomes subtle when the equations are pushed toward extreme densities. At those extremes, quantum effects are expected to matter, yet we do not have a finished quantum theory of gravity. As we rewind, the universe does not simply get smaller, it gets hotter, because radiation is blue-shifted as the scale factor shrinks. Photons gain energy, particle collisions become more frequent, and the cosmic soup approaches thermal equilibrium. In that early epoch, temperature is not a metaphor but a measurable distribution of energies. The past becomes a laboratory where particle physics and gravity share the same stage. The same equations that govern accelerators and reactors begin to govern the sky. The evidence for a hot early universe is broad and mutually reinforcing, and it arrives from very different directions. Light element abundances match predictions from primordial nucleosynthesis in the first minutes. The cosmic microwave background is the cooled afterglow of that early plasma, still washing over us from every direction. The expansion history also ties together galaxy redshifts, cosmic ages, and the growth of structure under gravity. These are separate lines of evidence that converge on the same early conditions. Nucleosynthesis works because the early universe was hot enough for nuclear reactions, yet not so hot that nuclei could survive for long. In the first second, protons and neutrons interconverted through weak interactions, and their ratio tracked the temperature. As the universe cooled below roughly a mega electron volt, those weak reactions froze out, leaving a neutron fraction that would soon be locked into helium. Neutrons also decay, so the clock between freeze-out and fusion quietly matters. A few minutes later, when deuterium could finally survive without being immediately photodissociated, nuclear fusion proceeded rapidly. The deuterium bottleneck is a simple phrase for a precise balance between photon energies and binding energy. Once that bottleneck breaks, helium-4 forms efficiently because it is tightly bound and energetically favoured. On screen, the plasma can be shown as a seething bath of particles, where brief nuclei flicker into existence and vanish until the temperature drops enough. The timing matters, and the timing is set by expansion. Reaction rates depend on density and temperature, while the Hubble rate sets how quickly conditions change. As expansion cooled the plasma, reaction rates fell and abundances froze in, like a chemical process quenched midstream. Hydrogen and helium emerged as the dominant products, with traces of deuterium and lithium left behind as sensitive thermometers of the early density. These are not arbitrary numbers, they are fossils that constrain the baryon content of the universe. When astronomers measure primordial deuterium in pristine gas clouds, they are effectively reading a relic of the first few minutes. When they infer helium fractions in old stellar populations, they are checking the same early recipe. The remarkable point is not that the predictions are perfect, but that a simple expanding, cooling model lands close to what the sky reports. That agreement turns the early universe into something like a controlled experiment, performed once and observed forever. It also means that any alternative origin story inherits strict numerical obligations. The CMB works because the early universe was once opaque to radiation, more like the interior of a star than empty space. Electrons and nuclei scattered photons constantly through Thomson scattering, keeping matter and light tightly coupled. In that regime, photons could not travel far without colliding, so the universe had no long-range transparency. The cosmos glowed, but the glow was trapped. It was a bright fog, where light existed everywhere and yet could not go anywhere. As expansion continued, temperature dropped to a few thousand Kelvin, and a crucial transition occurred. Electrons combined with nuclei to form neutral atoms in a process called recombination, although it was really the first durable combination. With fewer free electrons available, the scattering rate collapsed, and photons decoupled from matter. The universe became transparent, and light began to free stream across cosmic distances. The surface we see is not a wall. It is a last scattering shell defined by probability. That released light still fills the sky today as a nearly perfect blackbody spectrum, a curve so clean it looks engineered. Its present temperature is about 2.7 Kelvin, and its spectrum matches thermal equilibrium to astonishing precision. This is one of the most persuasive signatures of a hot origin, because it is hard to counterfeit. The CMB is not just radiation, it is thermal radiation, cooled by expansion. On screen, the spectrum can appear as a smooth arc overlaid with data points that cling to it almost unnervingly well. Yet the CMB is not perfectly uniform, and the imperfections are where the story becomes intricate. Tiny anisotropies appear at the level of tens of microkelvin, mapped as mottled patterns across the celestial sphere. On screen, the smooth orange glow resolves into speckles and swirls, like weather patterns on a planet that spans the universe. Those anisotropies encode the seeds of later structure, and they do so with a statistical regularity that can be measured. Each spot is a record of density, velocity, and gravitational potential at last scattering. The standard expansion history also fits the observed Hubble flow and the large-scale distribution of galaxies, which form a web of filaments and voids. It ties together redshift, cosmic ages, and the growth of structure under gravity, using a small set of parameters. In this picture, the universe is about 13.8 billion years old, and the CMB comes from when it was roughly 380,000 years old. The same model that predicts the CMB also predicts how density fluctuations evolve. The web we map in galaxy surveys is the late-time echo of those early ripples, yet the same model raises sharp puzzles when pushed back toward the earliest times, and these puzzles are not cosmetic. They are questions about what the equations imply when extrapolated and about what must be assumed. The closer we approach the earliest moments, the more the universe seems to demand special preparation. It is as if the initial state was not merely hot, but carefully arranged. The first puzzle is the horizon problem, and it is a problem about causal contact and information flow. Regions of the CMB separated by large angles were never in communication in the simplest Big Bang expansion, yet they share nearly the same temperature to extraordinary precision as if they had agreed on a common value. The sky looks coordinated across distances that light, in the standard timeline, could not have bridged. Coordination without contact is the kind of clue physicists learn to distrust. To picture this, imagine the early universe as a growing sphere of plasma, with sound waves rippling through it. There is a maximum distance over which any influence can travel, because signals cannot exceed the speed of light. That maximum distance defines a horizon, a causal boundary set by the age of the universe. At recombination, the horizon size corresponds to only a small patch on today's sky. Beyond that patch, the simplest story offers no time for thermal negotiation. In the standard picture without new physics, the early universe expands too quickly for distant patches to equilibrate. Light could not travel far enough before recombination to smooth conditions across the whole sky. The uniformity then looks like coordination without a mechanism, a coincidence written across the microwave background. The question is not whether the universe is uniform, but how it became so uniform. If nature prefers explanations, what did the smoothing? The second puzzle is the flatness problem, and it is a problem about stability and sensitivity to initial conditions. Spatial curvature evolves in a way that makes near flatness fragile under ordinary decelerating expansion. If the universe is close to flat today, it had to be tuned even closer earlier. The numbers become uncomfortable when the clock is wound back. A tiny deviation early can balloon into a dramatic curvature later, unless something suppresses it. In the Friedmann equations, curvature competes with matter and radiation as the universe evolves. Matter density falls as the inverse cube of the scale factor, radiation as the inverse fourth, while curvature falls more slowly. In a decelerating universe, that means curvature tends to become more important over time, unless it is extraordinarily small. The early universe then seems to require an implausibly precise initial balance. The discomfort is not philosophical. it is mathematical sensitivity. A visual helps here, a ball balanced on a hilltop, where any tiny nudge sends it rolling away. Flatness is not exactly that, but the analogy captures the instability. The closer the universe is to flat today, the more delicately it must have been set near flatness at early times. We're forced to ask whether this is a brute fact or a clue. If it is a clue, it points toward a dynamical attractor that flattens. These puzzles do not prove the Big Bang is wrong, and they do not erase its successes. They show that the simplest version is incomplete as an origin story, because it leaves key features unexplained. They motivate a mechanism that sets initial conditions into the narrow corridor our observations demand. The theory needs a prelude. The prelude must be brief, powerful, and testable. Inflation enters as that mechanism, and it changes the early timeline without discarding the hot Big Bang that follows. It proposes a brief epoch of accelerated expansion before the hot Big Bang phase, when the universe's energy budget behaved like a temporary vacuum. During inflation, the scale factor grows nearly exponentially for a tiny fraction of a second. In that blink, the universe can expand by an enormous factor. The phrase fraction of a second hides a staggering multiplication of size. Accelerated expansion has a distinctive signature in general relativity. Ordinary matter and radiation slow expansion because their pressure and energy density gravitate. A vacuum-like component with sufficiently negative pressure does the opposite, making expansion accelerate. In equations, it is the combination of density and pressure that matters, and inflation exploits that subtlety. In plain terms, the universe can be pushed apart by a form of energy, whose pressure is effectively tension. On screen, the inflating universe is not a fireball, but a rapidly stretching fabric, where a tiny patch swells to cosmic proportions. Accelerated expansion can enlarge a small, causally connected region into the entire observable universe. It can make distant regions share a common thermal history before they were stretched apart. The horizon problem becomes a memory of an earlier, smaller domain that once fit inside a single causal neighborhood. What looks like coordination is reinterpreted as shared ancestry. Inflation also drives the universe towards spatial flatness in the observable region, and it does so with brute efficiency. Exponential stretching dilutes curvature the way it dilutes unwanted relics, because curvature terms become negligible compared to the dominant vacuum-like energy. The flatness problem becomes a natural consequence of rapid expansion, not a delicate initial tuning. After enough e-folds, the geometry looks Euclidean on observable scales. The ball is no longer balanced. The hilltop has been stretched into a plane. Inflation is usually modelled with a high energy field and an effective potential, often called an inflaton for convenience. The field's energy density behaves like a temporary vacuum energy, with negative pressure arising from potential dominated dynamics. That negative pressure causes accelerated expansion in general relativity, because it contributes to the gravitational source term. In plain terms, the field acts like a spring held high on a hill, storing energy that drives expansion. The spring does not push matter outward, it changes how space-time itself evolves. The details depend on the shape of the potential, which determines how long inflation lasts and how smoothly it ends. A flatter potential allows slow roll, where the field changes gradually and the vacuum-like behavior persists. A steeper potential ends inflation quickly, sometimes violently. These are not aesthetic choices, they affect observable predictions. Even the slight tilt in the primordial spectrum is a fingerprint of that shape. The model then needs inflation to end and reheat the universe, because an inflating vacuum is cold and nearly empty of particles. The field's energy must convert into a hot bath of particles and radiation through decay and interactions. This reheating sets the initial conditions for nucleosynthesis and later cosmic evolution, effectively lighting the furnace of the hot Big Bang. The universe becomes filled again, not by compression, but by conversion. On screen, the smooth stretching can give way to a sudden bloom of particles, like sparks filling a dark volume. Inflation is not only a smoothing machine, and this is where it becomes conceptually daring. It is also a generator of structure through quantum fluctuations, taking microscopic uncertainty and stretching it into macroscopic pattern. Tiny vacuum fluctuations in the inflating field and in the metric are stretched to cosmic scales. What begins as quantum noise becomes the blueprint for galaxies. The same randomness that seems like a nuisance in the lab becomes creative on the larger stage. In quantum field theory, even the vacuum is restless, with fluctuations constrained by the uncertainty principle. During inflation, wavelengths are stretched faster than causal processes can erase them. When a mode's wavelength exceeds the horizon, it effectively freezes, because causal microphysics cannot act across it. Those fluctuations become classical density perturbations after horizon exit, in the practical sense that they behave like fixed random fields. The quantum becomes a pattern not by magic, but by loss of causal contact. Later, when the universe expands more slowly, the perturbations re-enter the horizon and causal physics resumes. Gravity amplifies them into the scaffolding for galaxies and clusters, while pressure in the photon, baryon fluid, drives acoustic oscillations. The universe becomes a resonant instrument, and the CMB records the harmonics. The pattern is not arbitrary. It is a spectrum with peaks and troughs. Each peak is a timestamp of compression and rarefaction in the primordial plasma. This mechanism predicts a nearly scale-invariant spectrum of primordial perturbations, meaning fluctuations are similar across many length scales with a slight tilt. It predicts a specific pattern of acoustic peaks in the CMB power spectrum, corresponding to sound waves caught at different phases. It also predicts correlations that match what satellites like WMAP and Planck have mapped with exquisite precision. The data do not merely permit inflation, they often seem to speak its language. The fit is not just visual, it is statistical and parameter-rich. Inflation's success is therefore practical and quantitative, not only philosophical. It explains why the CMB is so uniform and why it is not perfectly uniform. It connects early quantum physics to the large-scale cosmic web, linking the smallest scales we can model to the largest structures we can observe. It is a bridge between the micro and the cosmic. Yet bridges invite the question of what lies on either side. Yet inflation is not a single theory with one clean set of parameters, and this is where confidence becomes cautious. It is a framework with many possible fields, potentials, and reheating histories. Different models can fit the same broad data with different microphysical stories. The umbrella is wide, and that width complicates the search for uniqueness. When many roads reach the same city, the map must be read carefully. That flexibility is a strength and a weakness, and the documentary lingers on the ambiguity. It allows inflation to survive many observational tests because it can be adjusted within a family of models. It also makes it harder to say what inflation uniquely predicts beyond general features, especially when new parameters hide in the reheating details. The more adaptable a framework becomes, the more carefully it must be constrained. Otherwise, explanation risks becoming accommodation. Some versions of inflation lead to eternal inflation, where inflation never ends everywhere, and the idea becomes almost vertiginous. Quantum fluctuations can keep parts of space inflating, while other parts reheat, creating a patchwork of outcomes. The result is a multiverse of bubble regions with different local conditions, separated by inflating space that keeps them apart. Our observable universe becomes one bubble among many. The camera can linger on a fractal-like foam, where new regions bud off as others cool. Eternal inflation raises a measure problem about probabilities, and it is not a technicality but a conceptual fault line. If infinitely many regions exist, counting outcomes becomes ambiguous, because every outcome happens infinitely often. Predictions can depend on how one regulates infinities and defines typicality, which risks turning physics into bookkeeping. The question becomes, what does it mean to say something is likely in an infinite ensemble? When probability loses its anchor, explanation becomes slippery. These issues do not erase inflation's empirical achievements, and they do not turn it into mere speculation. They show that inflation may be an effective description rather than a final explanation, a useful layer above deeper physics. The deeper question becomes what selects the inflating state in the first place, and why it began in the right conditions to start at all. The prelude itself demands a prelude. If inflation is the engine, what started the engine in the first place? At this point, the documentary's hook tightens. We began with a far future that may lose scale and clocks, drifting toward conformal simplicity. We now face a beginning that seems to require an astonishingly special starting point, not merely hot, but ordered in a particular way. The symmetry between end and beginning becomes a tension. It is as if the universe is easy to end, yet hard to start. The low-entropy puzzle is often stated too casually as a claim about smoothness and disorder, as if smooth automatically means random. In ordinary gases, smoothness looks like high entropy, because many microstates look uniform when averaged. A box of air at uniform temperature and density is a high entropy state, because there are countless microscopic arrangements consistent with that uniformity. With gravity included, that intuition flips, and the flip is the heart of the mystery. Gravity makes uniformity precarious rather than typical. In a gravitating universe, clumping increases entropy because gravity opens new macrostates. A smooth mass distribution is not the generic high entropy outcome, because gravity makes uniformity unstable. The generic outcome is structure, collapse, and eventually horizons, where information becomes hidden behind causal boundaries. Gravity turns smoothness into a special condition rather than a typical one. The same force that builds galaxies also builds the entropy budget. The early universe was hot and close to thermal equilibrium in matter and radiation, and that suggests high thermal entropy per particle. The photon bath had an enormous number of microstates, and the distribution was nearly perfect. Yet the gravitational field was extraordinarily ordered because spacetime curvature was unusually simple. Thermal disorder and gravitational order coexisted, and that combination is the clue. It tells us that entropy is not one number, but a bookkeeping across different degrees of freedom. This is why the CMB's smoothness is not a trivial equilibrium state, even though it looks like one at first glance. It is a sign that the gravitational degrees of freedom began in a very restricted configuration, with little room for tidal complexity. The arrow of time seems to be written into that restriction, as if the universe began with a boundary condition that favoured future growth of structure. We're not just explaining what happened, we're explaining why it could happen. Why did the universe begin with so much gravitational room still left to explore? Penrose frames the issue in terms of phase space volume and improbability, using the language of statistical mechanics. The set of initial gravitational states compatible with a smooth Big Bang is tiny compared to the set of allowed states, once gravity is included. The specialness is not a small detail, and it is not a mere aesthetic preference. It is the central boundary condition that makes an arrow of time possible. If the initial state were generic, the future would not look like our history. To make this vivid, the documentary might show a vast landscape of possibilities, with a narrow channel carved through it. Most gravitational configurations lead quickly to clumping, anisotropy, and horizons, which are high-entropy gravitational outcomes. The observed early universe sits in a rare corridor where the geometry is smooth enough to delay collapse. The question is why the universe began in that corridor, rather than in the overwhelming majority of alternatives. Is the corridor selected, or is it simply the one in which observers can arise? Inflation is often presented as a solution to smoothness, and in a limited sense it is. It can take a patch and stretch it, making it look uniform and flat, even if it began with modest irregularities. Penrose's objection is that inflation may move the problem rather than remove it, because it assumes an inflating patch that is already special. The mechanism smooths, but it also requires a smooth start. A smoothing machine still needs a surface to begin with. Inflation requires an inflating state that is itself special in gravitational terms, not merely energetic. It requires a region dominated by vacuum-like energy, with low inhomogeneity, so that accelerated expansion can proceed without being disrupted. The question becomes why such a region existed, why it was large enough, and why it began so smooth. If the inflating state is rare, then the rarity has not disappeared. The origin story shifts one step back, but it does not end. Penrose's deeper claim is that the real low entropy condition is gravitational, not thermal, and he seeks a geometric diagnostic. He focuses on the Weyl curvature, the part of curvature associated with tidal distortions and the free gravitational field. A low Weyl curvature initial state corresponds to low gravitational entropy, because it suppresses the degrees of freedom associated with gravitational radiation and anisotropic distortions. In plain language, it means space-time began almost unwrinkled. The wrinkles are not in matter alone, but in the geometry itself. In the early universe, the Ricci curvature is tied to matter and radiation density through Einstein's equations. The Weyl curvature encodes anisotropy, shear, and gravitational radiation not fixed by local density, and it can exist even in vacuum. A nearly vanishing Weyl curvature means the geometry began with minimal tidal structure, like a calm ocean without swells. That calmness is not guaranteed by thermal equilibrium, and it is not demanded by the known dynamical laws. The equations allow many beginnings, yet we observe a remarkably quiet one. Penrose's whale curvature hypothesis proposes that the Big Bang had whale curvature near zero, and it treats this as a boundary condition. It sets the arrow of time by declaring that the universe begins in a state that strongly suppresses gravitational clumping and tidal complexity. The hypothesis does not claim to derive this condition from known physics, but it names the condition precisely. Naming the constraint is a way of sharpening the mystery. Once the condition is stated clearly, the demand for an explanation becomes harder to evade. As the universe evolves, whale curvature grows as structure forms, and the growth is visible in the sky. Inhomogeneities collapse, tidal fields strengthen, and gravitational radiation becomes possible as massive systems accelerate. The growth of structure then tracks a growth of gravitational entropy, even as local systems can temporarily decrease entropy by exporting heat. The arrow of time becomes a story of geometry becoming more intricate. The calm ocean develops currents, eddies, and storms. Black holes become the extreme case of gravitational entropy, and they make the abstract discussion concrete. Their horizon area encodes an enormous number of microstates in the Bekenstein, Hawking formula, where entropy is proportional to area in Planck units. A universe with black holes is a universe that has explored a vast region of gravitational phase space. The entropy budget becomes dominated by horizons, not by the thermal disorder of ordinary matter. On screen, the smooth early glow can dissolve into a later cosmos, punctured by dark silhouettes and lensing arcs. This is why the beginning looks so strange when compared to the end. The early universe contains almost no horizons and almost no gravitational complexity, despite its high temperature. The late universe contains many horizons and an enormous entropy budget dominated by them, even though it is cold and dilute. Heat is not the only measure of disorder, and gravity changes the accounting. The universe can cool while its entropy still climbs. The arrow of time then seems to depend on a special beginning rather than on dynamical laws alone. The second law explains why entropy increases from a low value, given such a value. It does not explain why the value was low to start with, and it does not specify which degrees of freedom were constrained. The universe appears to have begun with a rule about what kinds of gravitational complexity were allowed. The deepest question is not why entropy rises, but why it had room to rise. This is where CCC re-enters as a rival origin story rather than a poetic coda, and the narration shifts back to the boundary between aeons. CC claims the next Big Bang can be naturally smooth because the previous aeon's far future becomes conformally simple. If only massless degrees of freedom remain, scale loses meaning, and the boundary can be matched without a singular, jagged handoff. The end becomes a template for a new beginning. The story tries to close its loop using geometry rather than coincidence. In CCC, the end of one aeon is not a hot crunch but a cold, dilute limit, where the universe has expanded for an unimaginably long time. After black holes evaporate through Hawking radiation, the dominant gravitational structures disappear, and the remaining content is radiation-like. With no rest mass to set a scale, the geometry can be rescaled without changing causal structure. The conformal diagram becomes the key visual, with light cones preserved as the metric is stretched. The screen can show the same causal skeleton wearing different scales like different costumes. Penrose argues that this conformal boundary can enforce a low whale condition for the next aeon, and that is the conceptual payoff. The next Big Bang inherits a smooth gravitational state because the previous aeon ends without surviving tidal complexity. The arrow of time is then tied to a geometric matching rule, not to an unexplained initial miracle. The universe begins smooth because it ends smooth, in the conformal sense. A boundary condition becomes a bridge between eras, but the promise is also the vulnerability, and the documentary lets the doubt breathe. Does conformal rescaling truly remove gravitational entropy, or does it hide it by changing what counts as scale? If entropy is a count of microstates, a relabeling cannot by itself delete them, unless the relevant degrees of freedom genuinely disappear. The question becomes whether the late-time universe really forgets enough to reset the boundary. Forgetting is a strong claim in physics, and it demands a mechanism. CCC must therefore be judged as physics, not only as philosophical elegance, and the criteria are unforgiving. It must reproduce the empirical successes of the standard early universe story, because those successes are not optional. It must yield the observed CMB spectrum and anisotropies, the acoustic peak structure, and the near-scale invariant perturbations. It must do this without leaning on metaphor where equations are required. Beauty is welcome, but it cannot substitute for a fit. It must also yield the observed cosmic parameters that define our expansion history, because the numbers are now measured with precision. It must fit baryon density, dark matter abundance, and the effective number of relativistic species inferred from the CMB and nucleosynthesis. It must match the observed near flatness and the statistics of large-scale structure, including how clustering evolves over time. Any viable origin story must land on the same sky. The universe is not obliged to match our preferences, but our theories are obliged to match the universe. If CCC replaces inflation, it must provide another mechanism for generating the primordial perturbations, because the CMB's pattern is a quantitative fingerprint. If it coexists with inflation, it must explain what role the conformal matching plays that inflation cannot, and why both are needed. Either way, it must make contact with data rather than metaphor, because cosmology is now an observational science. The microwave background is not a canvas for ideas, it is a measurement. The sky is a dataset, and it is remarkably unforgiving. Inflation's fingerprints include specific correlations and polarization patterns in the CMB, and the documentary foreshadows what will matter later. Primordial gravitational waves would leave B-mode polarization at large angular scales, a twisting pattern distinct from density-driven E-modes. Non-Gaussianity constraints already limit many inflationary models, because the observed fluctuations are close to Gaussian random fields. The sky is not only mottled, it is statistically disciplined. Even the randomness has rules, and those rules are clues. CCCC's proposed fingerprints are different and more controversial, and the narration keeps the tone cautious. Penrose has argued for low-variance circles as possible imprints of violent events in a previous aeon, such as energetic processes associated with black holes. Critics argue these features are consistent with noise, selection effects, or standard statistics, and that the claimed signals are not robust. The debate is not about possibility alone, but about significance. In cosmology, significance is the difference between a hint and a discovery. The documentary does not decide the dispute here, because this chapter is about framing the problem with precision. It sets the stakes and clarifies what must be explained, whether by inflation, CCC, or something not yet imagined. A new origin story must earn its place by matching the sky we actually see, not the sky we wish to see. The universe is generous with beauty, but strict with evidence. If the beginning is special, the evidence of that specialness should be written somewhere. So we end this chapter with a sharpened tension. Inflation explains much, yet it may not explain the deepest specialness of the beginning, the low gravitational entropy that seems built in. CCC promises a geometric reason for smoothness, yet it must still reproduce the early universe data with quantitative fidelity. The beginning remains both illuminated and mysterious. We are left with a question that feels almost personal. Why did the universe start with such restraint? The next step is to look where the earliest information is preserved most cleanly, before stars and galaxies complicate the record. The place to look is the oldest light we can see, stretched into microwaves by cosmic expansion. We turn to the cosmic microwave background, and we ask whether it carries any echo of a prior aeon. We leave the philosophical edge of endings and step into measurement, because CCC lives or dies where predictions meet maps of the microwave sky. The shift is almost tactile. Ideas that sounded poetic now have to survive calibration tables, beam models, and the stubborn arithmetic of uncertainty. In cosmology, elegance is not enough, because a hypothesis must pass through detectors, pipelines, and the quiet tyranny of error propagation. The cosmic microwave background is our oldest photograph, but it is also a calibrated dataset with error bars attached. It was released when the universe became transparent, about 380,000 years after the Big Bang, at a time when matter and radiation finally stopped behaving like a single fluid. Before that moment, photons scattered off free electrons in a dense hot plasma, and information could not travel far without being scrambled. The early cosmos was not dark, but it was opaque, more like the interior of a star than an empty sky. In that plasma, pressure and gravity argued constantly, and the argument left a pattern we can still read. As the universe expanded, it cooled, and the average photon energy dropped until electrons could bind to nuclei and form neutral atoms. That transition, recombination, followed closely by photon decoupling, collapsed the scattering rate, and the mean free path of light suddenly became cosmic. Photons began free streaming, carrying a snapshot of temperature variations and gravitational potential wells imprinted across the last scattering surface. The surface is not a literal shell you could touch, yet it behaves like one in our maps, an ancient boundary drawn by atomic physics. Even the redshift is part of the story, because this light comes from around Z100, when the universe was 1,000 times smaller. When we say oldest photograph, we also mean a photograph taken with a specific exposure time. The last scattering surface has thickness, because recombination happened over tens of thousands of years rather than in an instant. That finite duration blurs the smallest features, and it sets a physical limit on how sharp primordial patterns can appear. Even before we argue about CCC, the CMB already teaches a lesson. The universe records its history, but it records it with a known instrumental blur. In practice, that blur mixes with the telescope's own beam, so theory and hardware share responsibility for what looks sharp. Today that light is stretched into microwaves and fills the sky at about 2.725 Kelvin, a temperature colder than any natural place on Earth. Visually, imagine a dark dome of space, and then imagine that every direction glows with the same faint heat, like a uniform emberscape just above absolute zero. The spectrum is an almost perfect blackbody, a signature of early thermal equilibrium that was confirmed with extraordinary precision by Cope's Pheros instrument. Pheros did not just see microwaves, it measured a curve so exact that deviations would have rewritten early universe thermodynamics. Historically, that result mattered because it ruled out many messy alternatives, leaving the hot Big Bang picture with nowhere obvious to hide. That blackbody perfection is the calm surface, and the anisotropies are the ripples. The deviations from uniformity are tiny, at the level of tens of microkelvin, meaning 1 part in 100,000. Yet those tiny differences are not random noise in the everyday sense. They are structured by physics that can be written down and tested. They encode acoustic oscillations in the photon, baryon fluid, the baryon density that sets peak heights, and the dark matter content that deepens potential wells without adding pressure. They also encode the geometry of space, because curvature changes how a physical scale projects to an angular scale on the sky. In a visual sense, the peaks in the power spectrum are like harmonics from a drumhead, except the drum is the entire observable universe. The standard story treats these fluctuations as a statistically simple field, seeded by inflationary quantum fluctuations, stretched to astronomical scales. In that picture, the pattern is close to Gaussian, meaning its information is largely contained in the two-point correlation function, or, equivalently, the angular power spectrum. The familiar plot of CMB peaks is not decorative. It is a compressed fingerprint of the universe's composition and expansion history. A single curve extracted from a full sky map can tell you the age of the cosmos, the baryon fraction, and the amplitude of primordial perturbations. What looks like a smooth line is actually a treaty between many parameters, each constrained because the peaks shift together in predictable ways. But CCC asks whether the CMB carries more than the story of this eon. If one aeon's remote future is conformally matched to the next aeon's beginning, some violent late events might survive as scale-free imprints. The claim is not that galaxies cross the boundary, or that stars drift intact into a new beginning, because masses lose meaning under the conformal rescaling CCC relies on. The claim is subtler. Patterns carried by radiation, and by the geometry that guides radiation, could persist when the universe is reinterpreted through a conformal lens. The question is almost cinematic. Can the closing credits of one cosmos leak into the opening scene of the next? In CCC, the far future is dominated by radiation and effectively massless degrees of freedom, because massive particles either decay, are swallowed, or become irrelevant compared with the stretching of space-time. That assumption matters, because conformal transformations preserve angles and light-like structure, while washing out absolute scales. It is a mathematical way of saying that if everything becomes light-like enough, the end can be redescribed as a beginning. The observational question becomes narrow and brutal, because mathematics alone is not evidence. Are there statistically significant features in the CMB that look like echoes, not just random fluctuations? If the sky's a record, we have to ask whether it is a diary or a palimpsest. CCC proponents focus on a proposed signal called Hawking points, which are meant to be sharp enough to search for. In this framing, supermassive black holes in the previous Asyon evaporate through Hawking radiation, an effect where quantum fields near the horizon produce particle emission. For stellar mass black holes, that evaporation time is fantastically long, far beyond the current age of the universe. For supermassive black holes, the timescale is longer still, so the idea implicitly lives in a remote cosmic future where ordinary astrophysical clocks have run out. The mechanism is conceptually simple, but physically extreme, because it depends on horizons behaving like thermodynamic objects. Near the end of evaporation, the remaining mass is released as a burst that is extremely energetic in its own frame. Because the temperature of Hawking radiation rises as the black hole shrinks, CCC arguments then invoke conformal mapping, claiming that this final burst can be re-expressed as an injection into the next aeon's early radiation field. The imprint would appear as a localized hotspot in the CMB, with an angular scale set by the mapping and by how the disturbance propagates before recombination. In narration terms, it is a message written in heat, small, circular, and placed on a sky that otherwise looks statistically indifferent. Visually, it is like finding a single warm pinprick on a globe of near-uniform frost. The Hawking point idea tries to be specific about morphology, because specificity is what makes it testable. The spot should be compact and roughly circular, not a random filament that could be blamed on scanning artifacts. It should have a temperature profile that falls away from a center in a predictable way, like a gentle hill rather than a jagged spike. It should be rare enough to stand out from Gaussian fluctuations, yet common enough to be found in full sky data without cherry-picking a single example. Its distribution should not track the Milky Way or known foreground structures, because a cosmological echo should not care where our galaxy happens to be. And if the signal is truly primordial, it should not prefer one observing frequency over another, once foregrounds are removed. A useful visual here is to imagine the CMB map as a mottled sphere, blue and red speckles spread across a globe. Then, somewhere within that speckle field, you search for a slightly brighter dot with a smooth radial fade, as if a pebble had been dropped into a pond long ago. The difficulty is that Gaussian random fields also produce peaks, and some peaks will look smooth simply by chance. CCC is therefore asking the map to do something subtle, not merely contain hotspots, but contain hotspots with the right statistics and the right profile. The challenge is psychological as well as mathematical, because our eyes are trained to promote coincidence into meaning. CCC also inspired earlier claims of concentric low-variance circles, which sound almost like a target pattern stamped onto the sky. The proposed origin is different, but the logic is similar, because it again relies on a violent event in the previous aeon. A supermassive black hole merger could produce an expanding burst of gravitational radiation, a wavefront that carries energy outward at the speed of light. After conformal matching, that burst becomes a spherical disturbance in the early plasma, and when projected onto the last scattering surface, it could appear as a circle. Multiple events from the same region, or repeated episodes, could produce multiple concentric circles with a shared center. On screen, the idea is instantly legible, rings on a cosmic globe, yet the statistics behind ringness are where the real fight begins. The concentric circle claim makes a statistical promise, and it is a promise that can be checked. Along certain rings, the temperature fluctuations should have unusually low variance compared with typical rings of the same radius. The effect should persist under changes in resolution and masking, because a real physical imprint should not vanish when you rebin pixels. It should not be an artifact of how the sky is scanned, or how the map is filtered, because those artifacts often leave telltale alignments with the instrument's motion. If real, it would point to a pre-Big Bang influence that inflation does not predict in its simplest forms. The deeper issue is whether the anomaly is local, like a scar, or global, like a change in the rules. A third family of anomalies is more diffuse and more controversial, partly because it is easier to argue about them without ever agreeing on a single test. Some analyses point to unusual alignments in low multipoles, including the so-called axis of evil, where large-scale modes appear to line up in a way that feels aesthetically suspicious. Others note hemispherical power asymmetry, where one half of the sky seems slightly more active than the other. Still others focus on the cold spot, an unusually large region of lower temperature that invites both cosmological and mundane explanations. These are the features that thrive in the borderland between statistics and storytelling, because they are visible enough to tempt us and broad enough to resist closure. CCC does not uniquely predict these patterns, but they are sometimes discussed as hints that the sky is not perfectly statistically isotropic. The danger is that anomalies can be collected like souvenirs, each one weak, together sounding persuasive. The mind is excellent at building a narrative from coincidences, especially when the sky offers only one realization to look at. A question hangs in the background. Are we seeing a message, or are we seeing the human habit of finding faces in clouds? If the universe hands us a single map, how do we separate an imprint from an impression? To evaluate any of these claims, we need to understand what the CMB maps actually are, because the photograph is not a direct image. Satellites do not measure temperature directly at each point on the sky, as if they were taking a simple snapshot. They measure microwave intensity in multiple frequency bands while scanning in time, recording voltages that must be converted into sky brightness. Mapmaking turns time-ordered data into a sky map by solving for pixel values that best fit the scan pattern and instrument model. Every step introduces choices, some explicit, some hidden in software defaults, that can imprint subtle systematics. Even the definition of zero level matters, because the monopole is removed and only differences remain. Historically, the path from raw signal to cosmological map was itself a triumph. Cope first detected the anisotropies at large scales, then UMAP mapped them with much finer detail, and Planck pushed further with higher resolution and broader frequency coverage. Each mission brought its own scanning strategy, thermal environment, and instrument design, and each had to fight the same enemy: tiny signals buried under much larger foregrounds and instrumental noise. When CCC asks for faint imprints, it is asking us to trust that this entire pipeline is not inventing patterns. The history also matters because each generation learned from the last, tightening systematics that once looked like unavoidable fog. Foreground removal is the first major battleground, because the microwave sky is not empty. The Milky Way emits microwaves through synchrotron radiation from electrons spiraling in magnetic fields, which tends to dominate at lower frequencies and carries a polarized signature. It emits free radiation from ionized gas, produced when electrons scatter off ions without being captured. It emits thermal dust emission from warm grains, which rises at higher frequencies and can look like a glowing veil draped across the galactic plane. Extragalactic sources add radio galaxies, quasars, and infrared emitters, each contributing point-like or clustered contamination. In a visual montage, these foregrounds are like translucent weather systems sliding over the same globe, each with its own texture and color. Each component has a different frequency dependence, so multi-frequency observations allow separation, but never perfectly. In an ideal world, you could decompose the sky like a set of transparent layers: synchrotron, dust, free, and the underlying CMB, and peel them apart cleanly. In reality, spectral indices vary across the sky, dust temperature changes with environment, and instrument bandpasses are not identical to their nominal labels. Foreground cleaning becomes a sophisticated inference problem, not a simple subtraction. Even small mismatches can leave residuals that are coherent across degrees on the sky, which is exactly the scale where CCC searchers like to live. Different teams use different component separation pipelines, and that diversity is both a strength and a source of disagreement. Some fit parametric models for foreground spectra, estimating spatially varying parameters and propagating uncertainties. Others use blind methods like internal linear combination, which minimize variance under constraints but can inadvertently suppress real CMB features. Each method trades bias against variance, and each can leave residuals that are small in amplitude yet structured in shape. Residual foregrounds can masquerade as spots, rings, or alignments if they correlate with the scan strategy or with mask edges. The uncomfortable truth is that cleaned never means pure, it means best effort with quantified leftovers. A claimed CCC signal must survive analysis choices that were not tuned to find it, because tuning is where false positives quietly breed. If a hotspot is only significant in one particular cleaned map, that is a warning sign. If concentric circles appear only after a specific filtering step, that is another warning sign. The CMB is a delicate dataset, and delicate datasets punish overconfidence. The more spectacular the claim, the more ordinary the explanation must be ruled out. Masking is unavoidable because the galaxy is bright and messy, especially near the plane where dust and synchrotron flare. Analysts remove the dirtiest regions of the sky, then infer statistics from the remaining clean fraction, but masks create sharp boundaries that couple modes and distort ring statistics, because the spherical harmonics no longer remain orthogonal on a cut sky. A ring that crosses a mask can have artificially reduced variance if contaminated pixels are removed unevenly. A hotspot near a mask edge can be amplified by filtering choices, turning a mundane residual into something that looks like a deliberate mark. In other words, the very act of hiding contamination can sculpt the statistics you later celebrate. There is also a visual reality to masking that matters for narration. On screen, the full sky map becomes a globe with a thick grey band cut out, like a censored strip across the Milky Way. The remaining sky looks pristine, but it's no longer the whole sky, and statistics derived from it must account for what was removed. The sky is not only a dataset, it is a dataset with missing data, and missing data always complicates inference. When we ask whether the universe wrote a circle, we must also ask what parts of the page we tore away. After cleaning and masking, scientists compare the real sky to simulated skies, because significance is a comparative concept. The baseline is LCDM plus inflation, with parameters fixed by best fits to the CMB itself and to related datasets. Simulations include beam smoothing, anisotropic noise, and the scan pattern, so the mock maps resemble the data in the ways that matter for the test. Analysts then run the same search algorithm on both real and simulated maps, producing a distribution of outcomes under the null hypothesis. The key output is a p-value, the fraction of simulations that produce something at least as extreme as the data. This is the stage where intuition often fails, because rare depends on the rules of the game you actually played. This is where the look elsewhere effect becomes decisive, because the sky offers many places to look and many ways to define extreme. If you search the sky for any unusual circle, you can vary center, radius, thickness, and the statistic used to measure variance. If you search for any hotspot, you can vary smoothing scale, threshold, and profile shape, and you can decide whether to weight pixels by noise. With enough trials, random Gaussian maps will produce seemingly special features, including features that look eerily clean to the human eye. The sky is large, and the space of possible questions is even larger. The correct question is not whether a feature exists, because features always exist in a rich random field. The correct question is whether it is unlikely given the entire search procedure, including all the knobs you turned along the way. A procedure that tries many possibilities must pay a statistical price, because each additional possibility is another chance to fool yourself. CCC searches often live or die on whether that price was paid honestly. In practice, that means counting not just the final test, but the exploratory steps that led you to it. Accessible language helps here, because the logic is simple even when the math is not. If you roll a die once and get a 6, that is mildly surprising. If you roll it 1,000 times, a 6 is guaranteed somewhere, and surprise is misplaced. In CMB searches, the number of effective rolls can be enormous. Because the parameter space is large and because the sky has many pixels, a posteriori choices, made after seeing the data, silently increase the number of trials, even when the paper's headline number does not reflect it. The deeper question is almost ethical. When does curiosity become a claim? That inflation of trials can turn noise into a headline, and it can do so without anyone intending to cheat. Scientists are human, and the temptation to refine a search after seeing an intriguing feature is almost automatic. Yet the difference between exploration and confirmation is the difference between curiosity and evidence. CCC, because it deals in subtle patterns, is especially vulnerable to this boundary. The more flexible the method, the more it can discover what it was built to admire. Many critiques of CCC signal claims focus on this statistical accounting, and the critiques are often technical rather than rhetorical. Some argue that the reported circles or Hawking points were selected after scanning many possibilities, which makes their quoted significance too optimistic. Others show that similar features appear in LCDM simulations when the same filters are applied, suggesting that the method itself manufactures apparent structure. Some find that significance drops when using alternative masks or component separation maps, implying that the effect is not stable. The dispute is not only about one number, but about whether the test was defined before the data were inspected. In a field built on one sky, procedural rigor becomes a substitute for repetition. Instrumental systematics add another layer, because real telescopes are not ideal. Map and Planck have different beams, noise properties, and scan strategies, and those differences matter when you hunt for compact features. A real cosmological feature should appear in both datasets, within expected differences in resolution and noise, but subtle beam asymmetries can create ring-like artifacts around bright sources, especially when scanning repeats along preferred directions. Time domain filtering can imprint stripes or correlated noise that affects variance statistics, leaving patterns that are not cosmology, but are also not obviously instrumental, without careful modelling. The instrument in a sense has its own handwriting. A robust detection must be stable across instruments and across map-making choices, and that stability is a high bar. It must survive different treatments of 1F noise, different de-stripping algorithms, and different assumptions about gain calibration. It must also survive different choices of pixelization and smoothing, because small-scale features can be sensitive to how the map is gridded. When CCC claims a specific morphology, it is implicitly claiming that morphology is not an artifact of these steps. The burden is heavy because the claimed signals are small, and small signals live where systematics like to hide. Polarization can help, but it also complicates, because polarization is weaker and more foreground contaminated than temperature. Temperature anisotropies are dominated by scalar density perturbations, while polarization encodes scattering geometry and velocity fields at last scattering. In simple terms, polarization is produced when electrons see a quadrupole pattern in incoming radiation, so it carries information about local motion and anisotropy. A CCC imprint that perturbs the early plasma might have a correlated polarization signature, and that correlation could serve as a cross-check. Visually, polarization maps look like tiny directional strokes painted over the temperature modelling. Subtle, but potentially decisive. If a hotspot is truly primordial, it may align with specific E-mode patterns, because temperature and E-mode polarization are statistically linked in LCDM. If it is a foreground or noise artifact, polarization correlations may fail, or the signal may appear only in frequency bands where dust polarization is strong. The promise is powerful. A temperature-only anomaly can be ambiguous, but a match temperature, polarization pattern is harder to fake. The complication is equally real. Polarization maps have their own systematics, and the cleaning problem becomes even more delicate. The sky offers a second channel of evidence, but it also offers a second channel of mistakes. So what would count as strong evidence for CCC in the microwave sky? Beyond intriguing pictures and selective statistics, the first requirement is a pre-registered prediction, stated before looking at the relevant data, because pre-registration forces discipline. It must specify the statistic, the angular scale, the expected profile, and the expected abundance, rather than leaving them adjustable. It must also specify how foreground cleaning and masking are handled, because those choices can move the result. Vague predictions invite flexible searches and flexible interpretations, and flexibility is the enemy of significance. In a mystery, ambiguity is atmosphere, but in a measurement it is a loophole. The second requirement is independence of pipelines, because a real signal should not depend on one team's favoured method. The same signal should appear in maps produced by different component separation methods, including ones designed with different assumptions. It should persist under reasonable changes in mask and resolution, and it should not vanish when you slightly alter the ring thickness or the smoothing kernel. It should be detectable by teams not invested in CCC, using code written independently, because replication matters more than rhetoric when the sky is only observed once. Agreement across rival methods is the closest thing cosmology has to a rerun. The third requirement is model comparison, not only anomaly counting, because science is not a contest of oddities. A feature can be unusual under one statistic, yet still not improve the overall fit of a cosmological model. CCC must provide a likelihood that competes with LCDM, not just an explanation after the fact that sounds satisfying. If adding CCC parameters improves fit only by overfitting, Bayesian evidence will penalize it, because extra freedom is not free. The goal is not to tell a better story, but to predict more with fewer degrees of freedom. A model should earn its complexity by paying it back in explanatory power. Even a clean CMB signature would not be enough by itself, because cosmology is now a web of linked measurements. Any cosmological model must be globally consistent with the rest of precision cosmology, not merely compatible with one mapped feature. The same initial conditions that shape the CMB also shape the matter power spectrum because they seed the growth of structure. They affect how galaxies cluster, how gravitational lensing distorts background light, and how baryon acoustic oscillations appear in surveys. A model that explains one anomaly but breaks 3 other datasets is not a viable origin story. The universe does not let you edit one chapter without changing the rest of the book. Large-scale structure provides a hard check because it traces the growth of the same primordial perturbations over billions of years. The amplitude and scale dependence of fluctuations are measured in galaxy surveys and weak lensing maps, and those measurements can be compared to CMB-inferred predictions. BO provides a standard ruler tied to the sound horizon, which is also encoded in the CMB peaks, linking early universe physics to late-time geometry. CCC must reproduce these linked scales without smuggling in inflationary assumptions it claims to replace, because hidden assumptions would hollow out the claim. Consistency across probes is the price of admission, and it is a price that cannot be negotiated away. Gravitational lensing of the CMB itself adds another constraint, because the CMB is not only a relic surface but also a backlight. Planck measures the lensing potential power spectrum, which depends on matter distribution integrated along the line of sight. Lensing subtly smooths the acoustic peaks and converts some E-mode polarization into B-modes, offering an internal consistency check. If CCC changes the primordial spectrum or introduces localized features, it can alter lensing statistics in ways that are already tightly bounded. The CMB in this sense is both the message and the light by which we read later structure. Any claimed Hawking point population must not create lensing or secondary anisotropies that are already ruled out, including distortions from rayonization, the Sunyaev, Zeldovich effect, or unresolved point sources. The microwave sky is not only a surface of last scattering, it is also a record of everything that happened later, layered on top of the primordial pattern. A localized hotspot must be distinguished from a late-time imprint, and that is harder than it first appears. The universe writes with many pens, and the CMB is where their ink overlaps. The question becomes whether the mark is ancient or merely a smudge from a later page. At this stage, the documentary's tension sharpens, because the idea is haunting and the data are unforgiving. CCC offers a possibility that the universe's final darkness becomes a new beginning, and it offers a concrete place to look for traces. The CMB is the one place where that possibility could leave a measurable mark, because it is the earliest electromagnetic signal we can observe directly. Yet the same dataset is a minefield of statistics, foregrounds, and human pattern finding, and it punishes anyone who confuses fascination with inference. The mystery remains, but it is a disciplined mystery, fenced in by what the instruments can actually justify. The difference between an echo and a coincidence can hinge on how the question was asked, and on how many questions were asked before that. A circle can look like a circle because the universe put it there, or because the algorithm was designed to find circles in anything. A hotspot can look like a burst from another aeon, or like a perfectly ordinary peak that happened to be smoothed at the right scale. When the signal is subtle, methodology becomes part of the story. The plot is not only in the sky, it is in the way we interrogate the sky. We can now state the controversy cleanly, without either dismissing it or romanticizing it. CCC-inspired features have been reported, but many independent analyses find them consistent with LCDM expectations once the full search procedure is accounted for. Some signals weaken when correcting for look elsewhere effects, and that weakening is exactly what statistics predicts when you search widely. Some depend on particular smoothing scales or masks, which suggests sensitivity to analysis choices rather than to physics. Some resemble artifacts that appear when scanning a Gaussian random field for rare patterns, because rare patterns are guaranteed somewhere. The sky is generous with coincidences, and it charges interest when we borrow them for meaning. The debate remains unsettled largely because the proposed signals are subtle, and the search space is large, and because subtlety invites disagreement. One team may define the statistic one way, another may define it slightly differently, and the significance can swing. One team may trust one component separation map, another may trust a different one, and the candidate features shift. In this kind of controversy, the most important question is not who is right, but what would make everyone agree. The answer is rarely a louder argument, and almost always a cleaner test. This does not mean CCC is disproven, and it does not mean the standard model is complete, because incompleteness is part of honest science. It means the observational arena is unforgiving, and the burden of proof is high, especially for claims that reach beyond the standard narrative. If the universe really carries messages across aeons, those messages must survive our instruments and our biases. They must be clear enough to rise above a sky that is already rich with structure, and they must not dissolve under replication. A true signal should look less like a clever find and more like an unavoidable conclusion. They must also fit into a cosmology that works everywhere else, because the universe does not grant exceptions for beautiful ideas. A model that changes the earliest conditions must still produce the right abundance of galaxies, the right pattern of lensing, and the right BAO scale. It must also preserve the successes of LCDM where LCDM is strong, because replacing a theory means inheriting its responsibilities. CC, if it is to be more than a metaphor, must meet that standard. The romance of cyclic time has to cash out in numbers. One sentence becomes the chapter's hinge, because the documentary has to move forward without pretending the data are clearer than they are. If the data remain ambiguous, the next battleground is theory, where geometry meets quantum physics in the most extreme objects we know. The story narrows from the whole sky to the darkest points in it, because CCC's most dramatic proposed signals come from black holes. The camera, in effect, zooms from a mottled sphere to a horizon so small it can hide a paradox. Hawking radiation is quantum field theory on curved spacetime, not a fully unified theory, and it sits exactly on the fault line CCC wants to cross. It treats the spacetime background classically, as general relativity describes it, while quantizing fields that live on that background. The result is profound and unsettling. Black holes are not perfectly black, and horizons have a temperature, yet the end state of evaporation raises questions about information, unitarity, and what is lost behind horizons, questions that remain open in quantum gravity. Historically, this is where 20th century physics began to argue with itself, because thermodynamics, relativity, and quantum theory all insist on being taken seriously. If CCC needs black holes to write messages into the next aeon, we must understand what black holes can actually emit and what they can preserve. Can a final burst carry structured information, or is it effectively thermal noise? Can a conformal mapping transmit more than energy, or does it wash away the very details CCC wants to keep? These are not decorative questions, because the observational claims depend on the theoretical mechanism being physically coherent. If the mechanism cannot carry a pattern, then the sky cannot be expected to display one. We close with the documentary's hook in a new register, leaning into mystery without abandoning discipline. What if the universe's final cold breath is not silence, but a faint transmission, one that arrives as a subtle warmth on the oldest light we can see? The microwave sky is where we would first notice it, and it is where we first learn how hard it is to be sure. Now we turn to the engine room of the idea, where the fate of information may decide whether aeons can touch. The next step is not a prettier map, but a harder question. We transition from maps to mechanisms, from statistics to the physics of horizons, because the next step is no longer about circles on a sphere. The next chapter follows the trail into black holes, quantum gravity, and the meaning of an ending that might still remember. We have followed the microwave sky to the edge of a claim. Now we descend into the physics that would make an echo possible. CCC leans on a specific promise, and it is a daring one. The universe's final darkness might be a boundary, not a dead end. In that picture, the far future is not merely empty space cooling forever. It is a surface where one description of space-time gives way to another. That promise runs through black holes, because black holes are the last engines left after stars fade. When galaxies exhaust their fuel, when stellar nurseries go quiet, gravity still keeps a ledger. It gathers remnants, merges them, and leaves behind horizons that can outlast almost everything else. To see why CCC cares, we have to slow down and look at what a horizon really is. In general relativity, a horizon is simple in definition and brutal in consequence. It is a surface that divides causal access, so that signals from one side can never reach the other. Visually, a horizon is not a wall you could touch. It is a boundary drawn by light itself, by the paths that photons can and cannot take. In a space-time diagram, it is the line where future-directed light rays just fail to escape. Yet the classical story is only half the story, because the universe is quantum at every scale. In quantum field theory, the vacuum is not empty, even when no particles are present. It is a state with fluctuations and correlations, a restless baseline that cannot be made perfectly still. Those fluctuations are not optional noise. They are enforced by commutation relations and uncertainty, and they are measurable in subtle ways. The Casimir effect, for example, shows that even nothing can push on metal plates when boundary conditions change. Put quantum fields together with curved space-time and the horizon becomes active. Particle creation appears where classical intuition expects silence. The horizon acts like a kind of amplifier, converting vacuum correlations into real excitations for distant observers. Hawking's result is often told as a particle escaping from inside, but that picture misleads. It is not a classical object tunneling out of a prison. It is a mismatch in how different observers define the vacuum, because time itself is sliced differently near a horizon. Near the horizon, field modes are stretched and mixed by gravity, and the stretching is extreme. Wavelengths that were once microscopic are dragged outward, and their phase relationships are scrambled. Positive and negative frequency components no longer align globally, so no particle in one frame becomes particles in another. One way to say it is pair creation near the horizon, with one partner falling in and one escaping. Another way is Bogoliubov transformations between past and future modes, which is the precise language of quantum fields in changing backgrounds. Either language points to the same outcome, and the outcome is startlingly concrete. The outgoing radiation looks thermal to distant observers, as if the black hole has a temperature. It is not a metaphorical temperature, and it is not a property of the interior. It is an effective temperature associated with the horizon's surface gravity, the acceleration needed to hover just above it. Surface gravity is a geometric quantity, and it measures how sharply spacetime is curved at the horizon. Stronger surface gravity means a hotter horizon and a more intense flux of radiation. In the simplest case, the temperature is proportional to surface gravity, divided by Planck's constant and the speed of light. For a non-rotating, uncharged black hole, temperature scales inversely with mass. Large holes are cold, small holes are hot, and the scaling is unforgiving. A stellar mass black hole radiates at a temperature far below the cosmic microwave background today, so it gains energy rather than loses it. This is why evaporation is slow at first, and for many black holes it is effectively frozen. A supermassive black hole radiates feebly for unimaginable times, with a temperature so tiny it is almost a mathematical whisper. Only when the universe itself cools below that temperature does net evaporation become possible. As mass decreases, the temperature rises, and the power output increases. The shrinkage accelerates because the radiating area decreases more slowly than the temperature increases. In simple estimates, the luminosity scales roughly like 1 over mass squared, so the endgame is not gentle. The late stage becomes a runaway, at least in the semi-classical story. The remaining mass is lost faster because the horizon grows hotter as it contracts. The black hole's lifetime scales like mass cubed, which means the last fraction of mass disappears in a comparatively brief finale. This accelerating end is central to CCC's imagery, and it is easy to see why. A final burst could be the last energetic act of an aeon, a brief flare after eons of dimming. In a visual sequence, the black hole would shrink from a silent shadow into a tiny, bright ember. Yet the details matter, because CCC is not only telling a dramatic story. The spectrum is nearly thermal, and thermal radiation is information poor in a naive reading. A perfect blackbody curve carries little about the specific history of what formed the black hole. CCC wants late-time energy release to seed a localized imprint, not merely a uniform bath. The CMB searches for Hawking points depend on that mapping from a final burst to a specific pattern. The question is whether the physics can naturally produce a concentrated, recognizable signal. Even in standard calculations, thermal is not the same as featureless. Grey-body factors modify the spectrum because the curved spacetime outside the hole scatters outgoing modes. Rotation, charge, and environmental fields can also shape what escapes, although the broad thermal character remains. But Hawking radiation is derived semi-classically, and that is a controlled compromise. The spacetime is treated as classical while fields are quantized, which is consistent when curvature is mild compared to the Planck scale. For large black holes, the horizon curvature is tiny, and the approximation is excellent. It becomes questionable near the end when curvature approaches Planck scales and quantum gravity should dominate. The semi-classical treatment assumes a smooth background, but the background itself is now fluctuating, so the first tension appears, and it is not a minor technicality. CCC needs the last stage to be meaningful, while our tools become least trustworthy there. The very regime where a dramatic burst could occur is also the regime where we cannot rely on the standard derivation. That does not refute the idea, but it makes it conditional on unknown physics. The second tension is deeper, and it has haunted theoretical physics for decades. It is the black hole information problem, which is not about human knowledge. It is about whether quantum mechanics remains self-consistent when horizons form and evaporate. Quantum theory demands unitarity, which means probabilities add up and pure states evolve to pure states. Information, in the technical sense, is not destroyed by time evolution. If it were, quantum mechanics would need a new rule, and that would ripple through every domain of physics. Hawking's original calculation suggests thermal radiation, and thermal radiation seems to erase the details of what fell in. If the outgoing state is exactly thermal, it is mixed, and it carries no record of the initial pure state. If a black hole evaporates completely, where did the information go? The question is not philosophical, it is a consistency test. If information can vanish behind a horizon and never return, then quantum evolution is not unitary for observers who remain outside. That would be a profound change, and it would demand a new framework beyond standard quantum theory. The paradox sharpened because black holes have entropy, and that entropy is enormous. Bekenstein argued that a black hole's entropy should scale with its area, not its volume, because otherwise the second law could be violated. Hawking's calculation then fixed the proportionality constant, tying entropy directly to horizon area in Planck units. Entropy counts microstates, even if we do not yet see them explicitly. If a black hole has microstates, evaporation should reflect them somehow, at least in principle. Otherwise, the entropy would be a bookkeeping trick rather than a physical count. Historically, this problem reshaped quantum gravity research. It pushed physicists toward holography, toward the idea that gravitational degrees of freedom might live on boundaries. It also forced a rethinking of locality, because the horizon seems to scramble information in ways that ordinary quantum field theory does not anticipate. The modern view has shifted, and the shift is not purely aesthetic. Many physicists now expect evaporation to be unitary, meaning the radiation ultimately encodes what fell in. The challenge is to explain how that encoding happens without violating the equivalence principle at the horizon. Holography is one reason for this confidence, and it comes with a powerful example. In anti-de Sitter space and related settings, gravity can be equivalent to a boundary quantum theory. The boundary theory is manifestly unitary, so the bulk process, including black hole formation and evaporation, should be unitary as well. That correspondence is not our universe in detail, but it is a proof of concept. It shows that quantum gravity can, at least in some worlds, preserve information. It also suggests that spacetime geometry might be emergent from entanglement patterns in a deeper theory. The Page curve is another reason, and it turns the paradox into a quantitative target. If evaporation is unitary, the entanglement entropy of the radiation should rise at first, then fall after the Page time. Early radiation is entangled with the remaining black hole, but late radiation must purify the early radiation. Hawking's semi-classical picture predicts only rising entanglement, because each emitted quantum appears entangled with a partner behind the horizon. That monotonic rise implies information loss if the black hole disappears. The Page curve therefore became a diagnostic, a way to test proposed resolutions. Recent work with islands changes the semi-classical bookkeeping in a surprising way. It adds new saddle points in gravitational path integrals, and those saddles effectively enlarge the region that counts as part of the radiation's entanglement wedge. In plain terms, the calculation learns to include parts of the interior when computing the entropy of the exterior radiation. With islands, the Page curve can emerge, consistent with unitarity. The radiation's entropy eventually decreases, as if the interior information is being transferred out. The result is technical, but its implication is simple. The semi-classical story was missing contributions that become important after long times. This is a shift with narrative consequences, because it changes what evaporation means. Evaporation may not be featureless thermal noise after all, even if it looks thermal in coarse measurements. The information could be hidden in subtle correlations, distributed across the radiation in a way that is hard to decode. But it also complicates CCC, because CCC often speaks as if black holes erase gravitational complexity. The Weyl curvature can be drained when horizons vanish, leaving behind a smooth, low-structure end state. If evaporation is unitary, the information is not destroyed, it is redistributed. Then the end state is not simple in an absolute sense. It may be simple only in coarse-grained thermodynamic variables, like energy density and temperature. Under the hood, the radiation could carry an intricate pattern of entanglement, a fossil record written in correlations rather than in lumps of matter. CCC needs a specific kind of simplicity, and it is more demanding than low energy density. It needs scale to lose meaning, not merely energy to spread out. It needs the universe to approach a regime where only angles and light cones matter, and where masses no longer define preferred rulers. So we ask what survives at the end, and the question becomes concrete. Does the universe become effectively massless, not just cold and empty? In CCC, mass is the enemy of conformal matching, because mass sets a scale through Compton wavelengths and rest energy. A massive particle carries a built-in clock, even if it is alone in deep space. Its rest mass defines a frequency, and that frequency defines a timescale. If masses persist, then scale persists in principle, and conformal invariance is not exact. If all particles are massless, physics becomes conformally invariant in a practical sense. Only light cones remain meaningful, because null directions are preserved under conformal rescaling. The difference between a meter and a kilometer becomes a matter of convention rather than a physical distinction. How could a universe lose mass, and lose it for good? There are several routes, and none are settled, but each route has a distinct scientific flavour. Some are particle physics hypotheses, and others are astrophysical processes that play out across absurd spans of time. Proton decay is one route, and it has a long history in grand unification. Many grand unified theories allow baryon number violation, which would make protons unstable. Experiments have not seen it, but the lower bounds on the lifetime still permit decay on timescales far beyond the current age of the universe. If protons decay, baryonic matter dissolves into lighter particles such as positrons, photons, and neutrinos. Chemistry ends, then solids end, and eventually even isolated atoms become impossible. The timescale could be enormous, but finite, and it would remove a major reservoir of rest mass. Even without proton decay, electrons can be removed from ordinary matter over long times. Capture into compact objects is possible, especially as stellar remnants and black holes interact gravitationally. In the deep future, rare encounters become the dominant events, and a single close pass can change a system's fate. Black holes can swallow stray particles, and they do not need much help. Gravitational encounters and slow accretion could feed remnants into horizons one by one. Over times far longer than the current cosmic age, even improbable captures can accumulate into a significant effect. In the far future, most bound structures are disrupted because gravitational systems are not perfectly stable. Encounters eject objects or send them inward, and the slow dance of three-body interactions tends to fling one participant away. Galaxies thin out, star clusters evaporate, and the universe becomes a sparse archipelago. If black holes dominate, they become sinks for rest mass, and CCC then waits for Hawking radiation to return that energy as light. The idea is thermodynamic and geometric at once. Mass is converted into radiation, and radiation is the form of energy that respects conformal symmetry. But there is a hard counterpoint, and it cannot be ignored. Some massive particles might be stable forever, and even a small relic population could matter. The electron appears stable, and its stability is supported by charge conservation and the absence of lighter charged particles. Neutrinos have mass, and their stability is strongly expected because there is nothing obvious for them to decay into. Even a tiny neutrino mass is still a mass scale, and it persists as a feature of the laws. Dark matter might also be stable, because many candidates are designed to be long-lived on cosmological timescales. If stable massive particles persist, the universe never becomes truly massless. Conformal invariance would be broken in principle, even if the breaking is operationally hard to detect. A mass scale can anchor physics, because it provides a reference that does not dilute away. CCC can respond by arguing operational irrelevance, and the argument has a certain austere logic. If everything is so dilute that masses cannot form clocks, scale may still fade from what any physical process can measure. In that limit, the universe could behave as if it were massless, even if masses exist in the equations. Yet that response is not automatic, and it raises a subtle question. A single stable mass scale can anchor physics, even in a thin universe, because it can define a threshold for reactions and a characteristic wavelength. The question becomes whether mass disappears physically or only becomes unmeasurable. CCC needs the stronger claim to feel inevitable, because the conformal boundary is meant to be more than a convenient approximation. It is meant to be a real bridge, a place where the notion of scale genuinely loses its grip. If mass remains in principle, the bridge becomes more fragile. Vacuum stability adds another uncertainty, and it is a reminder that cosmology depends on particle physics. Our vacuum might be metastable, meaning it is not the absolute lowest energy state. A decay could rewrite the far future, and it could do so abruptly, like a phase transition sweeping through space. A vacuum transition could end an aeon violently, preventing the quiet conformal boundary CCC requires. Or it could create a different kind of boundary, with different fields and different symmetry. CCC does not yet have a complete account of such events, because the relevant physics is not settled, so the bridge between aeons cannot be built from black holes alone, even if black holes provide the drama. It needs a geometric rule, something that tells spacetime how to connect one era to the next. Conformal matching is that rule, and it is the mathematical heart of CCC. Conformal matching proposes a way to glue the end of one aeon to the start of the next, without preserving ordinary distances. The key move is to rescale the metric, multiplying it by a conformal factor that can blow up or shrink lengths. Angles are preserved, and null directions are preserved, but rulers are not. Light cones remain unchanged under conformal rescaling, and that is the crucial invariant. Time-like and space-like intervals change, but causal structure persists. In plain language, the pattern of what can influence what remains the same, even as the meaning of how far is rewritten. In Penrose diagrams, infinity can be brought to a finite boundary, and the trick is not merely artistic. The infinite future becomes a surface, a line you can point to on a page, because the conformal factor compresses endless time into a finite coordinate range. This is how relativists make the global structure of spacetime visible. CCC identifies that surface with a new Big Bang, and the identification is bold. The next aeon begins where the previous aeon's conformal time ends, so the far future is reinterpreted as a kind of beginning. The boundary is not a place you could visit, but it is a place the mathematics can define. This is not a bounce in the usual sense, and CCC insists on that distinction. There is no contraction to high density in ordinary proper time, and no reversal of the expansion. Instead, the end is stretched and then squashed by a conformal factor, and the singularity is avoided by redefining scale. The mathematical elegance is clear, and it is part of the appeal. The physical meaning is the open question, because elegance does not guarantee reality. What does it mean to identify two manifolds across a boundary, and what does it mean for fields that live on those manifolds? What fields are continuous, and what data are reset? Are there matching conditions for radiation, for curvature, for quantum states? CCC claims the Weyl curvature can be controlled, and that the boundary condition can enforce low gravitational entropy at the next start. In CCC's language, the early universe is special because it is smooth in a gravitational sense. The Weyl tensor measures tidal distortion and free gravitational degrees of freedom, and low Weyl curvature corresponds to low gravitational entropy. The proposal is that the conformal boundary naturally sets Weyl curvature to zero or close to it. But the mechanism is not derived from a full quantum gravity theory. It is a proposal about how geometry should behave when scale loses meaning. That makes CCC both intriguing and vulnerable, because it lives where our current theories do not fully reach. This brings us to space-time geometry at extremes, where black holes and big bangs are the stress tests. Classical general relativity is extraordinarily successful, but it predicts its own breakdown in certain regimes. Those regimes are marked by singularities, and singularities are warnings that the theory is incomplete. Singularities appear in general relativity under broad conditions, as shown by the Penrose, Hawking singularity theorems. The theorems show geodesic incompleteness, not necessarily infinite density, and that distinction matters. It means spacetime paths end prematurely, so the theory cannot tell you what happens next. Cosmic censorship is a hope, not a proven law, and it is a hope about what observers can see. It suggests singularities are hidden behind horizons, so the worst pathologies are not visible from the outside. If censorship holds, nature protects predictability by keeping naked singularities out of view. But CCC wants to avoid a classical singularity entirely, because it wants a clean boundary. In CCC, the Big Bang is not a conventional singularity, and it is not a place of infinite curvature. It is a conformal boundary where scale is redefined and where the geometry is continued in a different guise. Other cyclic models take different routes, and the comparison clarifies what CCC is and is not. Bouncing cosmologies use contraction, then a bounce from new physics, often invoking modifications to gravity at high density. Some use loop quantum cosmology effects, where quantized geometry can produce a repulsive term near Planck density. Some use ekpyrotic smoothing in a slow contraction phase, where an ultra-stiff equation of state suppresses anisotropies. Those models face their own entropy problems because they must prevent entropy from accumulating cycle after cycle. If each cycle inherits the mess of the previous one, the cycles degrade. CCC avoids that by not recycling matter, and that is a central conceptual move. It recycles only conformal geometry and radiation-like content, while matter in the usual sense is meant to fade away. The price is that CCC must explain why the boundary is physically allowed, not just mathematically writable. A mathematical identification is not automatically a dynamical process, and physics cares about dynamics. Something must enforce the matching, and something must explain why the universe chooses that route. Here the missing piece becomes unavoidable, and it is the same missing piece that haunts every extreme cosmology proposal. We do not have a complete theory of quantum gravity, and we do not have a universally accepted set of rules for Planck-scale spacetime. We can do semi-classical calculations, and Hawking radiation is the flagship example of controlled reasoning without full unification. That success is real, but it has boundaries. We can compute particle creation on a fixed background, and we can include back reaction approximately in limited regimes. We can track how energy loss changes the mass slowly, as long as the curvature remains small. But we cannot yet describe the Planck scale end of evaporation with confidence. We cannot yet describe the earliest moments with confidence either, because the same scales appear. CCC's handoff lives exactly in that gap, and it asks quantum gravity to permit a conformal transition without a singular crash. It asks for a graceful rule at the very edge of our competence. Some approaches hint at tools, and they are worth naming because they shape the modern landscape. Path integrals over geometries suggest that space-time history might be summed over, not fixed. Holographic dualities suggest that space-time might be encoded in a lower dimensional quantum system. Quantum error correction ideas suggest that bulk locality might be approximate, protected by redundancy and entanglement. These hints are not a finished theory, but they change what seems possible. They make it less absurd that a boundary condition could emerge from deeper quantum rules. But none provide a finished, universally accepted account of cosmological initial conditions. None yet derive CCC's matching as inevitable, rather than as an elegant option. So the chapter's climax is not a solution, and it should not pretend to be. It is a confrontation with what we do and do not know, and the confrontation has sharp edges. If black hole evaporation is unitary, the far future may retain hidden complexity and correlations. CCC must show why that complexity becomes irrelevant for conformal matching, not merely invisible to coarse measurements. If stable masses persist, conformal invariance may fail in principle. CCC must show why physics still forgets scale, and why the remaining mass scales do not obstruct the boundary. If vacuum decay occurs, the quiet boundary may never form, and CCC must show why our vacuum survives long enough. If quantum gravity resolves singularities differently, the bridge may look nothing like conformal matching. CCC must compete with other resolutions, and it must do so with predictions, not only with geometry. Now the comparison with inflation returns, because both stories claim to explain beginnings. Inflation adds a dynamical smoothing phase in the early universe, and it is designed to solve specific problems. It stretches quantum fluctuations into classical perturbations, and it drives regions of space toward flatness and homogeneity. In visual terms, it takes a tiny patch and balloons it into a cosmic canvas. Inflation often leads to a multiverse through eternal inflation, where inflation never ends everywhere. It produces pocket universes in an inflating background, each with its own reheating history. The multiverse here is branching, like bubbles forming in a boiling pot. CCC offers a different multiverse language, and the difference is structural. It offers sequential eons rather than branching bubbles, and it ties diversity to the long internal history of each aeon. Instead of many universes side by side, it imagines many universes one after another. Inflation's diversity comes from quantum branching in a potential landscape, and from different ways inflation can end. CCC's diversity comes from the accumulated astrophysics of an aeon, including black hole mergers and the distribution of mass and radiation. Both are speculative in parts, but they speculate in different directions. Their predictions differ in emphasis, and the differences are where evidence can bite. Inflation predicts specific statistical properties of primordial perturbations and possible primordial B-modes in polarization. CCC predicts possible imprints from prior eons and a different account of initial low-whale curvature. Both face contested evidence because the sky is subtle and the data are hard. Neither framework is free of untested assumptions, and neither should be treated as settled doctrine. Inflation assumes an inflaton sector and a reheating history, and CCC assumes conformal matching and an effectively massless far future. Both assume quantum gravity will not sabotage their core steps, and that assumption is the shared vulnerability. So we stand at a fork that may be false, because nature is not obliged to choose between our favourite stories. The real answer could be a third option not yet formulated, built from principles we have not discovered. At this point, the documentary's hook tightens. The end of the universe might be a thermodynamic fade or a geometric handoff. The visuals can linger on a cold, expanding cosmos, where galaxies have slipped beyond reach and only thin radiation remains. If CCC is right, black holes are not only tombs, they are the last scribes, writing energy into the boundary, and perhaps writing it in a way that can be read as structure in the next aeon. The idea is both haunting and precise, because it ties cosmic rebirth to a calculable quantum process. If CCC is wrong, the same physics still teaches something, and it teaches it sharply. It shows how close our theories come to contradiction at horizons, and how much of space-time may be encoded in quantum information. The information problem is not a side plot, it is a clue about what space-time is made of. Quantum gravity is not a missing chapter we can skip. It is the binding that decides whether any cyclic story is physical, and whether any boundary condition is more than a choice of coordinates. The bridge between aeons is not built from poetry, it is built from rules. So we end this chapter with the central question sharpened to a point. After heat death, does the universe truly end, or does geometry permit rebirth? We have reached the bridge, and the bridge is made of uncertainties, each one a test of our deepest assumptions. The final chapter must decide what counts as a scientific rebirth, rather than a metaphorical one. With the evidence contested and the theory incomplete, we return to the central question. What does it mean, scientifically, to say the universe rebirths after it ends? We return to the central question, now stripped of romance and defended by physics. After heat death, does the universe truly end, or can geometry turn an ending into origin? The question sounds poetic, yet it is also technical, because it depends on what we mean by time, scale, and measurable change. Under standard cosmology, the long future is an asymptotic fade of structure. Expansion thins matter, redshifts radiation, and drives most regions beyond each other's horizons. Galaxies that are now neighbours drift apart until even their light can no longer reach us. On the larger scales, the sky grows emptier, not with a bang, but with a quiet loss of contact. In LCDM, accelerated expansion is not just motion through space. It is the stretching of spacetime itself, described by a scale factor that keeps growing. As that scale factor rises, wavelengths stretch with it, and energy densities dilute. Radiation cools faster than matter, and matter thins until interactions become vanishingly rare. Entropy rises, free energy vanishes, and the remaining dynamics become rare and increasingly unmeasurable. Stars burn out, then stellar remnants cool, and even the most stubborn structures erode. If protons decay, baryonic matter dissolves into light particles over immense timescales. If they do not, the story still trends toward isolation and exhaustion. Heat death is not a single event that happens on a date. It is a limit where gradients disappear and the probability of organized change approaches zero. Temperature differences flatten, chemical potentials equalize, and work becomes impossible in the everyday thermodynamic sense. In that limit, the universe does not explode or collapse. It simply stops offering new macroscopic stories. Visually, imagine a cosmic timeline that once bristled with landmarks. the era of recombination, the first stars, the rise of galaxies, and the brief flare of heavy elements. Then the marks thin out like ink running dry, until the page shows almost nothing but blank space. The physics is still there, but the events that make time feel eventful are gone. The earlier chapters pushed a sharper point beneath that quiet. If clocks and rulers require stable, massive systems, then measurement itself becomes fragile. A bath of long-wavelength radiation can exist, yet it cannot easily define duration without a counter. A clock is not merely a number, it is a physical process that repeats in a reliable way. In the early universe, clocks were abundant because matter was dense and interactions were frequent. In the far future, the opposite holds, and the operational meaning of time begins to fray. You can write down a time coordinate in equations, but you may not be able to build anything that experiences it in a structured way. The distinction is subtle, yet it matters when after becomes a question about what can be defined. That operational problem is not a loophole in thermodynamics, it is a statement about what physics can mean. Proper time belongs to time-like world lines, and massless quanta do not carry it. A photon has no rest frame, and along its path the interval is null. If only null trajectories remain, the word after becomes harder to anchor. Even the idea of a tick depends on scale. A second is defined through atomic transitions, and those transitions require bound states and mass. If the far future becomes dominated by radiation and effectively massless particles, the reference points that once set our units evaporate. What remains may still be describable, but it is no longer describable in the familiar way. This is where conformal cyclic cosmology makes its most audacious move. CCC says the far future may become effectively massless and therefore scale-free. If scale loses meaning, conformal geometry becomes the natural language of what remains. The proposal is not that matter survives forever, but that the geometry of light-like structure can outlast matter's ability to define size. Conformal transformations preserve light cones while discarding absolute size. They keep causal structure intact while allowing infinity to be compressed into a boundary. In practical terms, they preserve angles and the distinction between time-like, space-like, and null directions. They do not preserve distances, which is exactly the point when distances cease to be physically meaningful. CCC proposes that the remote future of one aeon can be conformally matched to the Big Bang of the next. The word matched here is careful, almost legalistic, because it is a statement about equivalence classes of metrics. You take a space-time that has expanded without bound, rescale it, and ask whether its conformal structure can be smoothly continued. In Penrose's framing, the infinite future becomes a finite surface, an edge where one description hands off to another. In layered form, the answer becomes two answers that share the same starting facts. Standard cosmology says heat death is a true end of structure, even if time continues mathematically. CCC says the same end state might be redescribed as an origin, because only the light-like skeleton matters. The divergence is not about what happens next Tuesday, but about what end means when scale disappears. CCC does not claim a simple repeating timeline with identical histories. It does not promise that you, or Earth, or any galaxy returns. It claims a sequence of aeons connected by geometry, where time and scale are reinterpreted at the boundary. The repetition is not of events, but of a structural possibility, that a scale-free future can be read as a scale-free beginning. The bridge is not a physical tunnel carrying matter across. It is a matching of conformal structures, a rule about how one space-time description hands off to another. The continuity is in angles and null directions, not in objects and distances. What survives is not a cargo of particles, but a pattern of causal relationships. That distinction matters because it prevents a common misunderstanding. CCC is not a cosmic reset button that rewinds events. It is a proposal that the universe can forget scale so completely that the end can be identified with the beginning. Forgetting here is not psychological. It is the physical loss of any operational handle on absolute size. Historically, this idea sits in a long tradition of using geometry to tame infinities. In the 20th century, conformal diagrams became a standard tool in general relativity, letting physicists draw infinite regions on finite paper. Penrose's own work on singularities and gravitational collapse helped define what beginning and end mean in spacetime. CCC extends that geometric instinct into cosmology, with a claim that is bold precisely because it is so spare. Yet the documentary's tension has never been only philosophical. CCC must face the same demand as any cosmology. It must make predictions that survive new data, not only offer a compelling reinterpretation of old mysteries. A beautiful boundary condition is not enough if the sky refuses to cooperate. We tested the most direct empirical arena, the cosmic microwave background. CCC-inspired searches look for localized imprints like Hawking points and for ring-like low-variance features. The idea is that violent events late in a previous aeon, especially supermassive black hole mergers, could leave faint circular signatures after conformal matching. Those claims remain disputed because significance depends on pipelines, masks, and look elsewhere accounting. The CMB can tell us about early conditions with extraordinary precision. It can also mislead us with foreground residuals and statistical flukes because we have only one sky. The map is a single realization of a random field, and cosmic variance limits what can be concluded at the largest angular scales. Intriguing anomalies are not decisive evidence, even when they are visually persuasive. In visuals, the temperature map looks like a mottled sphere, with hot and cold patches only tens of microkelvin apart. Overlay a mask, and the galactic plane becomes a missing strip, because dust and synchrotron glow drown out the primordial signal. Then change the processing choices and subtle rings can appear or vanish. The lesson is uncomfortable. The data are real, yet interpretation is fragile. Elegance is not evidence, and discomfort with inflation is not a detection of CCC. A theory earns belief by risking failure in ways that are unambiguous. The history of cosmology is a history of beautiful ideas being disciplined by error bars. Even the Big Bang model itself earned trust slowly, through multiple converging lines of observation. So we reconcile the philosophical and the empirical without flattening either. CCC is attractive because it reframes what an ending is, and because it targets the low-entropy puzzle. But the universe does not reward aesthetic coherence unless it also matches the data. In cosmology, the most seductive stories are often the ones that must be tested hardest. We can now say what would actually decide the question, at least in practice. The first decisive tests are next-generation CMB polarization maps with lower noise and better control of systematics. Polarization adds independent structure that can confirm or break temperature-only anomalies. It also carries information about scattering at recombination, which is sensitive to early universe conditions. Polarization is not just a technical upgrade, it is a different kind of evidence. The E-mode pattern is now measured well, and it matches LCDM with striking fidelity. The B-mode pattern is far harder because it is weaker and easily contaminated. If primordial B-modes were detected robustly, they would strongly favour inflationary gravitational waves. Better foreground modelling is not a technical footnote, it is a gatekeeper. Dust polarization, synchrotron complexity, and spatially varying spectra can mimic subtle features. A CCC signal must persist across frequencies, component separation methods, and independent instruments. If it appears only in one band or one pipeline, it is not a cosmological relic. We also need improved statistics for large-scale anomalies. Low multipoles are cosmic variance dominated, so claims must be framed with rigorous null tests and pre-registered pipelines. The goal is not to collect oddities, it is to compare models with honest trial counting. When you search many patterns, some will look special by chance, and that fact must be priced in. Independent probes of early universe physics can also separate stories that look similar in temperature maps. Primordial gravitational waves, if detected, would strongly support inflationary dynamics. Tight upper limits already constrain many inflation models, and they also constrain alternatives. The absence of a signal is not nothing. It reshapes the space of viable beginnings. Large-scale structure, lensing, and spectral distortions provide additional cross-checks. A model that changes initial conditions must still reproduce BAO, matter clustering, and CMB lensing statistics. The web of galaxies is not merely scenery, it is a fossil of primordial fluctuations. Cosmology advances when one explanation survives many linked datasets. The theoretical side has its own decisive bottlenecks. CCC depends on the far future becoming effectively massless, so conformal invariance is not merely approximate. Stable massive particles, neutrino masses, or long-lived dark matter could obstruct that limit in principle. If rest mass never truly disappears, then scale may never fully lose its meaning. This is why CCC often emphasizes a kind of ultimate simplification. In the deep future, Black holes dominate as reservoirs of mass and entropy, while everything else becomes dilute. Then Hawking evaporation, over fantastically long times, removes horizons and returns energy to radiation. In Penrose's framing, the evaporation era is a cosmic laundering of structure, an erasure of the last clumps. CCC also leans on black holes as the last major reservoirs of gravitational entropy. Hawking evaporation removes horizons and can, in Penrose's framing, erase gravitational clumping. But modern work on unitarity suggests evaporation may preserve information in correlations, not destroy it. The radiation may look thermal locally, yet still encodes subtle quantum structure globally. That creates a subtle tension that cannot be waved away. If information is preserved, the far future may be thermally simple, yet quantum mechanically intricate. CCC must explain why that hidden complexity does not reintroduce gravitational entropy at the conformal boundary. The question is not whether the universe is cold, but whether it is truly forgetful. We return to entropy in the arrow of time, because every origin story must face it. The second law explains why macroscopic time has a direction once low entropy is given. The deeper question is why the early universe had low gravitational entropy at all. In gravity, smoothness is special, because clumping is the generic direction of evolution. Penrose framed this in terms of Weyl curvature, the part of spacetime curvature associated with tidal distortion and gravitational radiation. A nearly uniform early universe has low Weyl curvature, which means it is gravitationally ordered in a precise sense. Later, as structure forms and black holes appear, gravitational entropy rises dramatically. The arrow of time is written into the geometry, not only into the temperature. Inflation can smooth and dilute, but it does not automatically explain why the inflating patch was special. It can take a small, smooth region and stretch it, turning microscopic uniformity into cosmic uniformity. Yet it still requires conditions that allow inflation to start, and it raises measure questions about what typical means. CCC proposes a boundary condition that enforces low Weyl curvature at each new beginning. That can look like an explanation, or like relocating the mystery into the rules of matching. If the conformal boundary naturally suppresses Weyl curvature, CCC may explain the smooth start without fine-tuning. If that suppression is assumed rather than derived, the low-entropy puzzle remains, only reframed. The difference between derived and imposed is the difference between mechanism and declaration. Dark energy and horizons also return as a constraint on what after can mean. Accelerated expansion fractures the universe into causally isolated regions, so no global dynamical reset can sweep through. CCC's handoff must therefore be geometric, not a signal travelling through space. The universe cannot pass a message across an event horizon, yet a conformal identification does not need to. That is both a strength and a vulnerability. It avoids the need for matter to cross horizons, because horizons are irrelevant to conformal identification. But it also means the proposal lives at the level of spacetime description, where empirical access is indirect. We are testing a boundary with relic patterns, not watching a transition unfold. At this point, the documentary does not pretend to settle the debate by narration alone. Under standard LCDM, heat death is the asymptotic end of structure and of meaningful measurement. Under CCC, the same future could be conformally equivalent to a new Big Bang, turning an end into a boundary. The difference is not a minor tweak. It is a different reading of what counts as physical continuity. The honest conclusion is that both pictures are currently underdetermined by the evidence. CCC is not ruled out, but its claimed CMB signatures are not yet robust. Inflation is not disproven, but its microphysics and measure problems remain open. In the background, the data keep tightening, and theories keep being forced into sharper commitments. So we end by clarifying what the series has actually learned. The universe forces us to separate three ideas that we often blend. Physical time, operational time, and narrative time are not the same thing in the deep future. When the universe thins out, those distinctions stop being academic. Physical time may continue as a parameter in equations even when nothing changes. Operational time may fail when no clocks can exist and no scales can be compared. Narrative time ends when the universe can no longer support new, recorded differences. The last of these is the one our intuitions cling to, because it is the one that feels like living. CCC exploits that separation in a precise way. If operational scale fades, then conformal geometry can become the only surviving structure. In that regime, the distinction between infinitely late and infinitesimally early can blur, because both are scale-free. The boundary is not a place you travel to, it is a description you arrive at when size stops mattering. Even if CCC is wrong, that lesson remains. The end of the universe is not necessarily a catastrophe, it may be a loss of distinguishability. The deepest future may be simple enough that our usual categories stop applying cleanly. When everything's the same temperature and nothing can form a clock, later becomes a word without a job. We bring the focus back to the human scale without shrinking the science. We're a brief pattern in a long thermodynamic story, built from gradients that will not last. Our bodies, our machines, and our memories all depend on differences, hot and cold, high and low, before and after. The universe gave us those differences for a while, and we learned to read them. Yet we can read origins from faint light, and that ability is itself a cosmic fact. A microwave photon that last scattered when the universe was young can still reach a detector built by creatures on a small planet. That chain of causality is astonishingly long, and it is also fragile. It depends on expansion, transparency, and the persistence of physical law. Cosmology is the art of extracting beginnings from relics that barely reach us. It turns microwaves into parameters, and parameters into histories. It also teaches humility, because one sky must answer questions that feel larger than any dataset. We do not get to rerun the universe, we only get to measure it more carefully. So what happens after the universe ends? In the standard view, the answer is that nothing happens in any meaningful macroscopic sense, because structure and measurement asymptote away. In CCC, the answer is that the far future might be the next beginning, because scale is no longer physical. The same mathematics of expansion can be read as a final dilution, or as a geometric handoff. We close on the only ending that is faithful to the evidence and to the mystery. The last photons of a dying cosmos may be the first light of another, if not in reality, then in the way physics reshapes the word end. On screen, the final glow fades toward darkness, then resolves into a new horizon, sharp, bright and unfamiliar. The page turns, and the question remains disciplined by what the sky will allow us to claim. We followed the universe as it spends its last reserves of difference, burning stars into embers, embers into remnants, and remnants into horizons. We watched entropy rise not as a villain, but as statistics made cosmic, free energy thinning, islands of causality drifting apart and black holes briefly becoming the final engines. Then even those engines fade, and the story turns stranger, because when only radiation remains, clocks and rulers lose their grip, and time becomes a question instead of a backdrop. In that deep future we met the central tension, between a one-way heat death and Penrose's conformal cyclic cosmology, where a scale-free end can be rewritten as a beginning. We tested the poetry against the data, asking whether the microwave sky carries scars of earlier aeons, or only the familiar fingerprints of inflation and chance. And we faced the hardest bridge of all, where Hawking evaporation meets quantum gravity, and where information may be preserved as hidden correlation rather than erased into simplicity. Across every chapter, the same theme kept returning. Mass gives the universe its measures, and without measures, after may be a word with nothing left to anchor it. So what happens after the universe ends, after the whisper has finished and light has nowhere left to go? The most honest answer is that after might not exist in any operational sense, yet geometry could still connect what looks like an ending to what we call a first dawn. If CCC is right, the universe does not reboot by recycling matter. It turns a boundary into a birth by letting scale evaporate, until only light cones remain to carry continuity. If CCC is wrong, it still leaves us with the haunting lesson that cosmological endings may be transformations of description. When the final darkness arrives, it may be the moment the page turns. Watch the next maps of the microwave sky, demand careful statistics and open pipelines, because the decision may come not from philosophy, but from a faint pattern in ancient light.